Uh, Afternoon. You guys can hear me? Let's call this back. Afternoon. You can hear me? Restart. Save the way to. Hi. Good afternoon. So we're starting at 2 o'clock as the poster advertised. I just trying to make sure that the live stream is up. Um, a little bit of noise from my outside today, so if you can't hear me at any point, just ask me to speak up. Hopefully, it's not too bad. But thanks for coming, guys. Please share the link. I just will make sure that the live stream is working now. Uh, Let me just I hope I never just cancel the live stream. Oh, I did not. Guys, I had to literally figure out how to do streaming on YouTube just to get this done. You know? So, but just share the link to anybody if you know somebody who might need it. I'm gonna send it in the group chat right now. So from there you can always get access if it is that you can't make it on the Zoom link. We're going to start at 2 o'clock. All right. Mm. Yes, physician. Mhm. Uh, Make sure they're ready to do some work today, guys. We don't want to start conversation now, but the idea is to try and use the next 2 days to go through all the past paper questions from 2007. I'm gonna mute my friend. Mm-hmm. The idea is to try to go through all of the past paper questions from 2007 go up. So that include 2007 specimen paper, the Trinidad and Tobago specific paper that they had. We're going to try to go through all of them. If we identify questions that we don't comfortable with, we try to consult others about it before the exam. Okay, so the thing about paper one, it's a full repeat paper. As long as you've done at least a decade's worth, you're going to see at least 40, 43, 44, maybe even 45 questions repeat. But you can always a study answer and a SWOT answer, quote unquote, but them not right. So that's why I try to do this because now we can have a discussion about the questions and try to see the solutions as well. So we're going to go through that. Hopefully after it's we know so we can secure the full marks then when we get it. So 2 o'clock, as we say, sharing around you can share the Zoom link and you can also share the YouTube live. I'm not sure how much people on the live now, but we're going to do that. We'll start at 2. Mhm.
Well, let me get in. 40 participants. Ready?
All right. So just give me 1 more minute. I'm going to fill my water bottle. But afternoon, guys. Thanks for coming. Remember to share the link to your friends them who you know need it because the idea is to today and tomorrow's session is to try and set you up for getting the full marks or hopefully close to the full marks when we come to the exam on Thursday. So we're going to go through the past papers. I've been working on them personally so that we can try to go through them smoothly. You don't know physics day, it's not the best, but kind of go through them over some period of time now where I'm going to show you the questions that the answer yeah, and as usual, my internet always frightened when it see people. So hopefully we don't have a lot of issues with my internet today. All right, so 2 o'clock. Go and get up. Ready now to start. Just bring my water close. Can get some feedback. Just to know that the live stream is going okay. Yes, I will be recording the session for sure. And when we record the session, we're going to make it accessible via the website. So let me just share the website link as well. But you can find that website link on the Instagram page. So that's where I try to compile everything. So recordings, resources, anything that I say I'm going to give you guys, it would be on the website. So let me stop. Let me pause my sharing for a second. And let me just go for that link. Okay, it's hot. And then we're going to start. But how are we feeling though, guys? Some of you probably were there for the paper two marathon. I heard that the paper two wasn't the best. I did look at it myself. It is what it is. But how we feel, guys? How we feel? How we feel about the physics? We've been studying, we've been going over about the content because just because it's paper one, that don't mean say you can not know stuff. We're gonna do the summarized version of it, but if anybody wanna like comment how them feel about it, gonna pass. Me wanna hear once. We'll pass. I've been up since yesterday trying to put together everything for you guys in the so we're not working for pass. We're going to get as much as we can. Not the best, no. That's how it goes. But all right, so I'm gonna start the recording and then I'm gonna give you guys a little idea of what we're going to do for the day, do a prayer, and then we're going to start immediately. So let me just start recording to the cloud. Um, the live stream should be okay as well. Make sure I set it up this time so that anybody, if they're not getting through here, you can get through on the live stream on YouTube there. So good afternoon again, guys. For those who don't know me, my name is Jeremiah. I'm a physics unit 1 tutor and a university student. So guys, the idea is that and you probably do some of your paper ones already. As a person who had done the 3 sciences, I can tell you for a fact that paper ones repeat. But the thing about it, you have to actually go through at least a decade's worth of paper if you can say, yo, I'm going to the exam and I'm going to see all of them questions again. Because if you spend the time to go through a decade's worth, you're going to see all of the questions and what them are make from 2008, 2009, 2007, go straight up. So my sweet spot is always starting at 2007 and then I go straight up. So that's what I've been trying to do for the past couple of times that I've done this. And that's what I will attempt to do with you guys today and tomorrow. So the stop point for today, hopefully, will be 2000 and we'll hopefully stop at 2012 today. You're gonna, all right, yeah, just a heads up, the first couple papers going to be like hell. Just prepare for that, and you're going to feel like you're not making any progress because for the first couple papers, I'm going to try and use it to teach stuff so that we can, yes, try from now. It's going to be good though, because at least you're going to have explanations rather than just going with whatever you feel. Like when I did it. So the thing is now, we're going to use the first couple questions, like the first 2 years, we're going to use it to try and go over the stuff them on the whiteboard. And I have the books them up as well, which by the way, these are my module books. So if you never get to see them when we do the paper two marathons, these are my module books, right? And basically, in these books, I have notes that I've went through for each module, module 1, 2, and 3. So this is module 1, module 2, module 3. And you'll see that each of these books have my own writing in it to the way I use it. Questions, if you don't feel comfortable with that topic, you can always go to this book. Where is this book, you ask? It's on the very good. It's on the link, the website link. So if you guys feel like you need to recap a topic before you go into that exam, you can always use these module books. And you see me going back to the module books and the physics study guide, because you can't just go in there not knowing the stuff. You have to actually have the background. The best part about paper ones is that you don't need to remember derivations, okay? You're not deriving anything. It's just know the formulas, know enough, and then you have these weird questions that you just have to know how to work them out. And once you get those questions, they're gonna repeat. So so I said these are on the website link. Then so one more thing before we do the prayer. So also on that website link, we'll have the marathons for upcoming sessions. So these are paid marathons. These are paid marathons. So Bio Unit 1. So I have a Bio Unit 1 marathon coming up this weekend, the 10th and the 11th. So if anybody interested about that, that's 1,500 Jamaican dollars. If you're interested, we'll have discounts as well, because I know that the money thing kind of difficult for everybody. But basically, we have tutors. These are actually teachers. For instance, bio teacher, somebody who teaches at a high school. So teachers who know the papers, they've been through it. So if you feel like you need that extra boost with some topics or with some subjects, we'll have them as well. Bio and pure maths, unit 1 and 2. So bio unit 2 already gone. So it's just bio unit 1, and you have maths and you have physics, which is what we're doing. And this is where the annotated books are. So when you go on this website link, you can scroll down and you see the annotated books. And I'll also post the recordings here. So recordings will be posted in this. You can click this, you'll be able to go right in it and see the recordings. And I still have the recordings up from the paper 2 marathon. All right, so with that said now, exit this. I hope I'm feeling okay. We're gonna do a short prayer and then we get right into it, starting with 2007. I don't know if anybody wants to do a prayer for us. Feel comfortable doing that for us today?
All right, sir. I'll do it.
Hey, I did it the last time, no? Roger this?
Yes, sir.
Uh, blessings. Thanks.
All right. So, and Father, I come for you. I come before you today to give thanks that we all can meet here happily together once again through through even paper two, and I give thanks that Mr. Jeremiah is healthy and strong to teach us once again, and I just come to ask you to bless us with enough knowledge and capability to go through some marathons for two last times before we face physics unit one, paper one again. Father, thank you. In Jesus' name I pray, amen.
Well, thanks. Appreciate it. All right, let we get into it. So as I did say, the first couple papers are gonna feel like hell. Just keep pushing. All right, so we're starting with 2007. All right, so this document is going to be in the website link, and I've been sending this around for like weeks now, literally since the exam did finish from me. So you should have this document, hopefully. This is a document where I've been basically editing it up with answers and stuff and solutions. And there's also this document that I'll be referring to as well. But I need to show you guys how to work out the questions because sometimes things change. So we're going to start. So the first question, which of the following pairs of units is the base SI units? So you want to go back to what is your base SI units quickly. So remember you have physical quantities, which can be described using a numerical magnitude and a SI unit. And then when you have a physical quantity that doesn't have a SI unit, you call it a dimensionless quantity. So when you talk about, for instance, a distance, 20 meters, it has a numeric magnitude of 20 and a SI unit of meters. And without that SI unit, you'd call it a dimensionless quantity. So just stating now, when you talk about those physical quantities, you can categorize them either as basic quantities or derived quantities. If they're basic quantities, these are like the foundational quantities that all other quantities are derived from. Those are the basic quantities. And you talk about them like length, mass, temperature. Try to remember these ones because I realize these are the ones that people tend to forget says basic quantities. Temperature is a basic quantity measured in Kelvin. Kelvin, not degrees Celsius. That's why when you do gas laws, you ever notice that when you're calculating stuff in gas law, when you have Boyle's law and Charles and such, you ever notice when you're doing gas law questions, you have to convert all of your temperature values back to Kelvin because the SI unit of temperature is Kelvin. And if you don't do that, you get it wrong. Just like how you have to convert mass back to kilograms. So remember that temperature is a base SI unit as well. And you have things like the amount of substance, time, everything come from time, and these other two like electrical current in amperes and the luminous intensity in candela, which is something for unit 2, right? And then you have the derived quantities. So going back to the question now, we can see easy thing. We should know all of them so that we shouldn't get questions like these wrong. So we don't want to leave anything to chance. So we know say temperature is one, we know say, you notice them use the current, because them figure out some people might not remember say current is a basic SI unit. And then others would be like mass, length, which other one? Time, and we said the luminous intensity, which is measured in candela. So know all of them so that you can never get it wrong. That's what I'm trying to say. But another trick to this, if you can think about, so looking at the others, if you can think about a formula for it, more than likely it's not a base SI unit. That's what I used to do. But key, remember what the base SI units are. Cool? And we're recording, right? Good. Yes, payment methods are on the site. You can either pay directly on the site or you can do direct bank transfer, but you can always communicate to me or the number on the thing afterwards, or text me directly afterwards. But those sessions are coming up. As a matter of fact, the pure math session this is 2007. The pure math session is tomorrow morning. I think it's pure math unit 2, that's 3971281. So if anything, and you guys interested in that, text me, or you just reach out to me some other way, and I'll communicate. So we did the first question. Everybody go okay with the first question? Journey of 1,000 miles begins with one step. We're good with it?
Yes, sir.
And it's 204 miles. Good. All right. So Kelvin and amperes. Remember all of the base SI units. You never get these type of questions wrong. Cool. Next one. So I'm making sure this is 2007. To be specific, this is the 2007 specimen paper. So there was a specimen paper, not sure what that means, but there was one, and we're going through it. So yeah. Then after that, we have a 2007 paper. So this now, sorry. Which of the vector triangles show the correct resultant of R equal P plus Q? So we're going into vectors. So the answer for this is actually this. I'm making sure that my thing is a bit clearer. So let me give you a brief talk about vectors. First thing, what is a vector? A vector is a physical quantity that has both magnitude and direction. So it has both magnitude and direction, and you can start thinking about things like force, displacement, the impulse, for example. Anything we know have some direction associated to it where you have to assume one side as positive and the other side as negative, that's a vector quantity. And in this case, so we have two vectors, P and Q. And then they ask you for the and then they ask you for the resultant R. So my trick to this question, look at the direction that the vectors are going in, because vectors have direction associated to them. So you notice that P is going in this direction. Sorry, P is going in this direction and Q is going in this direction. So they're flowing into each other. So the resultant has to be going in that direction as well to connect both of them. Because what that resultant is representing is the shortest possible distance from where they started to where they finish. Am I making sense?
Yes, sir.
Think the thing breaking up. Come. You guys can hear me?
Yes, sir, we can hear you.
It's
Yes, sir.
breaking up a little. Hopefully, I might have to reload, but hopefully it's not a problem too much. So it's the shortest possible distance from the starting point to the finish point. And yet all you have to do is look at the direction of the vectors. So you realize this vector is going in this direction, and then this one is going in this direction. So overall, they're going in this direction. And they use connecting the 2 points is that the shortest possible distance is that. So this perfectly is the answer. I think I'm going to reload because I don't want it to be a problem. I'm going to rejoin. Try that quick. Why is my internet unstable? Hey, can you hear me?
Yes, sir.
Yes, sir.
Yeah, sorry about that. My internet kind of shaky, especially during the earlier part of the day. But we'll move. So we see that the resultant would therefore be the shortest possible distance traveled from start to finish. And we can look at the vectors traveling from here, meeting up, and then going up here. So shortest possible would be there. There's this thing about a parallelogram method, but I don't really fancy it. Just look for start to finish and look at the directions, and you always get these questions okay. Right. This was me recapping vectors because specifically displacement. When you talk about displacement versus distance, we know that displacement is a vector quantity and distance is a scalar quantity. Guys, if you have any questions as we go along, please ask, because my difficulty now is trying to summarize things without going too deep. So if you have a question on something, ask it. We'll have the time. So distance, we say, is when you have a scalar quantity. Distance is a scalar quantity, which means it don't have a direction associated to it. So if I had somebody traveling now, and they're traveling from point A to point B, so point A to point B, and then walk from point A, and then go all the way to point B, and then go back to point A, who can tell me what their total distance would be? So assume this is 20 meters.
Point A to point B and back to point A.
Yeah, so all right, assuming this is 20 forward and 20 back.
40
Yes.
meters.
And I love that. Yeah, that is units. 40 meters in total, because distance, since it's a scalar quantity, it doesn't care about if you're going forward or backward. You just add up how much you travel. The magnitudes add up. But if you're asking about the displacement now going from A to B and then back to A, what would that be?
0 meters.
Because whenever you talk about a vector quantity, you always think about a net. When you look at a vector quantity, it's the sum of the vectors going in the forward direction or in the positive direction, plus the sum of the vectors going in the opposite direction. So I mean by that, if we consider vectors as when you're moving in a particular direction from a starting point, right? That's what a vector is, moving in a direction from a starting point. If you consider going this direction as positive, then this direction becomes negative. And this logic goes for any vector, whether it's force, displacement, anything. So what you're doing is simply adding up the vectors, but you have to consider the direction that they're going in. So if this is positive 20 meters traveled forward plus negative 20 meters traveled backward, you go overall of a vector, which is a resultant, which is a net sum of the vector being 0 meters. So you need to sync the basics so that when the complicateds come, you can tackle them. So look at this one now. This one did get problem last year. Basically, we have a personal so item 3 refers to the figure below showing how the displacement of a particle varies with time. I'm going to use this moment to go on the whiteboard and show you guys quickly what a displacement time versus velocity time graph look like quickly. So displacement versus time. Displacement in meters, time in seconds. So the first thing, I want to draw a straight line. When you have this straight line suggesting a direct proportionality between, so this is a displacement time graph, displacement versus time graph. When you have that straight line showing a direct proportionality between the y-axis and the x-axis for a displacement time graph, I'm going to ask, what does it represent?
Constant velocity.
And I told you some things more specific than that. Constant positive velocity. See that? You see that?
Yes, sir.
Because first of all, well done, because you see that it's displacement versus time. If you took the gradient of this graph, you're going to end up with a velocity. And since it's a straight line, that's a constant gradient. So therefore, you have a constant velocity. for this body traveling from zero displacement to whatever displacement this is. But we have to remember that it's a positive velocity, meaning that it's a constant positive velocity. That's the same as saying the person is moving at a set amount of displacement over time in the forward direction. When you have a positive velocity, it means you're going forward. When you have a negative velocity, it means you're going backwards. Because what is velocity? Displacement over time. If the displacement is positive, it means you're going forward. Hence, you're going to have a positive displacement over time and therefore a positive constant velocity. If the displacement is negative, like for instance, in a scenario like this, if the line are going like this, that would mean say have a constant negative velocity because the displacement is decreasing over time. Or in other words, you have a negative displacement over time, a negative change in displacement over time. So you have the person is going backwards. Am I making sense?
Yes.
Yes, sir.
So just trying to recap those stuff, make sure we have them solid. So I already tell you what this is. This would be a constant negative velocity. First going backward at a constant amount of velocity per unit, amount of distance per unit time, because that's velocity. So what would this straight line going horizontal represent?
The acceleration.
Constant speed.
This is the
Okay,
thing, no,
that's
guys. All right, come.
There's no displacement.
Explain your answer.
Hold on. There, displacement remains constant since it's not going up or down.
Exactly.
Right?
So the thing is, I want you guys not to feel uncomfortable with graph type questions anymore, because it's really just looking at what the x-axis is doing versus the y-axis. Let's imagine this
Yes, sir.
motion. Repeat.
I think this would also mean that its velocity is zero, right? Because it's no longer moving.
Exactly. All right, so let's reason it from the beginning. This is like, let's putting it in a realistic scenario. This would be when the body was at zero displacement. So the car, say you have a BMW and it park up in the parking lot, zero displacement, it now move. And then you decide to step on the gas and get it moving at a constant amount of distance per unit time, moving at a constant velocity, coming out of the parking lot, going forward. So that would be you getting it out of the parking lot at a constant velocity. Usually when you have a constant velocity, that's like when you're on a highway or something where your velocity is just constant because you don't have any net force acting on you to accelerate you. That part makes sense to you? Because going into Newton's second law, let me not say that. I just want you to appreciate that constant velocity means a set distance over time. Newton's second law elaborate further on that. However, set distance over time. But then you realize, just looking at the graph without complicating anything, you can see that when you reach up here, what is happening is that looking at your graph, there is no change in the y-axis. What is the y-axis? Distance, displacement rather. There is no change in its displacement. So this would be like you drive out and then you stop somewhere. And you wait at a place there. Let's say you stop at the 50-meter landmark and you wait there for a period of time. Maybe you wait there for 20 seconds. And then you decide to wheel around and go backwards to where they come from. So that's how you see this. We good? We good?
Yes, sir.
All right. So the thing I was bringing up about Newton's second law, we're going to talk about that a little later because I want you guys to see connections. That whole idea about a constant velocity, it's all coming from the ideas of Newton's law. Because I'm talking about the first law in particular, I hope you appreciate that more, but we'll get to that another time. So we know this, when you see the arc curve like this, going back to maths, we have to remember that when you have a graph and you see the gradient straight like this, it means you have a constant gradient. So proportional constant gradient happening here. But if you have a graph like this and you see curve, it means that the gradient is changing. It's not constant. So whatever that is, whatever that gradient is, Once you see a curve on the graph, it means that gradient though constant. So this is a displacement time graph. It's telling you have a constant displacement over time, constant velocity. But with this curve, it's telling you that you have a gradient that is not constant. You have a change in velocity. And when you have a change in velocity over time, what does that represent?
Acceleration.
So you can appreciate mathematically and physically that this is an acceleration, because you can see that math still says a change in gradient. What is the gradient? Velocity. And since that velocity is changing over time, changing velocity over time is acceleration. When you accelerate, you're increasing your velocity every second. So you're moving faster every second. All good?
Yes, sir.
Just want to make sure that we're remembering the basics then. And then with this now, once you see it going downward, you still have a change in velocity, but it's a change in velocity that is decreasing. So this would be a deceleration. So the smile is acceleration, the frown is a deceleration. Other thing to add, when you look at a graph, generally when you look at a graph, if you want to know the gradient of the graph are going to be the y-axis values divided by the x-axis values. So the SI unit for the gradient of that graph going to be the y-axis values over the x-axis values. Let me give you an example. Why am I bringing this up? Give you an example. Because I want you to understand gradient versus area under the graph. It's the same thing for any type of graph that you do. When you're looking for the gradient of a graph, it's always the y-axis values divided by the x-axis values, because you realize that gradient is y2 minus y1 over x2 minus x1. So them divide. But when you have the area under a graph, you realize it's the y-axis values multiplied by the x-axis values. So I'm going to give you a good example of that. When you look at a force versus time graph, the area under the force versus time graph represents what?
Impulse.
Exactly, which is force times time, Ft equal to change in momentum, that is impulse. So I want you to appreciate area under the graph is just multiplying the axes. Gradient of a graph is dividing the axes, no matter what graph it is. Good. Another example, a force versus distance graph, for instance, with Hooke's law, when you see the force versus extension graph, the area under the graph represents the work done to extend that spring, because force times distance give you work done. We're making sense?
Yeah.
Moving.
Yes, sir.
Cool, sir. Good. Remember, guys, ask questions. It's now or never. So, the velocity time graph. When you see a line like this, what's happening? You realize this is representing a constant gradient. And what is this graph? Velocity over time. Velocity divided by time is acceleration. So this is a constant positive acceleration. And then when you go like this now, what happened here, so?
Velocity stays constant.
Constant velocity. So that's similar to when you did to the displacement time graph, it did go a straight line like this. That was the constant velocity for a displacement time graph. This is represented with this on a velocity time graph. Right? And then you see when it go down like this now, decreasing velocity over time, that would be a constant negative acceleration, aka a deceleration, right? And then when you see the curve, when you have a curve on a graph, no matter what type of graph it is, that means that the gradient is changing. The gradient is not constant, it's non-uniform, it's changing. So the gradient of this graph is acceleration. So this is a non-uniform acceleration, specifically positive acceleration. It's increasing. So acceleration is the same as positive acceleration. Why am I say that? Because negative acceleration would be deceleration. So I just want to be clear on the semantics. So this would be a non-uniform deceleration over here. So this is non-uniform acceleration, non-uniform deceleration. And then the last thing for this, the area under velocity versus time graph would represent what? Let me ask. Using the same logic that I told you just now.
Displacement.
Displacement or distance?
Distance. I realize I prefer to say distance, not displacement for some reason, but distance. We're going with distance. Better distance than not. So a distance real. Okay, you can see since area under the graph is multiplying the axes, you realize multiplying velocity and time, you end up with a distance. So that's that. Use the basics and you get all of the questions in. So somebody asked me about impulse graph. So I was using the impulse graph as an example to prove my point that whenever you have a graph, the gradient of the graph is going to be the y-axis values divided by the x-axis values. But the area under the graph, no matter what type of graph it is, it's always going to be the y-axis values multiplied by the x-axis values. So gradient is y-axis divided by x-axis, and that makes sense, okay? You know the formula for gradient is y over x. But the area under the graph is y-axis values times the x-axis values. Them little things just save life. And the example that I gave you was with impulse. Because what happens is that Newton did realize some things, I'm gonna show you later. Basically Newton's second law. When you have an impulse, it's basically looking at the force acting on a body in a particular time, that reaction force in a particular time. And it has a change in the momentum during that force acting on it in a particular time. Like for instance, when a man hit a cricket ball, when he hit the cricket ball, the force he's exerting on the ball in that small period of time is going to create a change in momentum, a change in its velocity over time. And remember, momentum is mass times velocity. So when you hit the ball with that force in that period of time, that 1 second or whatever, you're gonna have a change in momentum. That is what impulse is. Impulsive, you're reactive with the force to the time, right? And the impulse is equal to force. The reason why we got this formula is because I guess I could show you that quickly before I go back to the thing. Everybody good with what I show you so far?
Yes, sir.
Sure?
Sir.
Everybody good? Ask questions, you know, because we're going to see these same logics. So I'm going to show you a bit of Newton's law. Well, I'll just show the Newton's law them now. I remember doing the contents in the first couple questions so that later on we don't have to do them as much. So pay attention. The thing now, Newton did realize, say, this is what I like about the progression of module 1. Module 1 shows you a gradual development of how we viewed motion. We started module 1 looking at equations of motion, just simply looking at how those 4 formulas could be used to calculate motion. V equal U plus AT, S equal UT plus half AT squared, average velocity times time, the other one. And then, after we did look at those equations of motion, Newton came and it said, all right, I'm going to include force to the equation. So we already did understand you did have equations of motion, looking at uniform motion. But how can we consider the force acting on these bodies in their uniform motion? That is what Newton achieved with his 3 laws. So the first law, he realized, all right, when a body is moving, I hope it makes sense. When a body is moving, he realized that in 2 scenarios, that's what he was looking at, 2 scenarios. He was saying that when a body is at rest, and when a body is at a constant velocity, that body will remain in that state until you have a net force acting on it. And when I say a net force is an unbalanced force acting on a body. Meaning, if you have a force of 5 newtons one direction and 6 in the other, the net force is the 1 newtons where are going in the positive direction, the direction where cancel out. It's that net force that causes you to move. So let me try represent this with a diagram. We have box here. I'm going to put box at a initial velocity of 0. And what I'm going to do is show you what I mean by having a net force acting on our body. So let's play with Newton's thing. Newton said, Newton said you have a net force act on the body. And you know what gonna happen when the net force act on it? It's going to experience an acceleration. Because what we know, force, net force in particular, provides an acceleration due to Newton's second law. See that falling perfectly? But follow it. So when you apply the force on the body, that is going to produce an acceleration due to Newton's second law. What acceleration mean? The body is going to have an increase in its velocity over time, or a decrease in its velocity over time. So representing that, velocity start at 0. And then you can see the velocity increase to a final velocity of whatever it is. So you have that change in velocity over a period of time. That's the idea of net force acting on a body so that its velocity changes over a period of time due to the acceleration provided at it. Am I making sense? This is where people usually get confused. But we're bright still, so we're good?
Yes, sir.
Yes, sir.
Guys, foundation is key. Ask me question. All right, so why am I going through all of this? Because if we appreciate it, all right, we'll not add that net force on the body, it will accelerate because of Newton's second law. So when you push something, it will move, basically, because it's the same logic. When something was at a velocity at 0, it had 0 displacement over time. When you apply that net force to it and you increase its velocity, what you're doing is allowing it to move, because with an increase in velocity, you're going to have an increase in displacement over time. So basically, layman's term, you add the force, it moves. It have an increase in velocity over time. It travel a particular displacement. All of these things make sense. So that is what happens when you apply a net force to a body. So what would happen in the absence of a net force? That's what Newton's first law is about. What happens when you don't have net force? You see, without that net force, 2 scenarios will take place. So follow me. If you don't have a net force acting on a body, 2 scenarios could be taking place. It's either the body going to be in a state where it's at rest, because initially what did happen? The body was at rest and there was no net force on it to make it move. It was when the net force come on it that it actually moved. So without the net force, it's going to remain at rest. That makes sense?
Yes, sir.
To have a net force, you don't move. Cool. Right? Or let's say I didn't apply that net force, and let's look very practical on this. Let's say in the car, looking at Newton's law. First scenario was when you're at rest. So your net force would be you stepping on the car gas so that the car can move. That is your net force. Without that, it's either 2 scenarios you're going to be in. You're going to be either at the point when you're at rest because you don't put no net force on it, or you can be in the second scenario where when you put that net force on the body, you're going to start accelerate because net force provides an acceleration, and you're going to have an increase in velocity. So how that's represented, what's that? Oh, let me mute. So how that's represented, imagine somebody parked in them parking lot, them step on the gas, so them apply that net force so that at rest we start move. We have an acceleration, so we start have a change in velocity. That would be like you driving out of the parking lot. So you're moving faster to come out of the parking lot. And then eventually you kind of ease up off of the gas so that you can remove that net force so that you have a set force acting on the body. You don't have a net force anymore. No net force. And you see what you've done is allowed your velocity to increase to a certain amount. But without that acceleration, the velocity will remain constant. And that is the second scenario that Newton spoke about. You can use a net force to provide an acceleration so that you can increase or decrease your velocity. But once you remove that net force, therefore remove the acceleration, you're no longer going to change the velocity, you're going to have a constant velocity. So I know I sound like I'm preaching this, but it's very important that you appreciate this. That makes sense? This is Newton's first law and second law, basically. First law states when a body is at rest or when a body is at a constant velocity, it will remain in that state until a net force is applied on it so that it can change its velocity. Because net force provides acceleration. Am I making sense, guys? Give me feedback. These are the,
Yes, sir.
Yes, sir.
that's 1 yes, sir. 2 yes, sir. 3 Mississippi. We're good? So that's Newton's
Yes, sir.
first law and second law understood. Right. Make sure. If you have a question, ask it. So what am I gonna do with Newton's second law now? Wait, before I go, Newton's first law is called the law of inertia. Why them call it that? Because what they realize is that when a body is moving, let's say at that constant velocity, it has a reluctance to stop moving, to change from that constant velocity back to zero. Because in order to get back to zero, you have to apply a net force that can decelerate it. You have to step on the brake. So you have a reluctance to stop moving because you need to apply force to stop it from moving. You have to decelerate it. You need to apply a net force to stop it from moving. So it has a reluctance to move, and vice versa. Let's say I have a body at rest. In order to move it, you need to apply that net force to get it to move. So it will have a reluctance to move because you need to apply a net force to move it. So there's a reluctance to get at rest and there's a reluctance to move. And that's the law of inertia. Newton's first law. So Newton's second law is where all of this logic comes because him said that net force acting on a body is equal to mass times acceleration. And we can represent this also as since mass and then acceleration is changing velocity over time, we can also say mass times velocity minus mass times velocity over time. And then beautiful, we can say, all right, looking at this formula, you have force equal this change in momentum, because momentum, this quantity talks about looking at mass in motion. That's what momentum is, looking at mass in motion, because mass have a velocity associated to it when it moves. Mass in motion, that's momentum. You can look at the mass when it's moving at its final velocity or at its initial velocity. And then you look at a difference in that momentum, aka change in momentum. Sometimes see it as delta P. So when you bring over the T here, you end up with this quantity called impulse. And this formula here, this is one of the MCQs you're going to see. So when we see it, we shouldn't have a problem with it. And then the third law, who can tell me what the third law state?
For every action, there's an equal and opposite reaction.
So that's what we'd tell them at the CSEC level. Tell me what you're going to tell me at the CAPE level. After yesterday.
When body A exerts a force on body B, body B will exert an equal and opposite force on body A.
Exactly. So you see, after you give them that, then you tell them the other one. Right. So when a body A exerts a force on body B is going to counter it by exerting an equal force but in an opposite direction. So equal but opposite force on body A. So that's how you have normal force. When you exert force on table exert force back on you. Normal force, perpendicular to the surface. Newton's 3 laws. Basically, he added the idea of force to motion with these formulas. And then you can take it to looking at energy, because energy will be force times distance, work done. And then you can look at power, which is work done divided by time. And everything get connected. All right, so let's go back to the thing. We're good? Have any questions? All right, so we'll move. So this is a displacement time graph. The problem with this, so refers to the figure below showing how displacement of a particle varies with time. Which of the following graphs represent the dependence of velocity with time for this motion? All right. Firstly, let's interpret this motion. This would be so let's looking at the motion. This is a displacement time graph firstly. So let me make sure I'm being careful with this. I wonder if we will have to interpret the motion though. So this, whenever you see a graph like this, you know, say some bar throwing up or down business. The challenge is figuring out how it started. Okay, realize it started at 0 here. If we're looking at the ball starting at 0, that would be when it's at hand level. So anytime I see a graph zigzag like this, is some bouncing business where you throw the ball up and down. We're at 0, so we just start at 0. Them show you have displacement increasing in the negative direction. I guess them consider going up as negative. So let's work like that. And then you reach a displacement of, let's call it 10. And then when you reach up here, for a period of time, you're supposed to hold your position and then come back down. So that's what's supposed to be represented in this region here. The changing of directions, so that now you're going back down, you're going in the positive direction. And as you go back down in the positive direction, you realize you start at the breaking up.
Yes, sir.
Yes, sir.
Wait, stop. Internet, I'm not sure. All right, so I'm gonna rejoin. Oh, they're recording. Okay. All right, come in. So I was drawing the diagram saying that this person, we can hear me?
Yes, sir.
Mhm. So this person would have thrown the ball upward. So that's why you can see, let me be careful though. Maybe interpreting this movement wrong, you know. But honestly, that wasn't the issue with this question. So I've read it before. Is the interpretation of this question is not as important. The problem is looking at this now. What they wanted you to do was identify which one of these graphs would best represent this up here. So let me show you. First of all, these are velocity time graphs. And the information they gave us was for a displacement time graph. So they want us to translate displacement time graph into a velocity time graph. So let's use our brain now. First of all, when you have a straight line on a displacement time graph, it represents a constant velocity. But notice it's going downward. So that would be a constant negative velocity. So you're going to look down and you're going to identify. This wouldn't be right. Anytime you see a graph that has this kind of situation, which type of motion should you be thinking?
Simple harmonic.
Very good. This is a sine wave for simple harmonic motion, right? At the amplitude, at the equilibrium, you know exactly how that goes. I will get to that. We just said that when you have this go down like this would be a constant negative velocity. So you look at the next one, you realize this is at the positive side. So this is constant velocity, yes, but it's on the positive side. So, and then you reach to these two. So here's the problem with this question now. Thank God it's not a repeat question. They have two answers that could be right. This one, same negative, constant velocity, and then this one. So what I did for this one, I had checked over most of the solution sheet that existed. And also my idea for this is that looking at the data, this velocity that we calculate here, so if we're calculating this velocity, we'd have to find the gradient. Looking at the expansion of it, this would look like a small gradient. That's why I went by it. So if I went and said, all right, this is y1, this is x1, and then this is y2, and this is x2, and work it out. I just said, all right, this probably is a small gradient, therefore a small velocity. So comparing these two, C and D, D has a smaller velocity than C. C have this big old constant velocity that's going on right here. But you realize that's the only difference between C and D. As I said, this is not a repeat question, but I would be comfortable going with D for this. And you realize there are several questions where you just have to decide where you're going to go with based on the information that you found. So guys, feel willing to converse with me about questions because at the end of the day, you are going to go into the exam. So converse to try and get the best out of it and figure out. But this is what I had went with when I went through this. So we're good?
Yes, sir.
Yes, sir.
But you realize the only difference between these two would be that they have a larger velocity here, a larger constant negative velocity. And then in this region, it's like you have a change in direction and then it's still a negative velocity. Let's interpret something for understanding's sake. You see, in this case, what this person would have done, this is probably like a driving scenario. Like the person probably did drive, I don't even want to interpret it, but this part in particular, what this person probably do, let's say them there at a particular distance, and then them turn backwards to go back to their original starting point. So them did they out there so, and then them start go backwards at a constant velocity. And you see when them reach them starting point where them did start drive from, when them reach them yard, you know what them start do? Them drive past the yard and start go beyond that. That's why you end up with a constant negative velocity on the opposite side. Suggesting that them reach from the opposite, them go past the starting point. Am I making sense? So that would be like the person go to the zero, then I go backwards, reach at the zero, and then them go over to the other side. That's how you get a graph like this. Right? You sure?
Yes, sir.
All right, so take the understanding and apply it with other questions. Move. All right, projectile motions. I'm going to recap projectile motions quickly on a whiteboard. And we'll not do it again. Ready? All right, so who can tell me how we approach projectile motion? What are the 3 cases? Who remember? Were there from the first sessions?
Yes, sir. I remember one.
So first, tell me
Well-
what is projectile motion? Fall into my trap. That's the first thing. What is projectile motion? So if you're defining projectile motion,
Projectile motion is a motion of an object in a trajectory with the shape of a parabola.
you get half a mark for that. Because not the shape of the object is parabolic, it's the equations of the motion itself that's going to be parabolic. But I guess technically are the same thing, but maths people don't like you saying it like that. You'd get half a mark. So it's 3 marks would I give for this question. Paper 2 got some stress upon definitions, but I'm gonna make you remember it. When you have a projectile motion, this is basically motion where the a body is projected, so you can use that same word, or thrown, or just say projected. Projectile motion is motion where a body is projected with the only acceleration acting on it being acceleration due to gravity. And its motion is described as parabolic mathematically. When you do the equations for projectile motion and you work it out mathematically, you actually get the equation of a parabola, which is something like ax squared minus bx. Do have to remember that. So projectile motion, you project the something and it's going to be projected with only one acceleration acting on it, acceleration due to gravity, which means the only force acting on it would be weight force. There's no drag force, no nothing else act on it. It's just weight force. It's only acted upon by acceleration due to gravity. And its motion is described as parabolic. That is projectile motion. And then we have 3 cases. Tell me the case them now, Roger.
Okay, sir. I don't remember them in order, but I remember you have a case where an object is kicked from the ground, from a ground level, and then follows a trajectory down to a distance. And then you have another case where the object is thrown at a height.
Okay.
I remember that. I forgot the others.
All right. Anybody else want to try? Come on, make a recap.
There is a scenario, I guess, like an object is at an elevated height. And
Repeat that, please.
a scenario with elevated heights.
Also, a body being projected from a height. Good.
And there's another one about project at an angle.
Yes, close enough. We're going to get there.
The third one.
Very good. I like remembering stuff in order because it forces you to remember things. Then again, that's kind of like swatting, where if you forget one part, you forget everything. But things have a pattern. If you follow a pattern, it's easier to remember stuff. But all right, may I tell you them again? I'll go through them. So it's 3 cases. When we say case, basically there are 3 scenarios that a body projected. You have to know how to calculate everything for. Them 3 scenarios there. And the question would just say that's actually case 4. Because there's this hybrid case where you fuse case 2 with case 3. And I call it case 4. But we'll start with the basics. First 3 cases. Right. In case 1, this is when our body is projected vertically upward. So when you just throw something up and it come back down in your hand, that is a case 1 scenario. And in case 2 is when you project something from a height. You just make it fall off from a height. And in case 3 would be when you project something from a horizontal level So what I'm showing you is a vector for each of them. The vector velocity where you project it off with, where you throw it off with. Projected vertically upwards, projected horizontally, and it fall like this. And then you project it from a horizontal level so that it go up at an angle and it will return at the same horizontal level. That's case 3. And then I tell you about something called case 4. Case 4 is like a fusion of case 2 and case 3, where something is projected from a height at an angle, which is typically what would happen if you throw your phone off from like high area for some reason. So from a height at an angle, case 4. So I'm going to go through the formulas for each. So case 1, first formula, if you want to find the total time in case 1, we said total time is 2v over g. We derive this by using the big equation we'll derive everything from. Equations of motions first, because remember, projectile motion is acted upon by only acceleration due to gravity, which means it's a uniform motion. If it's uniform, constant acceleration, that means the equations of motion apply. Therefore, technically, all of these formulas are derived from the equations of motion. But once you remember them, you don't have to think, oh, I need to transpose this or work around the formulas then. You know a specific formula to work out everything in each case, if you remember it. So this formula for total time was derived from the equation S equal ut plus half at squared, which we know is one of the equations of motion. Deriving equation of motion this. Anytime I need to derive something, or that equation. And then the time to reach max height, what we said was that in case 1, when you project the body like this, it will go up and it come back down. And assuming that this is a symmetrical motion, the time it takes to go up going to be the same as the time it takes to go down. So the total time is the same as 2 times the time to reach max height. So if you want to find the time to reach max height, it's just half the total time. So the formula for time to reach max height is half the total time, so it would be V over G. You following me? You following me?
Yes, sir.
Right? All right. Sure?
Yes, sir.
So 2V over G, I'm going to show you how to derive these, but we don't need to know the derivation to paper 1. But know where it comes from. That can help if you remember the formula.
Yeah, you could
What's up?
could you go through that again?
All right. So let me show you it in another book instead. Let me just show you. It's not a lot of them, but pattern recognition with it. Oh, something important. When you have the paper ones, remember the first 15 questions going to be module 1 questions. So once you reach 16, you know, so you reach the module 2. And then when you reach something 30, you know you reach module 3. So that's a good way to pace yourself. Hold on. All right, see here. So so let me repeat. First thing is 3 formulas for case 1. 3 formulas you need to know. You just want to know how to calculate the total time of flight, going from all the way, coming from projected up to come back down. Then you want to find the time for reach max height, half the total time. And then you want to find the max height itself, how you reach up there. So, and the idea is by understanding how the case look. So remember, you projected off at a velocity, and as it got the velocity, that projected velocity, I want you to also remember vectors. I want you to remember vectors because vectors is crucial. When you have a vector like this, where something is projected vertically upward like that, first thing you do, or overall, when you have a vector, the first thing you do, you break it down in its components. I would say that components are just like parts of the vectors found in the vertical and horizontal plane. There's just two parts of it in two different planes. And we said that when the vector is vertically upward like this, just like that, we said that the vector ends up being equivalent to the vertical component of that vector. Because when you think about it logically, when you have the vector just straight up in the vertical plane, it ends up being equal to the vertical component. And therefore, none of it is in the horizontal plane. So the horizontal plane is 0. Am I making sense? Recapping vectors as we go along.
Yes, sir.
So I have to remember that. So flatten out the vertical plane, not in the horizontal plane. Vectors. So looking at this case one scenario, it's just like this. And when I did do the paper 2 marathons, I did show you all the different scenarios with vectors. But just like this, you can see going directly upward, that means that the vector is going to be equal to the vertical component of that vector. And in the horizontal plane, that horizontal component going to be equal to 0. It just a go up. It not nothing to do in the horizontal. That's what we are trying to say. So what we said is that going up and going down, this is a symmetrical motion. So the time it takes to go up is the same as the time it takes to go down. And the distance to go up going to be the same as the distance to go down. Important. So now, how we get this formula about 2v over g? You don't even remember that. It's just that S is equal to ut plus half at squared. What do we tailor this formula to the situation? We want to find what happened when you do the entire duration. You want to find the total time. So then tailor this formula with that in mind. If you're looking at the displacement when you do the entire movement, what would that displacement be? Quickly.
0.
Because you travel up and then you travel back down to the starting point. So the displacement is 0. So then put the 0 there. And then the initial velocity, that initial velocity in the vertical plane specifically is equal to v. That's why then swap it out with v. So it's like you split up that vertical, it's like you split up the vector v in its vertical component and the horizontal component. At this point, these are initial velocities because you just start the vector, the vector there. You can split it in the vertical plane and the horizontal plane. So that initial velocity, v, is equal to the vertical component. All of that so that you can appreciate why then put uy also. V is the initial velocity, that may I try to say. But then put ui because v is equal to uy. Don't need to understand that. But after that, them use must say wait name again, simultaneous equation or something like that. No, quadratics, so that they could find out what t is equal to. And then they found that t was equal to 2v over g. So that's the total time. But if you're finding the time to reach max height, it would be half the total time, so you end up with v over g. For understanding? Yes? No?
Yes, sir.
Cool. We're so on board. All right. This one, which says v squared over 2g, right? And we get this from saying we want to find the max height. So we need for tailor a formula to suit just coming from right here, go up. And since we are trying to find a distance related to a velocity, remember when I showed you all of the equations of motion, I gave you specific uses. So the v squared equal u squared plus 2as, that formula is best when you want to find the relationship between a velocity and a displacement, distance. Tell me if you're following me. So that formula is best when you want to find a relationship between velocity and displacement. The v squared equal u squared plus 2as. So that's why them use the formula, you know, to make a formula for the max height. So them say, all right, that final velocity up here would be 0. Because when you reach max height, the velocity is 0. Because as you go up, acceleration due to gravity is negative going upwards. So you have a decrease in velocity over time as you go up. say you reach a velocity of 0 when you reach max height. So that is 0. The initial velocity is the v. Then the acceleration with the g is going to be negative g because you're going upward. And then the displacement is the max height that you're trying to find. And then them transpose this so that them end up with v squared over 2g. Right. Those are the three formulas for case 1. Then case 2, we said that load it. Boy. I have to read them. All right, cool. Oh, stop. So, because so I just try to go over the content now so that later on we don't have to repeat it too much. Once you remember the stuff, then you're good. When restart. Internet not able to do. Well, can you hear me?
Yes, sir.
Sorry about the internet stuff. Might take a while, but we must finish. We must finish. All right, so we'll go through again. I try not to go too much into the details, but I want to at least catch it for the first time so that when I go forward, we don't have to say it a lot.
Excuse
So-
me, sir.
Yeah.
Could you go back to the formula for case 1, please?
Okay, so remember now, case 1, 3 formulas. We want to find the time to reach the total time first, which we say is 2v over g. Time to reach max height, half the total time, which is v over g. And then you have the max height itself, which is v squared over 2g. I still have the recordings up from the paper 2 marathon, so if you feel like you want like an extra explanation on something and maybe there, you can watch those. But all they going through the formula stuff. The only other thing I could add is that let's say you want to find the total distance, you'd say max height and you times it by 2 because the distance to go up is the same as distance to go down. So them things there. And you realize the physics like to push your understanding. That's why I'm not trying to force enough to understand. Trust me. So this case 2, so I'm gonna show you case 2 quick on here. Not going to no whiteboard. Follow me, guys. Case 2 is the one I'm love to test the most. This is when you project something from a height. So you just store it off at a height. And it all comes back to our understanding of vectors. So I will ask, when I look at this vector that's flat on the horizontal, what would you say is occurring for the Vx and Vy of this vector, the horizontal and vertical component? What would my Vx be equal to? Come.
0.
Or what? No, come. Reason it out with me.
Could you
Got it.
repeat the question, please?
All right, so what would they, so first thing, whenever you look at a vector, the first step is to break it down in its components. So no matter how it looks, you just go and draw broken lines to say horizontal component and vertical component. That's the first thing. And then you say, all right, looking at V, you see that V is flat in the horizontal plane. So it's overlying Vx. So you can see that, what would that mean then? What would my Vx, my horizontal component be equal to? What would my Vx be equal to?
You will result of velocity. E?
It would be equal to V. Okay, you can see that the vector velocity here, that velocity that you throw it off with, that vector velocity is going to be directly on the horizontal. Therefore, it's equal to Vx. Just like how when it did directly upon the vertical, it did equal to Vy. When it directly upon the horizontal, it equal to Vx. So these are just scenarios that you have to commit to memory and understand when you talk about vectors. What happens when them directly on the horizontal? What happens when them directly on the vertical? All right. And when I did do the paper 2, I did go through some more, but these are the ones that you need for the paper ones. And then so if this is Vx, what would be my Vy for this?
0.
Exactly. Reasoning. Because overall, what you want to remember as well is that using Pythagoras theorem, when you have two perpendicular components like that and you want to find the resultant, Pythag tell you that the resultant is equal to the square root of the two perpendicular thingies. So if in this scenario we say that Vx is equal to V, that means that Vy must be equal to 0 so that you can end up having V adding up. If Vx is equal to V, that means that Vy have to be equal to 0 so that this can add up back to give V. Because this already equal V, so this needs to be equal to 0 so that you can get V. So logics it up. So them understanding the carry forward. Ask questions if you need, please. So we're gonna look at the ball at 2 scenarios. When it reach here, so when it reach here, so. When it reach here, so this is the vector velocity. and I'm going to break in it component. So in the horizontal component Vx and vertical component Vy. Now in the horizontal component, my acceleration, what do you think is happening to my acceleration in the horizontal? Remembering that projectile motion only has one acceleration acting on it, acceleration due to gravity. What would be my acceleration in the horizontal?
0.
Because you don't have any gravity in the horizontal plane. You don't get pulled to the ground horizontally. You get pulled to the ground vertically. There is no weight force and no acceleration due to gravity in the horizontal plane. So acceleration in the horizontal is 0. Therefore, if there is no acceleration, that means you have no change in velocity over time, which means that your Vx is going to remain constant throughout. That makes sense? Yeah? No?
Yes, sir.
Remember, guys, ask questions. And then in the vertical plane, the acceleration due to gravity going to be g in this scenario because the body is falling. And then if you have an acceleration this time, how are you going to find that velocity? I want to carry you back to your equations of motion. So somebody, well, no, let me just write them down because everything started at the equations of motion. You must remember them. V equal U plus AT. So it's 2 velocity formulas and 2 displacement formulas. That's what I remember. V equal U plus AT. Then you have V square equal U square plus 2AS or AS, whatever. And then you have S equal U plus AT square. Sorry, S equal UT plus half AT square. This is one they love to use for derivations. And then you have S equal average velocity. Says the sum of final and initial divided by 2. Average velocity times time. And you must remember your equations of motion. This formula is good when you want to find a velocity at a specific time. This formula is good when you want to find a velocity at a specific distance. That's what I was saying earlier. This formula is good when you want to find a distance at a specific time. And this formula is just whenever you don't have acceleration. We're good?
Okay, could you repeat the uses, please?
Right. So this formula is good when you want to find a velocity of a body at a specific time when it's accelerating. Because remember, acceleration causes your velocity to change. So at any given point, your velocity different. So how you find your velocity at that specific point, that specific time? V is equal to U plus AT. Because what this formula tells me, this formula was first derived from V equal U. Acceleration is equal to change in velocity over time. If I'm talking too fast, ask me to slow down as well. So this is where this came from. What they did was say, all right, transpose to find V. And this formula perfect because you want to find a velocity at a specific time. So what you do? First, you find out what the initial velocity of that body was. So let's say it start off at 0, or let's say it start off at 2, whatever that was. And you know, say, as you move in velocity change, you just want to know how much in velocity change by so that you can add it to the initial velocity. That's what this is doing. You know the acceleration, which is the amount of velocity change per second. You know how much velocity you're going to increase per second. That is what acceleration does. Gravity, 9.8 meters per second square. It tells you that you increase your velocity by 9.8 every second you fall. So acceleration telling you how much your velocity change per second, hence it's changing velocity over time. If you know how much your velocity change per second and you multiply it by the number of seconds, you're going to know the total amount of velocity change in that period of time. And you add it up to your initial velocity. Am I making sense?
Yes,
Yes,
sir.
sir.
So I want you to love your formulas basically until you finish Unit 1 physics. This formula is for finding velocity at a specific time. This formula is for finding velocity at a specific distance. This formula for finding displacement at a specific time. This formula tends to be done with quadratic formula. You can make this into a nice quadratic equation. Avoid doing that at all costs. And then this formula is when you don't have acceleration. We're good? Equations of motion. And you use equations of motion when you have a constant acceleration, like in projectile motion. So I'm gonna drink some water. I'm gonna ask again, how would I find, so we appreciate saying the horizontal for this body, acceleration is 0, velocity is constant. In my vertical, acceleration is gravity. How would I find my velocity at any given point?
When I use the V equal U plus AT formula?
Yes. But guess what I'm going to do? I'm going to tailor it to this situation. So what's the initial vertical velocity in this situation?
0.
Very good. And what's the acceleration in the vertical plane?
0.
No.
Vertical plane? Oh, yes, 9.81.
Gravity. And then you have time. So just to repeat that, we knew that in order to find the velocity in the vertical plane at any given time, so at this point right here, we have to use V equal U plus AT. But we want to make it look like, tailor it to this specific scenario. So the initial velocity in the vertical plane, we saw that it was 0. And then acceleration in the vertical plane is gravity. And then time is time. So that's why the V going to be equal to G times T in this scenario. To get comfortable with the idea of formulas being tailored to this situation. So that's how you do it in case 2. And when you reach down here, so it's the same thing are gonna happen. Where, so this is the vector. In the vertical plane, Vx is going to remain in the horizontal plane. You start at the horizontal. In the horizontal, Vx always going to be constant because there's no acceleration in the horizontal. So when you're up here, so Vx was constant. When you're down here, so Vx still have a constant. So I'm gonna ask you now, what is that Vx equal to? I don't lose you. In this case 2 scenario, what can you identify that Vx as? Start from the very beginning. So Vx constant when it's down here, but you don't know where constant to. It constant when it's up here, still don't know where constant to. What was the very first Vx? Vx was equal to V. So at any given point, that constant Vx is the projected velocity in case 2. That makes sense? And the thing about this is not something where you need to remember. If you understand it, you will remember it. May I make sense?
Can you repeat, sir, please?
All right. So first thing I gotta ask you, you understand when I tell us if Vx is constant in the horizontal, Vx horizontal component is constant.
Yes, sir.
Right. So what me ask you now is what is that constant Vx? So you start back track. You remember that when we started off, we said that V is equal to Vx and Vy was equal to 0. And all you did was just look at what happened to the V at every given point. When you reach yourself Vx, you split the V and you get Vx to still be equal to V. It remains constant. And you see that Vy going to be equal to G times T. When you reach down here, so Vx still going to be equal to V. And Vy going to be equal to G times T. That's what it is. That makes sense? Should I repeat? You wonder why me if remember all of this paper one? Because when them drop the weird questions, it them something I have to use remember but can't answer stuff. We okay? Should I repeat?
No, sir.
Remember, I need
Wait.
feedback too.
Hold on.
Ask the question.
The vertical velocity is gaining a negative increase or something like that.
Why? Why? You tell me why. So go back from the
Because of
beginning.
acceleration, pulling it downwards.
It's positive. Remember, so gravity is positive going downward. So as it go down in the vertical plane, that velocity is increasing. So let's do it again. But how I have to think about it? Think about it like you have a vector, and then you want to look at what's happening to the horizontal vector as it go down, and what happened to the vertical vector as it go down. So think about it like that. Look at what happened to the vector, what happened to the horizontal, what happened to the vertical as it go down. So in the beginning, the vector was equal to Vx, and Vy was equal to 0. I understand that. That was the beginning. When you reach here, so in the horizontal, we have to understand that there is no acceleration due to gravity, which is the only acceleration in a projectile motion. So in the horizontal, acceleration is 0. Since acceleration is 0, that means you're not a change in your velocity. So velocity is constant. We're good? We're good? We're good?
Yes, sir.
Right? And therefore, you can appreciate, say, in the horizontal, that Vx going to remain constant, a constant V. But in the vertical now, the Vy vertical, you have an acceleration. Therefore, you can calculate the change in velocity by using that V called you to say T. You tailor it down to GT. So at any given point, if you want to find Vy at that point, you just need to plug in gravity and multiply it by the time at that point. Why you need to know this? Because let's say them they tell us the impact. This is a typical question with them paper 2 type. The impact velocity. When them say the impact velocity, they're asking you for that vector velocity. And how you find it is with Python. Square root Vx squared plus Vy squared. But if you're going to do this, you need to know what Vx is equal to. Vx is equal to the constant V. It remains constant. And Vy going to be equal to G times T. Make sense? Now, if I go tackle paper ones, you said the thing about paper 1 questions, this is when them let out all of the mad stuff then, because you have to really understand the content for the paper 1. So make sure you understand. We're good?
Yes, sir.
All right. So if we're good on this, right? The formulas to remember, 2 formulas. In the vertical plane, so we say S is equal to UT plus half AT squared. And we tailor this in the vertical. So the initial velocity in the vertical is 0. And because of that, we can say, all right, solve for T, square root of 2h over G. This is the perfect formula, and you're going to see this again. This is the perfect formula to find the time it takes to fall from a height. If you want to find the time it takes to fall from a height, it's the square root of 2h over G. Remember that. Square root of 2h over G because of this derivation. Time to fall from a height, square root of 2h over G. There's a question like that where the answer is 0.61 seconds. That's just how much it get to. Yeah, eventually I'm gonna memorize answers. We'll get there. Time to fall from a height, square root of 2h over G. When you find the range, it would be the Vx times T. Right. And then you have case 3. We're good? We okay? Give me some water. I would say now case 3. This is when somebody is projected at an angle to the horizontal and they're gonna land back at the same horizontal level. Right? So it's like you kick the football and it drop back down. It's a symmetrical motion. So them says that the time to go up gonna be the same as the time to go down. Easy. That sound familiar though. Which case would it say that, where it's a symmetrical motion?
Case 1.
Exactly. So you know what I like about case 3? Case 3 is literally just like case 1. So you don't have to remember new formulas. So because it's a symmetrical motion. So yeah, so the case 3 formulas are exactly the same as case 1. The only difference is that the component is a little different. So I'll show you. So the time to reach up here is the same as time to go down, and the distance to reach up here is the same as distance to go down. Cool. Also, so now look at the vector. So this is the vectors that you used to see when they're at an angle. And you don't know when them they are the angle. First step, with any other vector, you have to split it up in its components. And then you're gonna say, all right, this is Vy, this is Vx. You see a trick with this, look at what I'm gonna do with Vy. I will draw Vy on the other side, right, parallel. So Vy up here, you can draw it over here. Why am I doing that? So that I can see the right angle triangle. You don't have to do that, but you can appreciate, so this is a right angle triangle. So Vy is here and this Vx is here. So this is the opposite. That would be the adjacent, and this would be hypotenuse. And therefore you can see the one that sandwiches the angle is going to be the cosine one, and the one that doesn't sandwich the angle is the sine one. So Vx would be V cos theta, whatever that theta is, and then Vy would be V sine theta using trigonometry. All right. So we're gonna do one more thing before we look at the formulas. Just like before, we're gonna look at the ball at 3 stages. Don't overthink this. When we look at it at the 3 stages, are the same steps. I want to know what the vector look like. I want to know what it's looking at the horizontal, and I want to know what looking at the vertical. And it's the same rules that go apply. In the horizontal, there is no acceleration. In the vertical, there is acceleration due to gravity. There's the same things I'm gonna do, but only now with a different scenario. So I'm gonna do it. This is the vector. I'm gonna split it in its components. It's supposed to look something like this. Now my sim Vx, not drawn properly, whatever. Vx, we have to remember that in the horizontal, acceleration is equal to what?
0.
Right? Therefore, the velocity is
Bx.
constant. Cool.
Oh,
Because without acceleration, you don't have change in velocity. Therefore, velocity is constant. So what was that Vx that's going to remain throughout? V cos theta. You see that? So at any given point, Vx is always going to be V cos theta. Even when you reach here, so Vx still going to be V cos theta because it remained constant. And it started off as V cos theta. Just like how previously, we did see that Vx started off as V. Well, see the pattern? We okay? Remember recapping this for you guys so that you can make sure you understand it enough. So give me your feedback, right? All right, so Vy is the same logics again. How am I gonna find out? So first of all, in the vertical plane, we said that the acceleration is equal to gravity. But there's a little difference now. And therefore velocity gonna be equal to Vu plus At. Vu plus At, right? Yeah, that's the formula. But there's a little difference. The difference is you notice the body is going up. So what do you think that I'm gonna do to its gravity?
lessen it.
All right, remember.
The gravity will be negative.
Yes, because what is gravity? Acceleration. What is acceleration? A vector quantity. So gravity is acceleration, right? It's a type of acceleration. Acceleration due to gravity. Every second, your velocity change by 9.81 meters per second. But vector, acceleration is a vector quantity. When you go down, gravity is positive. So as you fall, you can literally feel yourself moving faster because you have an increase in your velocity of 9.81 for every second until you splat. But as you go up, it's the opposite. Your velocity is decreasing by 9.81 for every second until eventually you have a velocity of 0 when you reach max height. Make sense?
Yes, sir.
Yes, sir.
Mhm. So as you go up, gravity going to be negative. That's why I want it to see. And therefore, it will affect how we put it in the formula. So we want to find V in the vertical. What is Uy in the vertical? What's the initial vertical velocity? That's what I'm asking.
0.
No, that was case 2. Tailor the scenario. What is happening in this scenario? What was the initial vertical velocity in the,
Uy, right?
yeah,
Would that be the V sine theta?
yes, but I don't want you uncertain. This. This is when it did initial, right? And this is its vector velocity, right? But when I ask it for its initial vertical velocity, may I ask it for the vertical component of its initial velocity, which is its vector velocity. That makes sense? Vy. Its initial vertical velocity would be its vertical component of its vector velocity initially. That makes sense? No?
Yes, sir.
So I just want to be sure of that. Vy is the same as initial. Well, Vy means vertical velocity, but this is the vertical velocity at the start. Therefore, this is the initial vertical velocity. So understand it, right? So that Vy would be V sine theta. And then we say we have A there going to be negative G times T. So this time Vy is equal to V sine theta minus dt. And why we need to know this? The same reason as before. Is it going to be the same thing down here? Vx going to be V cos theta. Vy going to be V sine theta minus dt. The idea is to understand it, not swat it. If you want to find vector velocity, that impact vector velocity, or vector velocity at any point, it's going to be Pythag, which means you need to know what Vy is equal to, and you need to know what Vx is equal to. So that's why I will stress those things. We good? Yeah? No?
Yes, sir.
Any question? Yeah, sure. I will jump into the question now and for good enough. All right, so the formulas them now. That was you understanding the motion. Now you need to remember the formulas. It's about 4 formulas for this, but them easy. Why? Because I'm just like case 1. So first formula is finding the total time. Total time. The way them get it is with the same method like in case 1. You use the S equal UT plus half AT squared. And then tailor it to the scenario, yada yada yada. But in this scenario, Vy, that initial vertical velocity, so UT, that initial vertical velocity would be V sine theta, unlike in case 1 when it was equal to V. So in case 3, all you have to do is swap out V for V sine theta. So in case 1, anywhere where you did have V, you just need to swap it out with V sine theta. So in case 1, the formula was 2V over G. So in case 3, it's going to be 2V sine theta over G because of the whole derivation. Am I making sense? Yeah. Sure?
Can you repeat that, sir?
So what I'm saying is that if you remember case 1 formulas, you know case 3 formulas. The way that they derive case 3 is the same way. They said S is equal to UT plus half AT squared, but they have to tailor it to the scenario. The U here in case 3 is V sine theta. This U is V sine theta. In case 1, that U, so V was equal to Vy. So in case 1, that U would have been V. But in case 3, that U is V sine theta. If you don't want to stress your head with that, all I need to remember is that if you know your case 1 formulas, just replace V with V sine theta for case 3. So case 1, the total time was 2V over G. But for case 3, the total time is 2v sine theta over g. Make sense? And then the time to reach max height, which is half the total time, it would be v sine theta over g. We're good?
Yes, sir.
Yes, sir.
All right. So since we're good, what do you think so first of all, what was the formula for max height in case 1?
V over G.
Mm-hmm. Come on again.
Was it V over G?
Something like that. This is why I'm gonna try to show you the derivations, because when you finish all of them, the formulas them look very similar. So you have to try to remember them using the derivations. That's how I'm gonna do it. So it's v squared over 2g. Because I remember that was derived from v squared equal u squared plus 2as. That was the one where you made it say, all right, I want to find velocity when you have a particular distance. So I'm going to use the equation of motion v squared equal u squared plus 2as, as being us. That make it easier to remember. And then I derive that to get v squared over 2g equal max height. So you're seeing how I remember it? We're good?
Yes, sir.
Write it down. So since it's v squared over 2g in case 1, in case 3, what we have to do is switch out v with v sine theta. So how that look? So it's v squared over 2g in case 1. So for case 3, it's going to be, I just have to put v sine theta and then square that over 2g. This is technically it, but there's a mathematical way to represent that. When you square v, you get v squared. Makes sense? When you square sine theta, you get sine square theta. That's how they like to show it. Why? Because when you say sine square theta, this is telling you that you're squaring the sine of the angle. So you're squaring the sine of the angle. So if the angle was 30 degrees, you're squaring sine 30. Sine 30 is about 0.5. So you're squaring 0.5. That is different from saying, let me now validate why you need to show it like this. That's different from you saying sine theta square. Why is that different? Because when you say sine theta square, that is you saying, let's say the angle is 30 degrees. That is you saying you square the angle first and then you sine it. And that would give you a completely different thing. Okay, if you square 30 degrees, you get something else and then you sine that, a problem. So that's why the formula look like this. Sine square theta, so that you remember that you're squaring the sine of the angle over 2g. We're good? V sine theta all square over 2g. That's the same as saying v square sine square theta. You're squaring the sine of the angle. Squaring the sine of the angle over 2g. All right. What next? And then the horizontal motion. This is the last formula, guys. You want to find a range. So who can tell me the formula for range in case 1? In case 2. I remember there was no horizontal in the case 1, so there would be no range in case 1. We okay? Man, for ask if we're okay, because I know that I don't want to feel like negative towards it or anything. Ask questions, it makes sense. What was the range formula from case 2?
S equal to
I prefer R.
T.
Yes, good. Vx times t. So, right, Vx times t. So this derivation, I don't have to show you. All right, so what I'm doing is say Vx is equal to V cos theta. You know that already. In this scenario, Vx was equal to V cos theta. And then I'm say times t. Now, total time is the same regardless if you're looking at it in the vertical plane or the horizontal. Because once you reach this, so your time this so is the same. You're not gonna have a different time in the horizontal plane versus the vertical plane. So I'm gonna say that is because the formula what them use here for total time is the formula from the vertical plane. So that's what them do. Them drop in a formula there. So them can say, all right, V times V, you get V squared. And then the rest of them come together, you get 2 sine theta cos theta over G. Maths people are gonna be like, oh, this is actually a thing. 2 sine theta cos theta is called the double angle formula, where 2 sine theta cos theta is actually the same as sine 2 theta. So let's say the angle is 30 degrees. 2 times 30 is 60, and then you sine that. If you were to say 2 sine 30 cos 30, you would get the same as saying sine 60, which is sine 230. That's a double angle formula. So the formula is V squared sine 2 theta over G for range in case 3. If you don't remember this, you can just say V cos theta times the total time if you get the total time. So you would have said V cos theta times the total time. Let's say you did work out the total time already using 2V sine theta over G. And that's the last formula. We're good? That's projectile motion, everything. So going forward, we don't have questions for projectile motion if you stay with me, right? All right, so let's look at this. One more writing, unnecessary. Give me some water. All right, so this was the case where I was telling you about when something is projected at an angle from a height. If we need to go into it, we'll go into it, but not now. So a stone is thrown from a building of X and follows a parabolic path as shown. I guess you can describe it as parabolic, just like what the person said earlier. All right. The maximum height reached by the stone is P. The vertical component of acceleration of the stone is, so I'm going to ask a question first. How would I calculate the max height? You see the thing about case 4, this case, that part here coming from here to here, this is case 3. When you project from the horizontal level and reach back at the horizontal level, that's case 3. But once you go past that, you have to consider case 2, because you realize case 3 only facilitates if you go back to the same horizontal level. But you're not doing that. You're actually falling down a height. So that's why I'm gonna call this a fusion of case 3 and case 2. The formulas though are the same for case 3. What I mean by that? If I want to find the height from here to here, and I'm gonna use the case 3 formula for max height. So how do I find max height in case 3? Come guys.
U squared sine squared theta over 2G.
No.
That's not max height.
I remember this is case 3, so hold on, wait, me probably wrong. So that again?
U squared.
V squared, that's why it tripped me up. So V squared.
Oh. I said over 2G.
Yes, that is the formula. Very good. V squared sine squared theta over 2G. But pretty thing about case 4. So that would only find this distance right here. So if they had asked you to find that total max height, you would have to add that distance where you just calculate by saying V squared sine squared theta over 2G. You'd have to add that with the height. Make sense? It makes sense? Yes. Only up here is the case 3. And then other things happen. If we need to see it, we'll show it. So the question asks about the vertical component of acceleration. So this is why I would stress myself to understand it. Them say, what is the vertical component of the acceleration of the stone? Or them said the vertical component. So is, and the answer is C. Why is it C? First of all, so try to ignore all of these writings, please. They're asking about 2 points X and P. So right here and right here. And them ask you the vertical component of the acceleration at these 2 points. So I'm going to ask you, what is the vertical component of the acceleration at those 2 points? Keep in mind,
9.81.
acceleration due to gravity. Very good. I just showed you everything that you needed to know regarding projectile motion. So you should have confidence now to say, oh, I can't get projectile motion wrong. That's the purpose of studying everything. So you know that in the vertical, acceleration is due to gravity. And that means that the velocity is going to equal to V U plus AT, right? And you can tailor that. So acceleration due to gravity is the same here, and it now going to change when it reach up here. Gravity always the same. So they were just testing if you understand the thing. So gravity is constant, and gravity is the vertical component of the acceleration. So what would be the horizontal component of the acceleration? Testing.
As in for the answers.
As in, just tell me, at any given point, what would be the horizontal component of its acceleration? Think about the question. So when we say what is the horizontal component of the acceleration, translation, may I ask you what is the acceleration in the horizontal plane? That's what I'm asking.
0.
Exactly. So you have to understand the words. May I ask you for the horizontal component? So what is the horizontal part of acceleration? What is the horizontal acceleration? The horizontal acceleration is 0. Yes. So we now go having a question sign, we go sure, because we have developed a learning field. Good. I remember how long it did take me to learn projectile motion. So don't feel like if you just see it, it'll take time, but just try to remember the formulas and you'll be good. So this question, all right, number 5. A wooden block is so let me zoom down a little. So a wooden block of mass 0.8 is being pulled along a rough horizontal surface with a 20 Newton force. You see, from you see a question like this, you should start thinking about friction because you see the word rough. And if you think about friction, you should also think about Newton's second law. So I'm going to show you. It's always going to be this. So the block is experiencing an acceleration and all of that. So they ask you to calculate the magnitude of the frictional force. So I'm going to calculate it over here. Should I use a blank thing? So first thing, I know that from the force involved, every force, no matter what kind of force it is, every force, net force in particular, will cause things to move is going to be equal to mass times acceleration. And what is a net force? The net force is the sum of the forces acting on a body. So looking at this body, him have a force we are pulling forward of 20 newtons, no matter what the force is. Him have a force we are pulling forward. And him have a force we are going to counter him, that is the frictional force. So if I'm going to say the net force acting on this body, it's going to be the sum of the forces. So if I consider going forward as positive, and then going backward as negative, the one that's countering you as negative, I'm going to call it FR, then you can say 20, which is the forward force, minus the frictional force, which is what we are trying to find. And then the next thing now, what they gave us was acceleration. So let me just make sure. I'm sure I'm using the right values. A wooden block of mass that is being pulled along a rough with a force of that. Cool. Okay, good. I just want to be safe with this. Right. All right, cool. So sometimes I have to make sure say I think it through properly. So first of all, what is the mass times acceleration? They gave you the acceleration provided by the net force. It was 5 meters per second. So they told you it's 5 meters per second, and you know its mass. So the mass, it would have been the 0.8, and then it, acceleration is 5. And that would give us how much? 4. And then that would be equal to 20 minus that. So you can see that the frictional force. So if I brought over this, it would be 4 minus 20. So I'm not skipping any steps. It end up in negative 16, negative FR, and the negatives cancel, so that you can see that the frictional force is 16 newtons. So it's all about understanding, and then you make maths to the rest. Net force is acting on the body. Some of the force pulling it forward, with some of the force countering it going forward. And then you know that net force is equal to mass times the acceleration provided by the net force. So all you have to know are transpose for FR. And that's what I did. Personally, I like to transpose before I use a formula, but this is good too. So we're good with this. And this is a repeat question. Right. So this now, so see projectile motion again. So a diagram below shows a body projected with a horizontal velocity of v from the edge of a cliff, and the height is given as 6 meters. So I'm gonna ask which case is this? I don't know about this.
Case 3.
Come again.
I was saying case 3.
Case 2.
Can't remember case. All right, I'm gonna go through the case again. You see, if you know what the case is, you don't really need to know it in an order, but I just want to make sure you have the right case in mind. Case 1 is the one where the body thrown vertically upward and downward, come back down. Then case 2 is the one when you throw it off horizontally from a height. That's this. So then turn it the other way around, so them know people have to see it the other way. And you can see that the body is projected horizontally from a height. That's case 2. So imagine you stand up on the cliff and you just throw it horizontally. You throw away your phone. Don't do social media. Throw the phone horizontally from a height. That's case 2. And then case 3 would be if you stand up on a football field and you kick the ball at a horizontal level at an angle, and it returns to the same horizontal level. Kick the ball up and it go back down. That's case 3. Case 3 is the one with the one bag of angles, because you kick the ball at an angle. Yes, because once you go through the first couple papers, you're gonna realize things repeat. Like I did say earlier, the first papers are hell because you have to use them for understand stuff. But once you go through, like by the time you reach 2014 or so, much faster. But you need to understand these. So spend the time with the first couple papers. Right. And this happens all the time. Every year is the same thing. You spend a lot of time with the first couple papers. By the time you reach 2014, easy. But that depends on if you did a follow. All right. So this now, this is case 2. So what they asked us was, so this is a reasoning question. Which of the following pairs of values of V and H give the maximum value of angle? So it's a reasoning question. So the first thing I did, I said, all right, we want to understand which pair of V and H are going to give me the greatest theta. So what I did, I said, all right, what is the formula for theta? Theta going to be equal to inverse tan Vy over Vx. Because what you remember, what you should remember is that, so this is ball. So I kept showing you how to find the resultant, which is V, but I never show you how to find the angle. I did show you guys in the paper too, though. So maybe you remember it from then. So this is Vx and this is Vy. If I drew Vy over here, you can see the right angle triangle. Yeah? Yeah? No? All right. So Vx, Vy, and this is V. I drew Vy over here so that you could see the right angle triangle. And why am I doing that is because you can see that V is the hypotenuse, Vx is the adjacent, and then Vy is the opposite. So if you have Vy and you have Vx, you have adjacent and opposite, that means tan theta, that would be Vy over Vx, adjacent, or it go, SOHCAHTOA, opposite over adjacent. That's why theta is equal to inverse tan Vy over Vx. So whenever you want to find the angling projectile motion is always inverse tan Vy over Vx. So that's why I remember this. And then I said, all right, what's the formula for Vy and what's the formula for Vx? I'm doing this because I want to find out how these values are going to affect the angle. And I want to know how those values relate to these, which are actually in the formula for angle. So I need to connect this formula to these two variables. That's what I'm trying to do. So look at Vx. Vx would be equal to, this is case 2. As you remember, Vx going to be equal to V and Vy going to be equal to 0. So we see that Vx is equal to V. So look at the relationship now between angle and Vx, which is the same as V. You can see that the angle is inversely proportional to Vx or V, which means that when you increase Vx, the angle will decrease. And what did the question ask? They asked so when you're going to get the maximum value for the angle. So by doing all of this, we see the angle is equal to Vy over Vx inverse tan. We know that Vx is equal to V. And based on the formula, you can see they're inversely related. This tells me that if I want the maximum angle, we need the Vx to be as small as possible. So I look for the smallest Vx, 10. We good?
Yes, sir.
Right. So you see how paper ones need you to think and it not going to change. So you can also reason it with Vy. Vy, how did I do Vy again? Give me a second. Oh yes. So what's the formula for Vy? Let me ask you. In case 2.
AT.
Yes, GT, nice. Very good. And we went through that. So I'm going to spread it further because what's the purpose of what I'm doing? We need to understand how I reason out questions. May I try find out, me make an equation for angle. And may I try find out how the variables in the equation are affected by these two values so that I can know how these two values can affect the angle. I found out that in my equation for angle, Vx is equal to V. So now I'm trying to find out how this affects Vy so that I can know how increasing this would affect Vy and therefore how it would affect angle. I'm going to make a sentence at the end. So, I know so Vy is equal to GT. And I also know that T, the time it takes to fall from a height is what? Square root of 2h over g. So therefore, Vy is proportional to T from this formula. When you increase T, you increase Vy. And therefore, they can see that, look at T is equal to square root of 2h over g, which means that T is also proportional to the square root of, well, T is proportional to the square root of 2h, which means that T increases when h increases. So when h increase, T will go increase, and therefore Vy will increase. So in order to get the greatest angle, when Vy increase, you need to make h increase, because when h increase, T will go increase, and when T increase, Vy will go increase, and when Vy increase, angle increase. May I make sense?
Yes, sir.
Sure. All right. So it's all about understanding this formula them so that you can use them to see how things are related to each other. If you have a question, please ask. All right, so I'm gonna move. But once you said you have the smallest v, them could have tricked you and give you another value. But notice this have the smallest v, vx value, and it have the largest h. So this one is perfect for giving it the greatest theta, because theta is equal to Vy over Vx, inverse tan. Vx is increased by Vx is the same as V, and you see that Vx is inversely related to angle. So when you have a large Vx, you would have a small angle. Therefore, you want the smallest possible Vx so that you can have the largest angle. And in terms of Vy, we saw that Vy was proportional to time, and time was proportional to square root of 2h. Therefore, when you increase height, you're going to increase time because of this formula, and you're going to increase Vy because of this formula, and therefore you're going to increase angle, which is what you want to do. So that's what I want you guys to be thinking. All right, so this now. A monkey of mass 20 kilograms rides on a 40 kilogram trolley moving with a steady speed of 8 meters per second along a flat surface. So the monkey on a trolley moving at a constant speed, and then the monkey jumps off and grabs an overhanging tree. This is a repeat question. At what speed will the trolley move off? So before we go into that, who knows the types of collisions?
Elastic and inelastic.
Right, and there's one more. You ever heard of perfect inelastic?
Yes, sir.
And for
Can't
some reason, perfect inelastic, for some reason, perfect inelastic is the one where them love to bring up the most, and them know so the man don't know it. So I'm gonna talk about collision quickly. It's a short topic. You have something called law of conservation of momentum. Law of conservation of momentum. And you know that momentum is mass times velocity. So what the law of conservation of momentum states is that the sum of the momentums before the collision is equal to the sum of the momentums after the collision, as long as there is no net force acting on the body. So if you look at bodies colliding, if you add up them momentum before, it should be equal to the sum of their momentums after. That's what the law of conservation of momentum means, because you conserve the momentum. And you always conserve momentum. That's the key. Hence, if it now conserve momentum, it will not obey the law of conservation of momentum. So I'm going to show you two scenarios. You have a scenario where, or I can probably make it 3 scenarios, just to cover more ground. Let's say I have 2 cars or 2 bucks coming together and them are gonna crash. That's the first scenario. Let's say I have 2 bucks, I go like so. It's like one car crashing at the back of another car. And then let's say you have 2 cars, them crash, and then them end up stick to each other and then move off with a steady speed. These are the 3 scenarios of master. So in scenario 1, it's the logical already know. what we understand is that the momentum, some of the momentums before equal to some of the momentums after. Momentum is a tricky topic, so you have to be careful with it. Now notice momentum, sorry, not moments. Momentum is a vector quantity, which means that if you're going in this way and you consider that as positive, going in the opposite way going to be negative. So I'm going to say MV or M1V1 plus, and then you're going to put that as negative M2V2. Just think about it. The velocity, you're going in the opposite direction, velocity going to be negative. So you're going to have a negative momentum, right? So you have to remember that when things collide, one of them have to be negative in terms of their momentum. Always remember that. And that sum going to be the same on the other side. So whatever you get for that sum over here, going to be the same as the sum over here. There's a question just like that. I don't remember the answer for it though. This scenario, they're going in the same direction, so both of them going to be positive. So you can say M1V1 plus M2V2, and then the sum of that going to be the same on the opposite side. Now you have a third scenario when them stick to each other. This is actually called perfect inelastic collision. I'm going to talk more on it after. So perfect inelastic collision. Because my friend said there are 3 types, but we're going to talk more. Usually what happens is that them start off with 2 bodies moving at opposite, moving with different speeds. So you have M1 at a particular speed and M2 at a particular speed. And then them would collide like a typical car crash, and then them stick to each other and then move off at a set speed. So they move off as 1. So them have a 1 speed because them move off as 1. So how the formula would look for this? That's the question. It would look like M1 times V1 plus M2 times V2, assuming that they're going in the same direction. If you're in the opposite direction, you'd put 1 as negative. But when you reach to the after the collision now, when them stick together, what you have to do is say, all right, the masses them are now 1. So you're going to say M1 plus M2, and then they're both moving at a constant velocity. They're moving at a steady velocity. So this is the formula that you use for a perfect inelastic collision. Before them they move as separates, and then after them have a stick up, them come together as 1. So them mass is 1 and then velocity is 1. So I said there are 3 types of collision. You have elastic collision. In elastic collision, the momentum is conserved and the kinetic energy of the body is also conserved, and the total energy is also conserved. So elastic collision would be like in atoms. In chemistry, for example, atoms collide in such a way where they don't lose any kinetic energy when they collide. As soon as when they collide, because they have so much kinetic energy because they're moving in constant random motion, when they collide, they don't lose any kinetic energy in the form of heat energy during collisions. They have the same amount of kinetic energy before and after collision. So that would be called an elastic collision. Kinetic energy remains the same before and after collision. No loss when them hit. And therefore total energy is the same. But then you have inelastic collision. In inelastic collision, firstly, the momentum has to be conserved because remember, you're following the law of conservation of momentum. So same before and after. However, the kinetic energy is not conserved. And this is what usually happens in real life. Because what happens is that when 2 things collide in real life, after collision, you're going to lose some of that kinetic energy. Because when you collide, you end up use some of the kinetic energy to overcome that friction so that you can move again. And that kinetic energy gets converted in heat energy, or light energy, or electrical energy, so that you can see the crash and fly and all that stuff. So you lose some of the kinetic energy to convert it into heat energy and other forms of energy. But since you're converting the energy and you're not destroying it, that means you still have the same total amount of energy. So the total amount of energy is still conserved. Then you have perfect inelastic collision. We're good so far,
Yes, sir.
right? So perfect inelastic collision is it's just like inelastic collision. The only difference is that the bodies stick together. So in inelastic collision, the bodies don't stick together. When it perfect inelastic collision, so this is like normal inelastic collision, but then you have perfect inelastic collision. In perfect inelastic collision, the bodies will stick together. So it's the same thing where you say momentum is conserved, kinetic energy is lost, converted to something else, but the total energy is conserved. What, understand?
Yes, sir.
So in inelastic collisions, the bodies stick together. That could look like this scenario or this scenario. It could look like either of them. So these two formulas are really for when you have inelastic or elastic collisions. Because the bodies are separate before and after. So it's either inelastic or elastic collision in these two formulas. But then this formula is specifically for perfect inelastic collision because the bodies stick together and the kinetic energy is lost. Right, so going back to our question with the monkey. So the monkey says, all right, let me jump off of this. And we can understand more about this, yeah. What happened out this stuff? All right, so we have to understand it. The monkey is at a mass of this on the trolley with a steady speed. So this would be when the monkey and the trolley is one. So how would I represent this? Some of the momentum before it, or some of the momentum after. But if you consider this as two bodies moving together as one, it would look like this: M1 plus M2 times V. Just like in perfect inelastic collision. So you have to be flexible. You realize this is similar to perfect inelastic collision. Then them said the monkey jumped vertically to grab an overhanging tree. And reason that out. So M1 is the monkey. If the monkey jump over to grab an overhanging tree, what do you think is happening to his velocity?
It reduces to 0.
Exactly, because him now move if him a hang off of one tree. So when him jump on the tree there, him not move anymore. So now it's just the trolley and move along its way at a particular speed, which they probably gave us. So you have all the information you need. Them say, what speed will the trolley be moving off with? So we're trying to find V2. So you're trying to find V2, you can simplify this formula into saying, all right, M1 plus M2, put that in brackets times V, all over M2 equal V2. And you know this are going to cancel out because the V is 0, so 0 times whatever that is going to be 0. So you just transpose your formula first and then you plug in your variables, right? And when I did that, I got 12 meters per second. So try it yourself. Practice to work these things out. Here's my calculator.
Sir,
All right?
could we see the information again, please? Like the masses?
Yeah, let me go carry it up, sorry.
Thank you, sir.
So work it out for yourself because this is gonna make it easy when you're in at the exam. You already know what the answer for this is and you've worked it out. So you're not sweating. So you say 20 times, no, plus 40 and that's 60 and then divide that by, well, let's multiply it by the speed of 8 first. And then I divide it by the mass of the second one, which is 40. And you get 12 meters per second. Easy. So all of that comes with understanding the topic. We good?
Yes, sir.
right? So now, anytime you see a collision question again, you shouldn't get it wrong, unless Cape really bullshit it. Look at this now. Water is poured in a measuring cylinder until it reaches this volume, marked on a scale. If a lump of ice of 50 grams is floating in the water, what will its new reading be? So this is just something to remember. The density of water is equal to 1 gram per cubic centimeter. So for every centimeter cube, it corresponds to 1 gram, which means that if you have 50 grams, you're gonna have 50 centimeter cube. Cross multiply. So if them add 50 grams, you add 50 centimeter cube, so the volume increased by up to 300 centimeters cube. And this is important for chemistry. All right. So
Sir, could I ask you the question again, please?
no problem. This is important for chemistry, cause you know, like in chemistry, when them tell you to do the energetics questions, enthalpy in particular, them usually would give you the volume of the liquid, and then you have to know so that can convert to mass. In enthalpy questions, where you have to use MCAT. So this is an important principle. The density of water is 1 gram per centimeter cube, or 1,000 kilograms per meter cube. So know the two of them as well, because sometimes you see it as 1,000 kilograms per meter cube. And that's all because of SI units. If you were to convert centimeters cube into meters cube, you'd get 10 to the negative 6 meters cube. Why? Because every centimeter is equal to 10 to the negative 2. And if you times that by 3, 10 to the negative 2 meters times 10 to the negative 2 meters times 10 to the negative 2 meters, you end up with 10 to the negative 6 meters cube. And then gram is equal to, so from small to big, what we say we do? We divide, right? From small to big, we divide. Remember me to show you, you make your hand go apart. So from small to big, you divide. And then from big to small, you put your hands together, you end up a multiply. So this is from small to big, you're gonna divide by 1,000.
With 10 to the negative 3 divided by 10 to the negative 6.
Yes. And when you actually work that out, you get 1,000, because when you divide, you end up reciprocate. So it would have been like 1/3 multiplied by 1,000,000. And then you would end up get 1/1,000 multiplied by 1,000,000, and then that would have cancelled, so you'd end up with 1,000. Something like that. Some maths. So SI units there, I'm show it, me take the time to explain that, because sometimes that is useful. Knowing that conversion. All right, so I'm gonna move. So I'm gonna explain the important topic here, terminal velocity. We're good?
Yes, sir.
So you realize the main thing is to kind of make sure you understand the topics then. Or you're gonna waste your time as you go forward. Trust me. All right, so terminal velocity. What is terminal velocity? Let me ask. I don't think it come on the paper too, thank God.
Terminal velocity is that the maximum velocity that obtainable by an object falling in a medium.
Excellent. But we need to understand that now. So I gotta understand it. You're correct. So I'll show you exactly why it is that maximum velocity, that constant maximum velocity that it falls at. I'm gonna show you. And there's a video that you can watch about this as well. Go on YouTube, type in terminal velocity. There is a video with a parachutist, and they explain every stage of the parachutist falling. Even when the parachute is opening parachute, that's another stage as well, where it's not even in the study guide. So that video, I think it's by GCSE physics or something like that. one white background kind of video. So if you care about that enough, go watch that video. But let's talk about terminal velocity. So what happens is that in this we kind of move from uniform acceleration. Well, think about bodies that don't have a constant acceleration now. That is terminal velocity. And another example is simple harmonic motion. The acceleration changes. So what happens is that you have this body. I have to look at it in different stages. So I draw one plane. And then you have parachutists at the top of the plane. Now, so I'm going to explain how we get terminal velocity. That's what we're about to do. So the first thing, we have to look at some parameters. What is the person's velocity up here? And then we're going to ask what is his acceleration and what is his force, his net force. So at the top, the person will have 0 velocity because you don't start moving yet. So there's no velocity. And at the top, the net force, because here's the thing, 2 forces that you're concerned with. As you fall, you have a weight force pulling you down, and then you have a drag force that's trying to counter you. You see this drag force? It's proportional to 2 variables. It's proportional to the velocity that the body is falling at and surface area. Why is that? Because as it falls, if it falls faster, it will collide in more particles and therefore it will experience more drag. So faster it drop is the more drag force because it will collide in more particles. And if it have a greater surface area, if it's bigger, it will collide in more particles. So these are the only 2 variables that is proportional. So this is in the study guide. And then you have weight force that just goes down. So initially, the velocity of the person in the plane is 0. Then the net force of that person would be the sum of the forces on the body. So if I consider down as positive and up as negative, right, I'd end up with a formula like this. But look at it, the drag force. You see, because the drag force is proportional to velocity, and the velocity is 0 initially, when you jump out of the plane initially, there would be no drag force. So initially, first scenario, jumping out of the plane, you're gonna have a weight force of 0. You're gonna have a net force that is equal to the weight force because you don't have any drag force initially. Follow me with this, guys. If you understand it, you don't have to sweat it. So the first thing I did, I said, what is the velocity? Then I said, what is the net force? The net force is the sum of the forces, but initially, that drag force is 0. Why? Because velocity is 0. And I showed you that the velocity is proportional to drag force along with surface area. Right. So I have a space for acceleration. Now, Maga asks, what do you think the acceleration going to be for this person?
(9.81 meters per second squared).
Why
Gravity.
you always do that? G, yes. Very good. Acceleration due to gravity, 9.81 meters per second squared. And you see why? Because him only have weight force acting on him. Sorry if I said that, because practice was the number for real. There's a difference between thinking 10 versus 9.81 meters per second squared. There's a big difference. So it's going to be G, and you see why it's G. So let's do further. Next scenario, the person jump out of the plane. So this person doing bungee jumping, living their best life, jump out of the plane. And we're going to look at the factors, the variables again. And it's going to make sense. First thing, velocity. Now you see, because as the person fall, they have a net force acting on them. What force are going to do? Force produce an acceleration. And what acceleration are going to do? Acceleration causes a change in velocity. The person is falling due to acceleration. That velocity is going to increase as the person falls. So as the person fall, them are gonna move faster, then velocity are increase because there is a net force acting on them, therefore there is acceleration, therefore velocity now gonna stay zero. So the next thing we need to do is look at what the net force are gonna be. So it's the same steps I'm gonna do for the three scenarios. So it's the same thing, but this time, what you notice, you see the drag force? Watch the drag force. The drag force are gonna actually increase. Why is it increasing? Tell me.
It's direct proportional to velocity.
So since you're falling and you have that force making you fall faster, so you have acceleration now, so you have moved with an increase in velocity. Since you have velocity increase, you're gonna collide in more particles and your drag force are gonna increase as well. So you realize that the net force is decreasing as you fall. This is interesting. This is a very unique scenario. And we're going to see it on the graph. And then the acceleration now. What do you think I got to the acceleration?
Acceleration decreases.
Exactly, because if the net force are decrease, the acceleration is going to decrease. Because what causes net force? What causes acceleration? Net force. Net force provides the acceleration because net force equal mass times acceleration. So understand the pattern is the same thing we've been saying since Newton. Net force equal mass times acceleration. Acceleration produces a change in velocity. That is the pattern. So we just look at all of these things putting together. So we start by saying, oh, the pressure velocity increased because there was a net force. That increased velocity increased the drag force. Therefore, the net force decreases. And therefore, the acceleration decreases as it falls. So guess what's gonna happen? I like to think about this like a limiting scenario. It's like the system is setting it's limiting itself from falling too fast. You're gonna understand what I mean by that. Because as it falls, it have the force to draw it down so that its velocity increase. However, as that velocity increase, it's decreasing that same force that's supposed to be causing its velocity to increase. Tell me if that makes sense. Fine.
Yes, sir.
Now I'm gonna show you. All right, fair. Because that's essentially how we're gonna eventually reach the state of terminal velocity. So let me show you what happened now. So let's looking at the formula. Look at net force. The net force we realize is equal weight minus drag force. But you see, if we keep falling and increasing our velocity, you're gonna realize that the drag force are gonna keep increase, and therefore that net force are gonna keep decrease, and the acceleration will keep decrease until eventually that person are gonna reach a point when that net force, when the drag force becomes equal to the weight force. So when these two things become equal, it are gonna reach a point when, so if those two are equal, it tell you that the net force is 0. Because once you have enough of this to cancel out this, you're not gonna have any more net force. So when the weight force, when the upward force is equal to the downward forces, you're not gonna have any net force that pushing out. So you're gonna have 0 net force, and therefore you're gonna have 0 acceleration. And if the acceleration is 0, what happens to your velocity?
No longer changing, right?
It has a constant velocity. And what do you think you call that constant maximum velocity where the person fall at?
The terminal velocity.
Exactly. So that's so you reach that rapid terminal velocity once you drop out of the plane. So if you understand these steps, you understand terminal velocity. So let me repeat. Firstly, it's just these 3 variables you need to understand. The person jump out of the plane, and you have to remember that the drag force acting on the body is proportional to the velocity of the body and the surface area. As no, what that mean? Or maybe that's no, but you all right. And you see the video I'm gonna tell you about, it actually show you what happens when you open the parachute. Yes, when you open the parachute, surface area becomes an issue. And then that creates this different terminal velocity. But those things I can't need you to know that. But just in case you could watch it because it's not that bad. Right, so repeating, the person, them a jump out of the plane, live them life. And well, remember, so two forces, weight force, drag force. Drag force proportional to velocity because more velocity, more leaking, and then surface area. And initially velocity is 0. The net force, you see where the net force be equal to. If the velocity is 0, drag force 0. So the net force can be equal to the weight force initially. Therefore, acceleration is equal to acceleration due to gravity, because weight force provides acceleration due to gravity. As the person fall, that net force is going to increase their velocity, because what net force do? Net force provides acceleration, and that acceleration causes increased velocity. So we're saying that as a person fall, the velocity increase. Basically, as that velocity increase, the drag force will also increase because they're proportional. Therefore, the net force will decrease as a result, and the acceleration will also decrease. So that's why I did call it a self-limiting kind of thing. Because even though when it did a fall, it was the net force that caused the velocity to get high in the first place. But because that velocity got high, it decreased the net force. So the net force caused the velocity to increase, but then when the velocity increased, drag force increased, and then the net force increased. So it's like a self-limiting thing, so that it don't get too high. It can stop itself. And just looking at it mathematically, we see, so wait, the velocity increase, drag force increase, net force will decrease, acceleration will decrease, until eventually the drag force will be equal to the weight force, so that when the drag force is equal to the weight force, net force will be 0, acceleration will be 0. By this time, your velocity would have increased to a particular point, and it just remained constant after that, and that's your terminal velocity. That's the logic behind terminal velocity. How you represent this on a graph is a VT graph. And you're going to select this curve, and then it plateaus. Because in this part, it's a, remember your VT graph state. This is a non-uniform deceleration, which is exactly what's happening. The frown, non-uniform deceleration. You see that the velocity, the acceleration rather, is decreasing as you go down. It's changing and it's decreasing. So it's a non-uniform deceleration until eventually the acceleration. So eventually, you're not going to have any more acceleration, and you're going to have a constant velocity, which is your terminal velocity. We're good? Go and take a short break. We're good?
Yes, sir.
Yes, sir.
Right. So contemplate this. Very important. I'm going to use the bathroom and come back. Mm.
Back. Ready?
All right, so we're supposed to can answer terminal velocity questions. All right, so let me go back. Ready? Back. Back. No. Back. No.
Yes, sir.
Back. All right.
Yes, sir.
All right, so let's reason out this. Cause you see the thing is paper one not ask straightforward questions and you have to understand the stuff then. So pre this now, look at this. A parachutist is falling through an air of uniform density from a great height. So it's falling through the air with a set density from a height. From a great height, you know, say it's gonna end up at the free falling, where eventually it's gonna reach its terminal velocity and go through all of those three stages that we did talk about, the three stages of depression. And which are the following graphs show how its acceleration varies with time. So your understanding for this, you remember that initially its acceleration would be equal to what?
The gravity G.
Because you remember that initially we went through it. Net force was only due to weight force because there was no drag force, because drag force was zero, because velocity was zero. Initially, acceleration equal gravity. But as the thing progressed, you realize that the drag force started to increase because the weight force increased, because the velocity increased, right? So the drag force increased because the velocity increased, therefore the net force decreased and the acceleration decreased. And then when you reach the end of it all, the acceleration is what?
Zero.
Zero.
So I'm gonna ask again, sure I understand this? So that
Yes,
graph is the best graph to represent that. You see them start at acceleration due to gravity, and you see that it progresses till it reaches zero. And at this point is when you have the terminal velocity. Very good. And this is an acceleration time graph. Good. What would be the gradient of an acceleration time graph? I'm not certain, so I asked him, I never really think about it. Not a SI unit, where we know. All right, sure. So that is that. So I'm show you
Sir,
yeah.
just want to confirm, gravity is not direct proportional to time, right?
In which
For the
scenario?
terminal velocity. No, yeah.
No, cause remember gravity is set 9.81. And then time is just going to go along. So all right, the only reason, because what graph is this? This is the acceleration versus time graph. It just so happened that this acceleration here is the acceleration due to gravity. So that acceleration is inversely proportional to time because as the person fall, them acceleration decrease. That's what you want to say. Not gravity specifically, but acceleration of the falling body was inversely proportional to time. Because as the person fell, their net force decreased and therefore their acceleration decreased. Making sense?
Yes, sir. But my problem was that D had the same thing, but just with a
Oh.
straight line.
Good. So well, I think this is because it's not a uniform thing. When you see straight lines, it's like a constant gradient kind of thing, and I don't think it's uniform. I think that was the reasoning, but I did go with this because this suggests that it's a non-uniform motion. Gradient wouldn't be constant, but then when I checked the gradient all the way, it wasn't something that we really know. Mass, well, distance per second cube. But I would go with B because it's non-uniform. Right. So
I guess so.
good question. Mhm. All right. So on the topic of proportionality, well, we'll get to that soon. I explored ChatGPT today. I'm gonna try to see if it did know physics, but iffy, kind of iffy. All right. So two rocks are spun around in circular paths at the ends of strings of equal lengths. What must be the same for both rocks if the tension in the spring is equal? So those are a quick recap through circular motion. Just a quick recap, don't want to spend too long. Make sure you understand circular motion. I'm gonna do it on the whiteboard. All right, so ready? I'll do circular motion recap. So what is circular motion if you were to define it?
Circular motion is the motion of an object in a circle.
Give me more. Why is it in a circle?
Because it has a resultant force called centripetal force acting on it towards the center.
Right, right. And the only thing you could have told me extra is that the resultant force there is perpendicular to its linear velocity. That is centripetal. That's circular motion. So what I mean by that. So quick recap. So two scenarios. All right. How circular motion going on my head? I remember firstly, you have a series of formulas that can be used for any case that you have. Then you have different scenarios. You have a horizontal circle, a vertical circle, you have something called banking, and then you have a pendulum, a conical pendulum. So if you master those, you're not getting circular motion wrong, but them easy in comparison to what you've done already. So it starts with this velocity and force. You see, when a body have its velocity and its force in the same direction, it's going to move, its motion is going to be forward. When a body has its velocity and its force in opposite directions, its motion is going to be backwards. That's what I should have, backwards. Because like you're having a countering force, like that thing. But what would happen if you have the force acting on the body being perpendicular to its velocity? That's the question. In a scenario when a body has its force perpendicular to its velocity, the motion of that body ends up being in a circular manner that is in the direction of that centripetal force. That's what they call the force. So force is directed to the center, perpendicular velocity, which we'll be able to calculate. It's going to have a motion that is going in the direction of that centripetal force. And then when the body reaches here, so same logic. It's going to have a force directed to the center, perpendicular velocity, and then its motion is just going to go in the direction of that centripetal force. And when it reaches here, same thing. Perpendicular force to its velocity, noting the force is directed to the center, its motion is going to be going towards the direction of that centripetal force in a circular manner. And then we're going to have right here, so centripetal force directed to the center, perpendicular velocity, and it's going to follow out the circle. And this is how things move in a circle. This is how planets orbit the sun, because they exhibit circular motion. You have a centripetal force and a perpendicular linear velocity. Too good? And then why I call it a linear velocity is because it's, if something were to happen to that centripetal force, the body is going to move off in a straight line in the direction of that linear velocity, a tangent, going to fly off in the linear, in that straight line. So this is a linear velocity, and you'll be able to calculate it. So I'm going to show you the formulas now, easy formulas. So the first thing, consider a circle, of course. And from here, circle, you should have think about circle theorem kind of things, but we're not going to go too deep into circle theorem, thank God. It's just now, first formula kind of rely on it a little. Let's say I want to find S. This is an arc. How you find an arc? You see the radius times the angle. This formula not as important. So you find an arc, it's radius times angle. That's from maths. Now, let's say I want to find something called angular velocity. Angular velocity is represented with the Greek letter omega, which is the W, omega. And what the angular velocity is a measure of angular displacement over time. Because if it's an angular velocity, it's telling you the velocity of the body as it travels with an angle associated to it. It's the velocity as it goes in a circle. And if you're saying a velocity that's dependent on an angle, that means you're going to say angular displacement over time. So not just displacement over time, but rather angular displacement over time. So this angular displacement, how we're going to get it? We're going to use something like radians. What we need to know about radians is that 2 pi is equal to 360 degrees, the entire oscillation. And then you do maths to calculate the rest. Half a pi is 180 degrees. So let's say I don't want to find the angular velocity. I want to make a formula. There are two formulas to know. If you look at the entire oscillation, the angular displacement can be represented in angle or in radians, but we represent it in radians as 2 pi. But the entire oscillation can be represented in 2 pi. Because 2 pi is equal to 360 degrees, the entire oscillation. And what you call the time it takes for the entire oscillation?
Time period.
Period. So you end up with this first formula, 2 pi over t, right? So the first formula allows you to find angular displacement when you're given the period of the oscillation. Once you have period, this is the formula that should come to mind when you're thinking angular displacement, 2 pi over t. But notice 2 pi, and then you can say times 1 over t. That's the same as 2 pi over t. 1 over t is the same as frequency. Therefore, you can also represent it as 2 pi f, which is another beautiful formula, because if I have the period and I want to find omega, I can use this formula, 2 pi over t. If I have the frequency and I want to find omega, I can use this formula, 2 pi f, and vice versa. If I have omega and I want to find frequency, we use that formula, you get the idea. Very good. And you use this in simple harmonic motion as well. Next formula, the linear velocity. So remember, the linear velocity is the one that's perpendicular to that centripetal force. You can calculate it with the formula r times omega. The reason being because remember, velocity is displacement over time. And if you look at the entire displacement around this is a circle. Circumference is 2 pi r. And then the entire time would be period. So you realize 2 pi over period is omega r. So V is equal to omega times r. And it's important to remember that because there is a question where they like set out the formula and you have to kind of pick which one is the correct one. And it's because you remember this, why you get that right. The answer did have A times R equal V and something else. V squared over R, omega thing. No, A was equal to V times R or something like that. But you have to understand it from this level. So acceleration equal V squared over R. This formula, we don't have a derivation for it, we just remember it. And also, what's the other formula for centripetal acceleration? Remember,
Omega
so
squared R.
yes, very good. Omega squared times R, very good. And this formula reminds me of simple harmonic motion because simple harmonic motion acceleration is omega squared times x. Remember that? We're going to see it. So, and they're connected because both of them have angles when they move. Circular motion have an angle, simple harmonic motion have an angle. So it's all connected. And then the last formula that's general is this one, the centripetal force, which is mass times the centripetal acceleration. So it's either mv squared over r, or you can say m omega squared times r. And it's crucial to remember the two of them, or you lose mark. So good with this? So now go through the different scenarios now. We good with this?
Yes, sir.
Yes, sir.
Good. So knowledge I keep. Now we need to look at the horizontal circle. Quickly through the horizontal circle. This would be like you have your hand on your side and you spin and you make this flat circle that's horizontal. As the name suggests, it's a horizontal circle and it goes around. Oh, all right. So that's a horizontal circle. I hope you guys remembering the answers for the questions we do as well, because them will soon repeat. So try to remember answers or at least know how to work about the question. Anytime we'll get to the point when it start repeat. All right, so first thing for this. Notice for this circle, the length of the string corresponds to the radius. So length of the string corresponds to the radius. Very important. Now I'm going to do a free body diagram, which is basically me showing all the forces acting on the body. Free body diagram is when you show all forces acting on the body. So you can say weight force acting down as it should, and then you can say there's this force called tension, which will act towards the point of suspension. When you suspend it at a point, tension go up to that point. And centripetal force would be the force directed to the center. So you realize for a horizontal circle, the centripetal force is equal to the tension force. So that means the tension force in a horizontal circle is equal to mv squared over r, or it can be m omega squared times r. We're good? That's that. We're good? We're good? Are we okay?
Yes, sir.
Good, good. Drink some water. To process that. Ask questions, guys. Right, so let's go over like so now. So what I'm going to do now is the vertical circle. This is probably the most asked. So this would be like you hold your hand in front of you and you make a big circle that is going up and down, and it's making a big circle in front of you. So it's a vertical circle. It exists in the vertical plane. Notice the horizontal circle is just flat in the horizontal. The vertical circle is in the vertical plane, it goes around. One time I did try use my earphone to represent this, and I mashed up my earphone. Not doing it again. So make sure you understand this. Vertical, and now we need to do the exact same thing. So the first thing as well, notice the length of this is going to correspond to the radius. Very important. So I'm going to, you have to consider it at 3 points, top, bottom, side. So at the top, I want to find out what the centripetal force is. Centripetal force will be all of the forces acting to the center, some of the forces to the center. So you have a tension force to the center, and you also have weight force going down to the center. So that centripetal force would be tension plus weight. But I'm going to solve for tension. Tension will be centripetal force minus weight. Right. What about the bottom? Same logics, we're going to find out what the centripetal force is. You're going to have a tension force going up to the point of suspension as it should. And you're going to have a weight force going down. Notice they're in opposite direction. So the weight force will go opposite, negative sign. Therefore, the tension look like this, plus sign. Okay, bring it over. So what about at the horizontal? Tension force will go, and the weight force will go down like this. So notice, notice the weight force has no effect on the tension force when it's on the horizontal. It was the same thing for the horizontal plane. If they're perpendicular to each other, the forces don't affect each other. And energies wouldn't be affected by each other either. So kinetic energy wouldn't be affected by a force in the perpendicular plane to it. That's a MCQ. So I'm saying that is because the weight force would have nothing to do with up here. Nothing not going with that, because them they're in a two opposite plane. This is vertical, this is horizontal. So you realize that the centripetal force will be provided only by the tension force in the vertical, in the horizontal region there. So the centripetal force is equal to the tension. So tension will be equal to mv squared over r. Right. And observation, you notice that the tension force, so the tension force is that force you feel when you're going like, you're, for instance, in a merry-go-round. When you reach at the top of the merry-go-round, it feel light. When you reach at the bottom, you feel heavy. That's the tension that you're feeling. You realize at the top, tension is the smallest. Tension is small at the top. When you reach at the bottom, tension is high. And then in the middle is halfway. So I remember that it's smallest at the top and it's bigger at the bottom. So just think about a well-shaped apple. Yeah, that's what we're thinking about. All right. And that's the vertical circle. The only other formula is that V, if you want to find the smallest velocity, is V is equal to R times Q. Drink some water. All right, we're good.
Excuse me, sir. Something that I have a problem with is like, why is it the centripetal force is always going like outside away from the center?
Outside. How we calculate the centripetal force is by finding the sum of the forces going to the center. So the centripetal force is just the forces directed to the center. So when we're at the top, the centripetal force is the weight plus the tension. And then we transpose for the tension. When they're at the side, the only thing that's going to the center is the tension. And when they're at the bottom, you have the tension going to the center, but the weight is going against the center. So that's why we put negative for the weight there. Mhm. That clear too?
Thank you, sir.
Good. So tension, the centripetal force is just the force is going to the center, which means the centripetal force is never just a set thing. It depends on the scenario. Can be different formulas, different things. It's just the sum of the forces directed to the center. Calculated with mv squared by r. Right. All right. So now we're going to talk about banking. The banking one. So banking relies on vectors. We have an angle here. So you have perpendicular normal force. So what happens is that in banking, imagine you have a car and this is a slanted road. Imagine you're there like Ozemarty or one of those places where you have a road with curve. And the car is going around the road like this. And then it gonna have a weight force that's acting down as it should. But it's get weak. So notice I draw a normal force. The normal force here can be broken into its components. Why am I doing that? Because I want to find the force directed to the center. This angle right here will correspond to this angle right here. We can prove that 30 degrees, 30. This would be 60. And then this would be 30. So we can see that this angle corresponds to this. And that's important because then we can see that this component would be n cos theta. And then this component is n sine theta. Which tells me that in the horizontal plane, n sine theta is acting to provide the centripetal force. Right, go to the center. And in the vertical plane, n cos theta, it's going to cancel out the weight force. Because since the car is not going upward, it now elevate up or go down in the ground, it tells us that there is no net force acting on it in any different direction. So overall, the upward forces cancel out the downward forces. So there's zero net force. Right? So upward force cancel out downward force, so n cos theta equal mg. And then the last thing, vector reverse. They like to see you find the angle. So how you find the angle? You're going to divide n sine theta by n cos theta. So you end up with mv squared over r divided by mg. And that going to cancel out to give you v squared over rg equal, because n is going to cancel, sine theta over cos theta give you tan theta. This is a formula you want to remember. We're going to use it. So you can say inverse tan v squared over rg.
Excuse me, sir. Can you repeat? Because I got up for 5 minutes.
Oh, I was saying that n sine theta over n cos theta, that's how we can find the angle. We know n sine theta is the centripetal force, so that's mv squared over r. And then n cos theta is the weight force. So when you work this out, this is the same as saying mg over 1. So multiply, I have 1 over mg, the m's can cancel. So you end up with v squared over rg. So inverse tan v squared over rg, that's where you get theta. And there's a question where they ask you about this in a very tricky way. All right, so I'm going to move. We're good?
Yes, sir.
Then try not to choke, my voice feels funny. All right, so we'll go back to Oh, we have one more scenario. Conical pendulum. Hmm. Hmm. So the conical pendulum, it's like the pendulum is like somebody hold a man down and they must spin the thing around. So it makes a cone like this. We can do firstly, did I show you what radius was? Let me go back for a second. So for here, notice the radius this time going to be whatever this distance is. They probably give you a radius here. But for the next one, radius going to be from here to here. Mm. The weight force. So this is the radius. This is the length of the string. So you have to realize that the length of the string is not the same as the radius in the conical pendulum. And this angle right here, we're going to say that it corresponds to this angle right here. So that we can say this component. So if we split the tension into two components, why are we doing that? Because one on one will provide the centripetal force. So splitting the tension into two components, we'll end up with T cos theta and then T sine theta. So we're going to say T sine theta equal mv square over r, very similar to previously. It's just if you understand the concept. And then T cos theta equal mg. And it's the same logic, forget the angle. You're going to divide T sine theta by T cos theta. You're going to end up with inverse tan. What was the formula again? V square. Yeah. This? Thing would go too fast. This is it, right?
V square equals to RG tan theta.
V square. All right, fair enough. Tan theta equal V square over RG. Excellent. So it's the same logic for this. And that's basically circular motion. Can't really give much more for that. And first time if I feel like it won't go fail marathon. Suspicious. All right, we'll go back to the question. Just take it easy with the voice. But we're good though. We okay? So when we see circular motion questions, we shouldn't get them wrong. All right. So this question is going to be so they said two rocks are spun around in a circular path at the end of a string of equal lengths. So just imagine both of them spinning as a horizontal circle. And they're doing so at the same length. And they ask what quantity must be the same for both rocks if the tension in the string is equal. So I'm going to ask you, what is the tension in the string equal to in a horizontal circle?
It's equal to the centripetal force.
So I did that because I want to see now, all right, which variables are affecting the tension? That's what I want to see. So I look in the formula and I say mv square over r, and I see that these variables therefore affect tension. They told me that the length is equal for both of them, which means that the radius is equal for both of them. Because for the horizontal circle, the radius is the length. Right? That's why I'm gonna stress that. Now, for this question, technically, mass and velocity could be used. I personally would go with mass, but when I did check it up, some sources that say speed. So go with whatever your heart say. Personally, I would go with mass, but I saw some sources try to defend the speed argument, and you can see why both of them would work because both of them affect extension. So, and I haven't found anything to support, say, oh, it's mass versus its speed. And I don't think this is a repeat question either. I haven't seen it again. So, and I went through. So, hopefully, this is not your problem come Thursday. But between the both of them. All right. So this now, airplane A is traveling twice the speed of airplane B. Airplane A is half the mass of airplane B. Which of the following statements is correct? Who remember how I did tell us to deal with these questions? I'm going to show you a trick. The other day I saw somebody use this trick. One of my students from last year, them using it in Unit 2. I felt proud because I actually remember it. So here's the thing, proportionality. When you understand proportionality, you understand how to make equations. There are two scenarios. Is either you're gonna have something directly proportional to something, or it's gonna be inversely proportional to something. So when this increase, this increase. When this increase, this decrease. So I'm going to analyze this first thing. I can use this and make an equation. So just by knowing that two things are proportional to each other, I can make an equation from it. For example, I know that force is proportional to extension based on Hooke's law. By that, I could create the Hooke's law equation. How do them do that? Because maths people tell them, say, all right, whenever you see two things proportional, it means that it's equal to the proportionality constant times that value. That's what it is. K. And what is proportionality constant? Proportionality constant is just a variable that is used to calculate these two varying variables. What do I mean by that? Imagine, say, I have A and B, and A is, let's say, velocity, and V is time. And you know, so when velocity increase, time increase, and vice versa. You know them related to each other. But you don't know if maybe a 5 meters per second velocity, which time I will correspond to it. Even though you know, so when both of them change, them affect each other, you don't know what specifically that are going to be corresponding with that. So you want to be able to can have a velocity value and know if you calculate the time corresponding to that velocity and vice versa. You want to know where the A value be and can calculate the B value corresponding to that. That's the purpose of proportionality constant. Because with a proportionality constant, you can look at the scenario and say, all right, I am going to only look at the relationship between A and B. If I'm only going to look at relationship between A and B, that means I'm going to need to keep all other variables constant so that all other variables, they don't affect those two values. So when A increase, the only thing we could have caused A to increase is because B increase and vice versa, because we keep all the other variables constant. May that make sense? And when you put all of them constant, that variable that you put together, that's the proportionality constant. May that make sense?
Yes.
Guys, man, I lose my voice for this, so make sure it's for real. I haven't lost my voice in a while. Crazy. I'm gonna have to do something to you tomorrow. But if you understand that, that makes sense. Because it's the same logic with gas laws. When you think about Boyle's law, what is Boyle's law? Quickly.
Boyle's law is pressure is inversely proportional to volume.
Right, that is exactly it. So you know what you know how that formula get made? The idea was that they found out that there was a relationship, there was a proportionality. Pressure was inversely proportional to volume. And from that, they made a formula. And here's the thing. The proportionality constant in that formula is just a factor, a number that keeps all the other variables constant, because they only want to see what volume, how volume affects pressure and vice versa, how pressure affects volume, which means say you don't want temperature change. You don't want the number of moles change. You don't want none of them something that change, because if you change temperature, that can affect volume. Because you know when you increase temperature, molecules collide more and then volume increase. You don't want that. You want to only see the effect that pressure has on volume and that volume has on pressure. Therefore, proportionality constants allow you to see these relationships by keeping everything else constant. So you're asking for an example. Let me give you an example for this one. Hooke's law. What the man Hooke did realize was that force was proportional to extension. That's all him realize. And because of that, he could say force was equal to a proportionality constant times extension. And that proportionality constant is the spring constant. Because some of them proportionality constant them give name. Just like the G, the big capital G in that topic there. Newton's universal law. 6.67 something. And that spring constant is keeping the variables constant. So you have a set amount of extension with a particular amount of force. Or maybe a better one would have been Charles' law. Charles' law states that volume is proportional to temperature. Therefore, volume would be equal to a proportionality constant times temperature, right? And this K keeps everything else constant. So pressure is constant, number of molecules is constant. So that we can only see the relationship between these two things. May that make sense? You wouldn't believe how much we rely upon proportionality constant for paper one. You're going to see. Trust me, we're going to see. I'll show you our next thing now. So I'll show you the first trick. How to make an equation from proportionality. Easy. All you do is put equal and K. Next trick. Let's say I have two scenarios. Let's say I did have a A and a B at one case, and then you did have A and B in another situation. So A1, B1, and then A2, B2. Can I make a formula that equates both of those things together? That's what I need to be able to do with any situation. And I'll show you how you do it. The proportionality constant is set, right? Once it's for that situation, it now gonna change. So I can say A divided by B equal K. That K is set for the situation. So no matter how you change A and B follow, K is going to be constant, which means that A1 over B1 will be equal to A2 over B2, because both of which are equal to K. We can see that?
Yes, sir.
Yes, sir.
You see this, the amount of time now to use this to calculate, we're going to see it. Make sure you know to use this ability. It's like a skill now. You know to make this with a formula. So I'm going to show you with others. So A over B, and then let's look at the inverse proportional now. And then I have one more trick. So I'll do the same thing with inverse proportional. A is equal to, you're going to put K instead, which is proportionality constant divided by B. All right. And then, that's why when you have a value on the denominator, you know say it's inversely related. When you have a value on the numerator, it's directly related, right? So the next thing would be to do something similar to this. I want you to be able to make a formula where you can relate A1, B1 with A2, B2. So you know that A times B is equal to K. And that K is constant, no matter how you change A and B. Follow. So if you said A1 times B1, that should be equal to A2 times B2. And this should look familiar, because with Boyle's law did say P inversely proportional to V. P is equal to K over V. P1 times V1 equal P2 times V2. We see it? We enlightened? We're good?
Yes,
We're good? We're good?
Yes, sir.
Right. So these are skills. The next thing now, last skill. Sometimes they'll tell you. So let's say I have a the best way to show this is an example. Force. Who can tell me the formula for the gravitational force? Call that Newton's fourth law. So force of attraction between bodies proportional to the
Equal to
product.
Gravitational constant times
Yeah.
the larger mass times the smaller mass divided by radius squared.
Excellent. You don't have to say like larger mass because eventually both of them are going to square times each other. So it's just a product of the masses. So two masses, if you have two masses, that the force that they exert on each other, what Newton realized, I call this Newton's fourth law. It's Newton's universal law of gravitation, aka new log. And they love to test this topic for paper one, by the way. Love it. So he said that the product of the masses is directly proportional to that force between the two of them. And it's inversely proportional to the square of the distance between them. That's called the inverse square law when you have an inverse distance to a value. So this is new log. So I'm using new log because I want to kill two birds with one stone. I want to show you my third trick. Think about it like that, tricks. It make it funner to think about. Let's say you get a scenario and I'm tell you, all right, and this is actually in the papers. Let's say them tell you say your radius has been halved and your mass has been doubled, and them ask you what's the new force. So maybe them give the first force and them ask you what's the new force, or what factor you would have to multiply the force by to get the new force. So here's the trick. What you're gonna do, you're gonna look at, you're gonna make the formula, because sometimes you need to know the formula to begin with. So you're gonna read the question and you're gonna realize, oh, this is a question about new log. I know the formula for new log, so I know see that formula. The next step, you're gonna be like, all right, I know the factors when I multiply by. So everywhere where them say me have a factor, I go put it in the formula. This is the most important. So R has been halved. So I'm gonna put half where R there and put it in the formula. So it's R squared, so it's half square. G, not never happened to G, so I'm gonna leave it as 1. It remains as the same. So it's multiplied by a factor of 1. Let's say M remain as the same as in the second M. Let's say the second M was the one where we double. And what I'm gonna do is you work out that now in the formula to see how it would affect the force. So it would be 2 divided by, when you square that, how much you get? Quarter though. How much you get when you square that? Yes, it's a quarter. So you would have said 2 divided by the quarter. And you realize you end up with 8. And you know what this is telling me? This is telling me that if I were to halve my radius and double my mass for a gravitational question, my gravitational force would be multiplied by a factor of 8. So if it was 10 initially, it's going to become 80 newtons. This is the trick. So remember this. Good?
Sir, could you go over what you did again, please?
All right, 3 steps. And yeah, usually in these questions, they're just going to tell us, oh, them double something or them half something or them whatever something. So the first step would be to identify the formula. Looking in the question, you're going to realize which formula you need to use. Cool. The next step, you're going to go over one side, you would write given information. Remember, whenever you start a question, you write given and you write given information. And you would realize them tell us that the radius half, the mass doubled. So you're going to put those factors inside the formula. So you're going to put 2 in the mass region and you're going to put half in the radius region. And then everything else will never get changed. You put 1 feet because it never changed. So it remained a factor of 1. Multiply by itself. Well, multiply by 1, remain itself. And then you're going to work out the formula with those factors. And you're going to see that is going to tell you how much the variable change. Easy. You good?
Yes, sir. Thank you.
That trick will take you straight up to unit 2. Right. I was about to say something. Alright, so that's good enough. That's good enough. Alright. So let's go back to the question. I asked you the same trick, you know. So I have to be able to identify when you need to use the trick. So airplane A is traveling with twice the speed of airplane B. Cool. Plane A is half the mass of airplane B. So in a question like this, given information, so I said, going from A to B, them say airplane A is twice the speed of airplane B, which means B, let me say, well, I come to write this, you know.
What did you say?
Repeat? Well, I come and write this, I'm gonna rewrite it. I'm just going to write the factor. So it's so plane A is half the mass of airplane B. So if we go from A to B, can you have a reference? How much you go, which factor you go up by or go down by? So we're look with respect to going from A to B. So going from A to B, what happened to the, what I'm telling you, the speed? Going from A to B, the speed is halved. You can see that? You see that?
Yeah.
So you see, you have to really think about it. So going from A to B, the speed has been halved because them say that the airplane B have twice the speed of A. Which means going from A to B, the speed has been halved. Because if this is 20 and this is 10, airplane here has twice the speed as airplane B. Speed has been halved going this way. So whatever it takes you for really, this is still 2007. As I said, the first year is just, first couple of years me helping you guys to go over the content. So that's why we're taking so long with the first couple of papers. But once we go over the content, it should take progressively faster. I'm prepared to see as long as you guys do, and the aim is to finish up to 2013 today. That's the plan. So let's see. Alright, so plane B. So plane A is half the mass of. So that means say you must double when you go there. Right. So you have to be careful, you have to can identify the factor. So what the next thing now? So now we see the factor. What them ask about? So we have to looking at the question. Airplane A has twice the kinetic energy as plane B. So because them say kinetic energy, you know which formula you have to think about. Half mv squared. And then you go plug in those variables. So you go say, so half now go change, so you go put 1 for half. Mass has been doubled. This has been half, and it's squaring. So that would be 2 times a quarter. And that would be what, a half? Right. So reading it now, we can say airplane A has twice the kinetic energy as airplane B. That's another way of saying that going from airplane A to airplane B, your kinetic energy has been halved. We good? So brain off of the palm body. We good?
Yes, sir.
Right. So once you remember the trick, you're good. So that now, an object is rotated in a vertical circle with no vertical circle. and him say with a constant angular velocity. What is angular velocity?
Omega.
Right? How we can calculate it with period?
Two pi over t.
2 pi over period. How we find it with frequency?
2 pi by frequency.
Right. So just what like checking. And the question now, which of the following quantities remain constant as the object moves around in a circular path? So let's read. The tension in the string. First of all, this is a horizontal this is a vertical circle, my bad. So what do you know about the tension? The tension is smallest up here, midway right here, and largest down here. So the tension is not constant throughout the entire circular path. So this is wrong. Right? And then I said the acceleration of the body. Now, remember that the acceleration is equal to v squared over r. As long as the v don't change and the r don't change, that acceleration going to be the same. The acceleration is v squared over r. They told us what them tell we. Omega squared is constant. The v is usually constant because it's just going to be r times omega. And you see say omega constant. So we can assume that the acceleration is constant. What about the kinetic energy? The kinetic energy will remain constant. Why? Because kinetic energy is unaffected by all of this madness. The reason being because the velocity remains constant. Since the velocity is constant, kinetic energy is constant because kinetic energy is half mv squared. And it's perpendicular to the centripetal force and things that would affect it. That make sense? That make sense? Yes,
Yeah.
feedback.
Can you repeat the kinetic energy part, sir, please?
Oh, so the kinetic energy is constant because the velocity is constant. The velocity is constant because it's perpendicular to the centripetal force. And the centripetal force, if you did have a force in this plane, the force would have caused acceleration, which would have caused change in velocity. But there is no force in this plane. That's why you end up with no acceleration and no change in that linear velocity. So that's why we say that the velocity here is constant. Therefore, kinetic energy remains constant. Because kinetic energy is half mv squared. So once you understand it, good. We're good?
Yes, sir.
Yes.
So let's push. Look at this lovely question. So when you see efficiency questions, you should be happy. Efficiency is basically looking at how well something work, which means say I go divide it. So if you look at how well something work, you are going to put in certain amount input. So this is all the time I'm going to explain efficiency, because easy. You put in something in it, and you want to see how much it can give you back from where you put in. It's like car. You put in the gas, you want to see how much mileage it can give back. Normally, when you put in, you have to use some of it for do random stuff. So you usually lose energy in the process of putting in. So you input in the engine and you got output, but you got lose some. So the efficiency is a measure of how much of that input is used. So in order to determine efficiency, you have to find out what fraction of that input has been used. Very practical. So if you want to find out how much of the input you use, you're going to say output over input. And you can even multiply it by 100 to put your efficiency in percentage. So output over input times 100. There is this question about a chocolate bar where the answer is 9. We're going to see it later down with efficiency. So it's output over input. You just look for the one will have that. Notice all of these others have some random business. Once you have output over input, even if it now have the 100, it's still efficiency it's representing. It's representing the fraction of input that was used as output. Good. So this now, which are the following experimental techniques reduces the systematic error of the quantity being investigated. So what is systematic error? Versus random error. I saw that it's the come on the exam.
The systematic errors produces constant errors, while the random errors produce are unpredictable.
Very good. Fair enough. So let's talk more on that. First with random error. You see, when you have a random error, what happens is that as the name suggests, there is some random environmental or external factor that is affecting the experiment so that you're not getting your true value. With a random error, you end up having variables that will be some amount greater or some amount less than the true value. So let's say I try to calculate acceleration due to gravity, 9.81. Random error due to you shaking the table, or maybe some happen like I don't remember anymore. But some external factor, or maybe you have experimental error, where you have parallax error, you read something wrong. Those external variables can affect how you take your measurements, and therefore you end up with a value that's greater than or less than the true value. That's a random error. And an association to make, random errors affect precision. So let's reason. Why? Because precision measures how close values are to each other. So when you check up gravity, you get 9.81, you get 9.815, you get 9.816, precise. But if you keep have random errors, your values are gonna always have something and push it away from each other. It now stay constant, it'll go all over the place. So random error is the bane to precision. RP, rest in peace. Random error affects precision. Just like how systematic error affects accuracy, which we'll see. Essay. So what is systematic error? Systematic error is a set error in the experiment or in the instruments. So it's something intrinsic that is wrong. So random error is more external, systematic error is more intrinsic. So when you have a systematic error, for example, something could be wrong with the measuring instrument. When you have, for instance, next year when you have the unit 2, the ammeter tends to have systematic error. It does 0 properly. So it's supposed to stop at 0, but nah, do that. Sometime our another systematic error. So that's a zeroing error. Zeroing error is very common for systematic error. Or let's say the experiment itself is flawed. You're supposed to do the experiment a particular way, but it's wrong. So you always are gonna get the reason why my friend said that it's a constant error is because if you have a set error, you always are gonna get that set error. So if your instrument is off by 0.5, you always are gonna have all your measurements them off by 0.5. So you have a constant error there. So linking it with accuracy, if it is that you always have this error due to the instrument or experiment that is affecting you from getting the true value, that means that you're preventing accuracy, because accuracy speaks about how close your values are to the true value. Make sense?
Yes, sir.
Right. So after that now, reading, systematic error, constant error, essay, accuracy is affected. So how do you fix a systematic error? You need to change the experiment or you change the instrument. So, and how you fix random error, let me ask.
So
You do it
fix it by retaking the measurements and finding the average.
exactly. Because if it's a case where you keep having it kind of bouncing around, what you need is an average. So that's what you do. You do multiple readings to find an average for a random error. Very good. But in a systematic error, you just change the instrument or change the experiment. So that's what we're doing here. We're adjusting a voltmeter. These instruments love random error, systematic error. So adjust it so that it don't have a 0 error anymore. Good. Say no. So all of these other things would have been trying to correct a random error. Once you see them, I say take multiple readings and I do average and then this and stuff. So we reach 15. What 15 mean? After 15, you reach into module 2. Right? So repeat question. Marcia needs to find the mass of her dog, and but he won't weigh himself on the bathroom scale. So what she does, she'll measure herself, she take her mass, and then she hold the dog and take her mass with the dog. So this is helping you to know uncertainty. So easy topic. I'll just show you in the textbook. And you have to remember it because it's an easy mark. So basically, we cover all the topics of module 1. So when we see module 1 questions, we get refreshed. Right. Systematic. This is where I want to be. All right, so here's this now. The whole idea of uncertainty or degree of uncertainty. What happens is that let's say I take a measurement 10 meters, but we know so instruments them flawed. So we're not gonna just take a 10-meter measurement and say, oh, that's a 10 minutes, so that's it. You want to give your measurement a room or a degree of uncertainty. So when you see them put 10 plus or minus 0.5 meters, what they're telling you actually is that this measurement that I've taken is 10 meters. However, in reality, that measurement is anywhere between less than 0.5 of 10 or more than 0.5 of 10. So it's a range between 9.95 and 10.5. That's what the plus or minus tells me. So degree of uncertainty is within that margin. So you're not just stay over 10, it's within that margin that my answer lies. And how you calculate degree of uncertainty, you have 3 different ways. You have absolute error, you have fractional error, and then you have percentage error. You have no R. Absolute error is when you're 2 ways. Is either you're going divide the smallest interval, and usually they give you the smallest interval. You just divide it by 2, or you so you is either you divide it by the smallest interval, or this other method is you're going subtract the determined value from the you're going to subtract the estimated value from the true value. So what this means is that you can, let's say the true values would be the measurements that you take. Kind of weird. But the estimated value would be the average measurement. This is usually used when you do a number of measurements. So if you take a number of measurements, you can say, all right, this measurement minus the average measurement. I'm gonna show you a scenario like that. So let's say you take a number of measurements. What you do for each measurement literally is say, all right, and this is what you should have done when you do your multiple readings in your lab. You'll determine the absolute error for each of them and then you add them up. So you just say your measurement minus the average, your measurement minus the average, and these would be your absolute errors. And then you're going to add them all up, ignoring the negative signs. And when you add them all up, that average that you get of all of these, that would represent the absolute error associated to the average measurement, because you take multiple readings to make an average. So now you're just finding the average absolute error. You still with me? We still with me?
Yes, sir.
Mm-hmm. Remember, tired is for the week. Let's not be weak for 2 days. All right, so we know that. So what about fractional error? As the name suggests, it's a fraction of the absolute. Well, it's a fraction. It represents what fraction of the true value or the measurement that you take is the absolute error. So it's the absolute error divided by the true value. What fraction of that true value is an error? That's what it's trying to say, the fractional error. What fraction of the true value is an error? Think about it like that. So you say the absolute error divided by the true value. Then a percentage error would be multiplying the fractional error times 100. Easy. The problem now, this is when you have one value. That's nice and good. But what happens when you have to have multiple values and then you have to calculate with multiple values? There's a repeat question where the answer is 14%. And that question is a density question. You have to know if you can multiply and divide. So if, let's say you have two measurements and you add them. So you measure 2.2 plus or minus this, so you add an error to it, and you have 3.4 plus or minus this. If you want to add these two variables, how you do it? You're going to add numbers first. So 2.2 plus 3.4, because that's the actual measurement, you get 5.6. Plus or minus, and what you must do is add the errors. Why? Because each measurement is coming with an error. So you have to factor the overall error. You add the errors. If you're subtracting, you're going to say, all right, subtract the main values. So this would have been negative something. But you're still going to add the errors. You're still going to add the errors. Why? Because both measurements are coming with their errors. So that's something to remember. We're good? Drink the water. We're good?
Yes, sir.
Sir, could you repeat the last part, please?
I was saying that when you have adding or subtracting, you have to so you do what you're doing with the true value, but you have to add the errors, no matter if you're adding or subtracting, because both measurements come with an error. If you take that measurement here with a microscope gauge and this with a vernier caliper, both of them two instruments, they have an error. So you have to add up the errors then. You add the errors. Always add errors. Make sense?
Yes, sir.
So what about multiplying and dividing, which is what you do most of the time? Easy. So you get these two values again, and they want you to multiply them. So the first step, you multiply the two values. So this times this, you get about 7.5, I think. But you want to know what going to be the error for both of them when they multiply. That's the question. So what's going to be the error? How am I going to get that? Easy. What you're going to do is find the fractional error for both measurements. Follow this. This is something that asks. Find the fractional error for both measurements. And once you find the fractional error for both measurements by saying, all right, so you have this, you divide this by this, and you divide this by this, fractional error for both of them. You're going to add the fractional errors for both of them so that you can get the total fractional error. So you see, once you have the total fractional error, remember the goal is to find the absolute error. So how can I use fractional error to find absolute error? I know that fractional error is equal to absolute error divided by the true value. And I just calculated the true value. So absolute error would be equal to fractional error times that true value. And yes, this is what you have to do in the exam. And then once you do that, you're going to get the absolute error. And you can say the true value plus or minus the absolute error. We're good?
Yes, sir.
There's a MCQ with repeats 14%. Is a density question. And it's this that you have to do. Oh, speaking of that,
Mass in the lead cube, right?
yeah.
Yeah.
And yes. So you realize you have to remember it. And there's another question similar to it as well. Pre this though. Let's say I have something raised to a power. So this raised to a power plus or minus the arrow. When it's kind of like logs. Yes, when it raised to a power, you just bring it in front to multiply the arrow. So whenever something is raised to a power, the arrow is going to be the absolute arrow times the power that it was raised by. This is, you see that same density question that we're talking? Remember, say volume is L cube. So if you had the volume, I think it was, I don't want to remember that, but it was something like this, plus or minus 0.1. If you want to find the, so this is the length. This was the length. If you want to find the volume, which would be L cube, you're going to say plus or minus, and the raise it by, I'm going to multiply the arrow. And this is exactly what happened in that question. Say you had the length and you cube it so that you could get the volume, but you have to remember that you have to multiply the arrow by 3 because that's the rule. Cool. And that is arrows. All right, so this question, this is a easier one. This is an addition one. So remember how we did learn about addition. So no, as a matter of fact, this is not addition because what she wanted is find the mass of the dog. So she get fewer mass with the dog and then she get her mass by herself. So she want to subtract her that from that. So the subtraction thing. So first you'd subtract 47 from this. What will I find? The fractional error? Oh, percentage error. Okay, cool. So now I jumped the gun. How would you do it? So me ask.
Add the absolute error and find the true mass of the dog, which would be 64 minus 47.
Why are you doing that though? Come on here, formulas in terms of how you get to your conclusion. So let me show you what me I think. The answer is supposed to be done here, but let me show you what me I think. What is so how you navigate questions in general? Look what them are asking for. Look at the given information, then see if you get what you need. You can answer. So them asking for the percentage error. So I know that percentage error is equal to fractional error times 100. So what I need to do is find the fractional error of both of these put together. So what I try to find from these readings, the percentage error in the mass of the dog. Let's not be careful. Yeah. So I just want to find the total fractional error and then multiply it by 100. So how am I going to do that? I'm going to say, all right, first find the fractional error for by ourselves. I don't know if I'm making a mistake. How much should I get with that? I feel like I'm making a mistake. I can always check this up list too. I have the answer somewhere over there. Yeah, I'm making a mistake somewhere. So let me figure out why. Oh, you're right, you know. That's what I say as well. You do it first, then you do what I talk about. As in, find the mass of the dog first, and then find the fractional error from that, and then find the percentage error. So how would you find the mass of the dog? You have to subtract. So you're saying 65 minus 47 plus or minus 1 plus 1. And that would give you, what would that value be? 65 minus 47.
17.
Good, thanks. And it's a plus or minus 2. And this would be the mass of the dog in kilograms. No more find the fractional error of the dog as you rightfully did say. Find the fractional error of the dog, you're gonna say 2 divided by 17. Because this time absolute error and this time mass, so our true value. So 2 divided by 17. And I got 0 0.12 roughly. And then you can say the percentage error, you just multiply that by 100, you get 12%. Makes sense. So you see how we have to reason out even with the simplest questions. So you have to carry your knowledge in the exam. But if you go through all of the questions, it will be easy. All right, so we did that. Good. So we reached module 2. So I have to recap a bit on module 2 as we go along, but it shouldn't be as long. Which of the following cannot be demonstrated in sound waves? We know that polarization talks about looking at the plane at which the wave is oscillating. So quick recap on that. Just I got right here. Remember, you have 2 types of waves, transverse and longitudinal. A transverse wave has, what is a wave first? Quick definition. Wave is the transmission of or propagation of energy through a medium, which results in the oscillation of that medium relative to the direction of the wave or wave motion. So what may I say? When you have a wave, energy is being propagated. So it's the propagation of energy, and the energy usually go forward. And that propagation of energy is occurring through a medium, unless you're talking about EMR, which passes through a vacuum. Usually it passes in a medium, like solid and water. So it's propagation of energy through a medium, which results in the oscillation of that medium relative to the wave motion. The wave motion is another word for the direction of the propagation of the energy. Am I making sense? Please make note of these things. Can be the difference between that 1 mark. We could have get to the 1. We good? All right, so now move. So transverse waves, the oscillation is perpendicular to the wave motion, which is, I said, is the propagation of energy in the wave. But with a longitudinal wave, they occur in the same plane. The oscillation is in the same plane. So you end up with rarefactions and compressions. And the whole idea behind polarization is that when you do a transverse wave in particular, like for instance EMR or light wave is EMR. Most waves are transverse waves. What happens is that because they're perpendicular to the wave motion, you see that oscillation, it can go in any plane perpendicular to the wave motion. So follow me. It could even go this way, as long as it's perpendicular to it, or it could go this way, as long as it's perpendicular to it. So the idea behind polarization is that it tracks the plane in which the oscillation occurs relative to the wave motion. That's exactly it. It tracks the plane in which the oscillation occurs relative to the wave motion, which means if a wave is going to be polarized, it needs to have an oscillation that's perpendicular to the wave motion. Therefore, sound waves cannot be polarized. And this is a way to differentiate sound waves from transverse waves. Because sound waves are longitudinal, transverse waves are, yeah. Right. This now, which of the following gives the correct relationship between intensity and amplitude? Who can tell me this? We're going to sub molecule for this. Brief. Relationship between intensity and amplitude. Come guys. Module 2 is right there.
Intensity is directly proportional to the square of the amplitude.
Very good. Do you know the relationship between amplitude and energy in a wave? Just to recap simple harmonic motion as well.
Amplitude is directly proportional to the energy given out.
Very, very good. Well, as a wave oscillates in simple harmonic motion, you're gonna realize if it have more energy in it, its amplitude are greater. And amplitude we say, so let's connect those variables. Amplitude is proportional to energy. And we said that the intensity is proportional to amplitude squared. And what is intensity? Intensity is equal to the amount of power exerted by a wave per unit area. So it's measured in watts per meter square. Power. So when an earthquake have intensity to exert enough power over the area. Earthquake. And what I want to say is that the intensity proportional to area, right? So I was about to say, you realize amplitude is proportional to energy. And this is the reasoning behind the different types of waves. When you talk about, say you have 3 types of waves. So in module 2 now, so I have to drop in module 2 stuff. 3 types of waves. You have free oscillation, you have damped oscillation, and then you have forced oscillation, aka resonance. Who can tell me the difference? Who will get the one in our physics? All of us. Who can tell me? All right, so may I quick recap then. All right. Capri. In a free oscillation, the body has no loss in its energy. Therefore, the amplitude is conserved. The reason why there is no loss in energy is because there's no friction to counter it so that it loses energy. So in a free oscillation, there's no loss in energy, amplitude is conserved. That is what we assume that we're doing in the lab when you see the pendulum go back and forth, because we assume say the amplitude constant. That's why we had all of them formula there with amplitude in it, assuming that it's constant. But when you have a damped oscillation, this is real life stuff. Amplitude actually decrease because energy decrease, because you have friction in a real life. And you have different types of damping. You have oh, it go again. You have the one where very slow. Do you remember what it's called? Then you have critical damping, which is when it oscillates one time and then stop. And the thing about critical damping, it's useful because sometimes you don't want things to oscillate. For instance, cars, you don't want suspension in cars to oscillate too much, or the car going shake, shake, shake. And bridges, you don't want bridges to oscillate a lot. So there was a question where they asked when is damping useful? The answer for when is damping not useful? And the answer for that was the pendulum clock. Because the pendulum clock needs to resonate so that it can go back and forth. But the other examples were like things where damping actually needs to do, like reduce vibration. We still in it?
Yes, sir.
I know if I start talking too much, I'm going to put people to sleep. That's why I keep asking if you're still with me, guys. So feedback is great, you know? Just make sure so we're following, yeah?
Sir, under damping is one for the
yes, under damp is one of them. And what the first one name again? Light damp, lightly damped. Lightly damped is what usually happens for a pendulum, where it slowly decrease over time. The amplitude slowly decrease over time. Then you have critical damp where it just decrease after one go.
Excuse me, sir. Is lightly damped the same as under damped?
No, cause the lightly damped looks something like, let's go to it, yeah. Module 2. Personally, you don't have to know much about the differences between damping, but let's see. So you have lightly damp. Lightly damp is like, because as you go up, what is changing is the amount of friction. More friction as you get more damped. So lightly damped is the least friction, so it has a gradual decrease in energy because you have a little amount of friction to counter it out. And this is like a pendulum. Pendulums undergo a light damp. So if you swing a pendulum and you lower it, you're gonna see that it gradually reach to equilibrium because it will gradually decrease its amplitude. Right? But then a heavy damp now, heavy damp would be like what is gonna so a heavy damp now is like you oscillate it, but it never, as in you initiated the oscillation, but it doesn't even go back and forth about the equilibrium position, because that's how oscillation works. It doesn't do that. It just take time, and so it's like you push it to the amplitude, but it just gradually go back to equilibrium. An example of this is the toilet, actually, because when you pull that knob, you realize it gradually go down back. So it's like you displaced it to an amplitude and it just gradually goes back to the equilibrium. So that's a heavy damp situation. And then critical damp is more common. That's when you only oscillate once. A good example is with cars, the suspension system in the cars, so that the car don't bounce all over. And then the overdamping, I've never really went into it too much. I don't have an example. Underdamp, was there such a thing? Probably in the study guide. But the more damp is, the more likely it is to stop oscillating. That's how we meant it. Right, so we're going through a lot of content. All right, and then the resonance, very important. We said that in resonance, so notice in free oscillation, energy is conserved. In damped oscillation, energy is lost. In resonance, you're going to see that the energy is gained and the amplitude increases. Why? Because what we do to this person in resonance, we apply an external force which has a frequency that is equal or equivalent to the frequency of the oscillating system. So it's like somebody on the swing and they apply an external force with a frequency that coincides with the frequency of the system. So once the frequencies are similar to each other, energy can be transferred from that external force into the system so that you can increase its amplitude. Making sense? All good?
Yes, sir.
All right, easy. So we just done all of the oscillation types. That's one of the first topics in module 2. This, we know this.
Excuse me, sir.
Mm-hmm.
What was that about intensity direct proportional to 1/r radius squared?
That no, I never want to go into that right now, but let's do it.
I see.
So what means that there are two formulas in regards to intensity. And guess why this is a easy for you? Because you know the proportionality trick. So that means that intensity is directly proportional to amplitude square. And then intensity is inversely proportional. No, come up back. Right. I have met this disappear in a cause it's a cause problem. But I'm gonna share about my screen. Right. So carry this up in a corner and then hide this. Right. Okay, that doesn't work. All right, fine. So I'm gonna say now, intensity is proportional to amplitude square, but then you also have intensity being inversely proportional to the distance from the source of that wave. So this is another version of the inverse square law, where one thing is inversely proportional to the square of some distance, just like in Newton's universal law of gravitation. So I want to show you for this is that remember how you treat proportionality. I, and this is used in the paper ones, is equal to a proportional constant times a square. Therefore, I1, so if you bring that down, A1 squared, that would be equal to K. So I2 over A2 square also equal to K. So you can make an equation and you can pretty this up further to say, all right, let's say I1 over I2. Just make everything homogeneous. I1 over I2 equal what now? So I carry this down and then I'm going to carry this up. A1 over A2. What I like to do for this formula, I like to just put all this in square to make it easier to the eye. Unless I try transpose one of them. Good? We okay? Good?
Yeah.
Right, so you see everything connect. A lot of this come up in paper too. So you have to put that square up at the top, not the bottom. So this, and then you're gonna have, so you see I'm doing the same thing over here. I2, E2. So as I said, this is a skill you just pick up once you practice. Put 2 here now. Be careful with the numbering. Right? And then you can pretty it up. You can say I1 over I2 is equal to, you end up with D2 over D1. And then all of that square. And it just clearly shows that it's inverse. Okay, you realize the I, them inverse with each other. And the two, them inverse with each other. Versus over here, everything they direct, everything they link up. So very important. All right, so I'm gonna go to now is the question. All right, displacement time graph and a displacement distance graph. The difference when you have a displacement time graph, so remember if you're looking at one complete cycle, you have to go from starting point to the max, go back to equilibrium, go to the opposite max, and then go back to equilibrium, are 2 consecutive points on our wave. So when it did, yeah, look for the part when it did just about to come out from the 0, and then see it when it just come out from the 0 again. Yeah, so it never come out on a 0, they're going at the 0. So when it come out of the 0 and it come out of the 0, 2 consecutive points. This is a complete cycle. And with a displacement time graph, you can determine the period because time is on the x-axis. So the time for a complete cycle is a period. For a displacement distance graph, you can determine wavelength because as the name suggests, the distance for a complete cycle is a wavelength. So to add to that, remember the wave equation. So you said distance over time. If the total distance is the wavelength and the total time is a period, and then if 1 over period is the same as frequency, wave speed is equal to wavelength times frequency, which is the first equation you should be thinking of whenever you think waves. Like once you see a wave, you should be thinking wave equation. Give me a second. All right, so what next? This. So what they ask you for the wave speed. Another way to calculate wave speed, aside from using this formula, is by just saying distance over time. So you can say this distance over this time, because this would be 10 and then divide by 20, you get the wave speed of 0.5 meters per second. So make sure you remember that. I forgot about this mnemonic. All right, so look at this now. Boy, we're gonna go into a little story. But you understand the story now and later. So who know all of the formulas them for refraction? So start list out some refraction formulas. Yeah. I'm clear my throat. When you hear refraction, which formulas?
N1 sine theta is equal to N2 sine theta 2.
That is one for real, right?
Then you have the refractive index is equal to B over C, B being this the speed in a different
I think
medium.
it's the other way around, you know.
Other way around.
Unless I'm wrong.
I think when it's for air, wave speed on the top, but I'm not wave speed at the bottom. I'm not sure. Actually no, I'm not sure about that equation.
It's a good equation because what it say, it's saying that the speed from the initial medium into the speed of the next medium is equal to the refractive index. The initial medium, I think, is the vacuum, so it's C over V, but we're going to see it, right? Good. But the first equation you should have told me is Snell's law.
Over sine R.
You want to remember? So you have to remember Snell's law first. So I'm gonna see if remember them in order, because order helps sometimes. So first thing, refraction is what? When you talk about refraction, you're talking about the bending of light when it travels from one medium to another. Bending of light, one medium to another. I'm not writing that. Bending of light when it travels from one medium to another due to changes in density. Because what happens is that when you go from a medium that's, for instance, with light in particular, because not just light refract, but light, for example, I'm going to show you differences. Light, for example, light is most popular. Light have a thing where it's bothered by density. Because when you talk about the speed of light, so I'm going to say the definition again soon. But when you talk about light and the speed of light is inversely proportional to the density of a medium. Why? Because light travels by photons and it needs space so that the photons can flow. Vice versa, sound, opposite. Speed of sound actually increases the more denser object because sound travels by vibration, not photons, vibrations, which means that the more dense is the more vibrating. So that's why speed of sound is faster in liquid versus solid. The speed of sound in water is about 340 meters per second. And then in a solid is about 1000 odd. Remember these from experience. And then light, you realize light is fastest in a vacuum because vacuum is the least dense. 3.0 times 10 to the 8 meters per second. So going back to refraction. Refraction is the bending of light or bending of a wave as it passes from one medium to another due to changes in the density of the medium. Because the density affects the speed of the wave. And the speed, once the speed changes, the wave will go bend. So I'm going to say that again. Wave bend due to changes in density because density affects speed. And once you affect the speed, you see bending. Why is that the case? Well, I go pick on light. You see, when light, for instance, I go from a less dense medium to a more dense medium, I have to keep in mind the normal, always keep in mind the normal relative to the normal. So let's say this was air. So you're going from as we get the formulas, I just want to get the rough up. The less dense, and then this is glass. What's the refractive index of glass? Let me ask. I know you guys probably did the lab on it, so that's why I asked. So the refractive index of glass is about 1.45, especially if it's that tough glass, so them always, 1.45. We're going to talk about it. And water is about 1.33 repetition. So we try to understand the basis of refraction. We said that speed affects bending. Why does it affect bending? Because imagine you have light coming at a particular speed. But you know what, when it hits you so, this more dense. So it can start move at a slower speed. And so because it start move at a slower speed, it start pulling to the normal. Imagine like there's a video by Boltzmann physics. Him show it like soldiers. Them walking in a straight line at an angle here. And when them going at the more dense medium like a sand, like them a walk from solid land to sand, because the sun are holding back, them kind of pulling into the normal. And that perfect to understand analogy wise, coming from air to salt to a more dense medium. More dense, you're slower, so you pull to the normal. Basically, even if you don't remember that, there's a mnemonic. Fast. You want it fast? Because F stands for forward, I think. Yeah. F stands for forward. No. No. F stands for faster. And then this is away. So what I mean by this? If a wave gets faster when it go into the next medium, it go and move away from the normal. So that would be, for example, if we look at the opposite, going from glass to air, more dense to less dense, air go be less dense, so the air go make light move faster. When you go from a medium will make you slower to a medium will make you faster, you're gonna move away from the normal. So faster, you go away. If you get slower, you go towards. You guys good with this? Good with this?
Yes, sir.
Yes, sir.
Very good.
Sir.
All right.
Sir.
Question?
What about lambda 1 over lambda 2
Remember,
equals refractive index?
When I start share the formulas, them yet, that's the thing. I'm gonna make another page with the formulas, them, but I just want to understand what refraction is. So we define refraction. I would say refraction is a bending of light due to changes in density, which results in changes in speed of the wave. And then we just appreciate why speed affects the bending of light or bending of waves in general. Because once it's faster, it'll move away from the normal because it'll get easier for move now, so it can move away from the normal. And when it's slower, it can move towards the normal. So now we can put in the formulas. So the lambda 1 over lambda 2 is a formula because that's a version of Snell's law. So formulas, the first formula you should think about. So you have to have try to have these formulas in your back pocket. There's a couple of them. So the first formula must be Snell's. Must be Snell's. Snell's law actually is a big formula because it tells you that so Snell looks at changing from the first medium to the second medium. And it looks at it in 3 parameters. First, it'll go look at it in terms of the angle. Sine I, so it's incident angle, over the refracted angle. Reason is, if the angle is larger initially than when it came out, that means that it come from a medium where it was further away from the normal, hence you had a larger angle, to a medium where it got to a closer point to the normal, so it had a smaller angle. If the angle is decreasing when it got to the next medium, you can see that N increase. And more importantly, if the angle is decreasing when it got to the next medium, it is telling you that the wave is getting slower. So slower, it's pulling towards the normal. So the greater N is the greater the ability of the wave, the ability of the medium to bend light. So when you have a high N value, it bend light a lot, because if N high, it means so when you're going to the next medium, your refracted value is well low in comparison to the initial angle. We good? We good? We're not tired yet. We good?
Sir, could you
good?
just repeat that, please?
Right. So I'm saying that, and this is useful because you can use it for pretty questions. When n is high, when you have a big n, first of all, look at n. N is sine I over sine r, which means that if you have a big n, it means the initial angle was big. So looking back at the wave, medium 1, medium 2. If the initial angle is bigger than the final angle, what it tells you is that the wave pulled towards the normal, which means it got slower, which means it bend the wave a lot. So n is larger when you have a wave that is bent more, meaning you have a more dense medium. You went into a very dense medium that bent the wave to the normal. So you have to connect the dots. Bending to the normal correspond to slower wave, which correspond to more dense medium. Because more dense medium make it slower so that it can bend to the normal. I remember fast. And what I said was that n, they like to use the refractive index as a measure of the bending ability of our medium for light, how well it bends light or refracts light. For example, diamond has a refractive index of about 3 point something. It's big. And because diamond has such a big refractive index, the light just bend up inside a diamond. And because of that, it sparkles. Also because diamond undergoes total internal reflection. So it allows light to be trapped inside it. So good?
Yes, sir.
Very good. Drink water. So this is not the only Snell's formula. Can also represent it in terms of speed. The speed it has initially over the speed it has in the next medium. If it did faster before it going on the new medium, that means when it going on the new medium, it gets slower, which suggests that it's going towards the normal. And you know the mnemonic, so it makes sense. It's all following suit. And then the last one, lambda. Lambda 1 over lambda 2. What we should appreciate is that wavelength and lambda is directly proportional. How we know that? Because wave speed, I'm not sure I say wave speed and lambda is directly proportional. Why? Because look at the formula. V equal F lambda. When you increase the speed, you increase the wavelength. And that means it get bigger. So if your speed was 10 meters per second, the wavelength was 20 meters, and you increase it to 20 meters per second, now your wavelength are gonna be like 40 meters. You get bigger. So they're directly related to each other. Right. So these three formulas, and how you know if you use them? Let's say them give the refractive index and you have the angle, and them ask you to find the reflected angle. You know, say this one if you use. Or let's say them give the refractive index, them give I rather, and them give R, and them give one of the V, them and them ask you for the other V. You know, you can relate these two equations together. So you know, once you have all of this, you're good. So there's other formulas like, I'm just going to go to the book for the rest of them. Almost there. Once we finish the first one, we should have a lot less talking to do. In terms of recap. So I use this. Going all the way down this up. Hopefully we can take a break about 8 o'clock the latest. Where am I? All right. All right, there's a formula. And then you have this other formula, N1 sine law over N2 sine law. Useful formula. If you give it, like, let's say I come from one medium, here has a refractive index of about 1. What that tells me is that the medium not change nothing about it. The speed it did have before, the speed after, the angle before, the angle after. That's why when you're looking in air, you don't see light bending up in the air like that. Vision is not impeded by air, because air is not a natural refractory medium. So, but let's say them the gear 2 medium with them refractive index, and then them access to angles. These are the formula to use. This formula, see, I don't know, say it was this not. Why? Because it's the initial velocity over the final velocity. Initially coming from a vacuum, and then what the velocity would be in a medium. Good? Good? I get hungry. We'll soon take a break. Let's try to finish the paper. But as I say, as soon as we finish this paper, we should have a lot less to be explaining. Because we would have touched all of the topics. That was the aim of doing that. All right, so that formula now. Remember this formula, very important. And they have this concept of total internal reflection. When you have total internal reflection, what happens is that the light is coming from a more dense medium to a less dense medium. And what happens is that if you're doing that, you're going to pull away from the normal. Cool. Now, there is a certain angle called the critical angle. And that critical angle I has the ability to produce a refracted angle that is equal to 90 degrees from the normal. So what is the critical angle? It's the angle that produces a refracted angle of 90 degrees. And there's a phenomenon called the total internal reflection, where if somebody were to surpass that critical angle, so incident, anything greater than that, looking at where we go, we are trying to go away, you know? Once we reach here, so which part we are going to go more? We are going inside of the glass and end up reflect inside the glass. So this is called total internal reflection. I always think about fish. Sometimes when we see the fish right here, so I over here saying that, or vice versa, because there's a total internal reflection of the image that we're seeing. Because it's coming, the light from the fish is coming out of the water, and then it probably will come out at an angle greater than the critical angle, and then gets reflected back in. So you see the fish over here, so name the over here. So there's actually a lab where you're supposed to plan that and make sure so you can catch the fish properly with the whole idea of reflection. Following me?
Yes.
Following me? Good. So what is the critical angle? We're good? As I said, guys, we're going to get the bulk of the work out of the way today. So as long as you're willing to stay with me, we'll go through. Tomorrow we not gonna have as much in terms of topic wise. The big thing is trying to get the the repeat questions out of the way. Wait, I'm looking at a message. Give me a second. This is also why I created the group chat, because if we're not very fast when it comes to the recordings itself, I can also answer questions for you guys in the group chat. So try to join the group chat and I can always try to answer questions, but at the end of it, we will finish these questions one way or the other. All right, so let me come back. Right. Look at this prism. What them do to this thingy here? 'Cause I think there's a MCQ for this. I'm not sure. Imagine, all right, so this is the normal. This is the normal, right? When they send it in at an angle of 45 degrees, the medium have a critical angle that is smaller than the 45 degree. So once you have a critical angle, once you have an angle that's greater than the critical angle we expect, it will just drop back right in. And then it's the same logic here. That angle greater than the critical angle, that 45 degrees where it's an incidence with now, greater than the critical angle. So it's going to just go right back inside. And that's how it go right in your eye. And they use the same logic for optical fibers and endoscopes. I think this is the last refraction formula. Very important. Critical angle. How you find critical angle? Sine C equal 1 over n. I wish I had a mnemonic. Yeah, it is what it is. Maybe Singer. Yeah. All right, move. Let's go. Let's go. So we're going through all of the refraction formulas. So this question. For light passing from air to material X, the refractive index is 1.3. And for light passing from air to material Y, it's 1.5. Which of the following shows the speed of the light in air, X, and Y in descending order of magnitude? So they want you to show descending order. What I mean, what again? Decreasing, right? Yeah, fastest to slowest is right there, Jeremiah. So what we remember, if the refractive index is greater, the speed that it's traveling out with, you can have a look at the formula VI over V2. You realize that it's going to be inversely related to the speed that it's going to come out with. So the greater the refractive index, the slower the wave, and it's going to pull closer to the normal. So air was the one with the smallest refractive index, then X, then Y. All of that for answer our question. All right, we're good? I'll take a 5 minutes. We're good?
Sir, good. Can I see the answer for the question again, please?
Yeah, man. Because that next thing that I'm about to show you is very important, interference. A lot of questions come for interference. Like literally every single year, there's an interference question. And there's just 2 formulas for it, so you just work out. All right, so I'm going to take 5 minutes and come back. Can you hear me? It's the most Jamaican 5 minutes I ever taken in my life. I have to do something quick. Can you hear me? We're back.
Yes, sir.
Mm. Consider that the break. Mm-hmm. All right, we'll come in again. Okay, let me just. All right, come in. So that topic I know is interference. It's a bit hot. All right, so interference. I'm going to go into the deep nitty-gritty because we don't need that for the paper one. just understand, say, I'll show you the basics of it on the whiteboard, formula wise. So just understand that you have these phenomena, right? So how we prove that a wave is a wave is if it obeys different phenomena. What I mean by phenomena? It have to undergo refraction, reflection, diffraction, and all of them weird sounding words. And one of the things was that light itself, there was a period in history when we didn't know if light was a wave, because there was the wave particle duality theory, which stated that light was both a particle and a wave, but then observation affected that. So what happened is that Young eventually found a way to prove that light was a wave, and he did it using the double slit experiment. So I'm going to show you how the double slit experiment works, and then I'm going to show you how the upgraded version of it works, which is the diffraction grating thing. So it's two formulas really, Yard, and there's this other one, right? But it's kind of important ish to know how Young's work, so I'm going to draw it for you. We're good? Will you hear me? Will you hear me?
Yes, sir.
Right, so I'm just showing you the drawing and then show you the formula, and then we'll use them as we go along. So how Young's double slit work, he wanted to prove that light was a wave. And in order to do that, he needed to show that light undergo one of the phenomena of a wave. The one that he was able to prove was that light undergoed interference. And what is interference? Interference is when waves meet and they are coherent, meaning they meet in phase with each other, or meet in phase and they have similar frequency and amplitude, and they tend to create constructive interference where the amplitude will summate, or you have destructive interference when the amplitudes will cancel out. So he was able to show that on double slit using bright fringes and dark fringes, thus proving the wave duality theory. So how he did it, he said, all right, now I get a light, just a shine light, and him shine the light through this small hole. But guess what happened? This as well is proving that light is a wave, But when him shine it through the light hole, the small hole, the light diffract. What is diffraction? Diffraction is the bending of light as it passes through an edge or a gap. When the edge has a hole that is similar to the wavelength of that wave, the diffraction is going to be greater. That's why sound waves easily diffract and spread across corners and all that stuff, because sound waves have relatively large wavelengths. So their wavelength is similar to the edges that they pass through, so they can diffract and spread. But light wave has a very small wavelength. And because of that, light doesn't diffract easily. So you can't look around the corner. You can't just look and see around a wall going on a corner, because the light now go at the wall and then diffract around it. Its wavelength too small for that. But sound wave can. But when Young created this very small slit, he was able to show that the light could diffract. So it passed through area S1 and area S2, and it started diffracting out of two holes. That's why it's a double slit. And when it diffract, because both waves are from the same source, they are considered coherent. So when you have two coherent waves meeting with similar amplitude and all of that stuff, you end up with interference. And what he realized was that in some places, the interference was constructive, which generally means that, so I'm going to tell you some key things where them love to ask about that. So you're going to see constructive interference as the white fringe and then destructive as the dark fringe. So you know that already. But like, I'm going to add something mathematically to it. You see, constructive interference is represented with what you call that again? A phase difference of n times lambda. So what do I mean by that? Is it phase difference or part difference? I think it's a part difference. So I might have to share the part difference. So there's this whole thing about path difference as well. So just bear with me. You should remember this from paper one. So it's just a recap. Paper two. Just giving you the bare essentials. Let's say the light them are going to meet right here, so right? You realize that the distance what this light travel to reach here is shorter than the distance the light travel to reach. The second light travel to reach. That is a thing. That separation between them is actually called the path difference. Path difference. Path difference. Because when you calculate that, that's the space between both of them going to the point where they're supposed to go. Path difference. And important to note is that when you have constructive interference, the path difference is a whole number of a wavelength between each other. So when you have, when you have the first bright fringe, that would correspond to 0. That would be 0, the end would be 0 wavelengths. When you have the, sorry, let me use the numbers properly. When you have the 0th bright fringe, that's what happened with the 0. When you have the first bright fringe, the end becomes 1. And you see it come up by a factor of a wavelength. But when you have the destructive interference now, which fall on the black spots, they are going to interfere, and this is something they love to ask. The destructive interference has a path difference that is a whole number and a half of a wavelength separating. That represents destructive interference, which would correspond to being 180 degrees out of phase, which is pi out of phase. May that make sense? That makes sense? With me? With me? We're not top out. With me?
Sir, you can go over that one more time, please.
All right, so the key takeaways. This light source, they love to call it a monochromatic because it's usually one type of color go through, like yellow light, for example. I remember Roy G. Biv. Roy being 700 nanometers, blue being about 400 nanometers. I think somebody call me. Malcolm, give me a second. Give me a second. I'm gonna check. All right, back. So I was saying, that Roy G. Biv thing can actually be used. So that's why I remember those values. There are a couple questions with them. Yeah, what you need to remember is that B is on the higher part of the spectrum in terms of frequency. Therefore, it have a lower wavelength. So it's a high frequency. Blue, that's why them talk about blue light in our eye, because blue light have a high energy, high frequency, but low wavelength. So from chemistry, that might make sense. But then red is kind of like a lower frequency, but a higher wavelength, because frequency and wavelength inversely related. So blue light is about 400 nanometers. So I just dropping this in, and this is 700 nanometers. So what was I saying now? I was saying that when the light passes through the first slit, it going to pass through the second system after diffracting, and that those are going to meet. And since these two light sources are the same, because it's coming from the same monochromatic light source, mono, one, chromatic color, when them interfere, you're going to have streaks of constructive and destructive interference. So you're going to have one big white center, which is the central fringe, and then you're going to have one. So it's supposed to look like this. So it counts on both sides. And we're counting the white spaces. And then in between the white spaces, you have the destructive interferences. So what I was saying is that the path difference is the distance between the two waves as they travel to meet their point. So this coming from there, this coming from there, there's a small space between them going up to this point. If you were to measure it, the line is longer. So that difference between them is a part difference. I was saying that if you're gonna have constructive interference, when you hit here, it needs to be a whole number of a wavelength separating them. So if it's the first bright fringe, n going to be 1 of a wavelength. Second bright fringe, n going to be 2 of a wavelength. But you see with the destructive interferences, remember say destructive, they're right beside the constructive. So it's a whole number plus a half of a wavelength. And that represents out of phase. That's why you have a destructive interference. So if it's the first fringe, you would have 1.5, and that would correspond to the first dark fringe. Make sense?
Yes, sir.
Right. And then the only other thing I'll tell you is the formula, your yard formula, remember? So how yard work is, this is fringe space. Y is for the fringe space. And then you have A. A is for the slit space. I think so. And then the lambda is for the wavelength, and then these for the distance from the double slit to the screen. So fringe space, the slit spacing, wavelength, the distance from the screen, and this is yard. This is the formula for Young's double slit. And then you have diffraction grating over here, which is an easier formula. Well, easier formula. It's A. So it's A sine theta times n times lambda equal n times lambda. How them get this? What them do, them end up take one piece of glass and then slice it up to make very small holes. And that's, they shine the light through the small holes, and that would basically do what this is doing, but at a larger scale. So it's better at getting results. And the formula that they got from it was A sine theta equal n times lambda. Very good. And key things with this is that you have something called the line spacing. Because what happens is that, so pay attention to this. What we do, we make one bag of small hole. And in terms of that, so I don't want to mix it up.
Sir, what did you say the A was?
Oh, the A is the slit space, so the distance between the different opens. And then F would be the fringe space. Trying to remember something important. Oh boy, I have to go back to the book. All right, so I think this is it. The thing where they love to ask about for this. So that should be it, right? So here's the trick with this. You think say the formula is that and that's just it, but there's a slight problem. When them do this instrument, them will, it's like a one bag of hose, right? So what they actually do, they imagine it come labeled with the number of lines, aka slits, per millimeter. So these come labeled with the amount of openings or lines it have per millimeter. Lines per millimeter, you see them call it. Let's say I have a lines per millimeter of 560 lines per millimeter. So this actually will convert. So let's say I want to get it in lines per meter. If you were actually to work that down, it would work out to be multiplied by 1,000. This is something I want you to just remember. Don't worry about working it out. If you're converting lines per millimeter to lines per meter, multiply by 1,000. Remember that. Because most of the time, they will gear these and then say, oh, it have 560 lines per millimeter. And then you can use that information now. Because guess what? You see, when you find out how much it be in lines per meter, so let's say it's about 2.0 times 10 to the 6 lines per meter. Watch this. If you know how many lines per meter, how many spaces per meter on this diffraction grating, if you were to inverse that, what you'd get is the distance per line. which is the same as the space between the slits, aka A. If you say 1 over D, D being the lines per meter, what you get is the meters per line, and that would give you the spaces between the slits. Make sense? Make sense? Very important. You get one of these questions for every paper. Literally, every single paper you have to can get comfortable with this so that it's not a burden. We're good?
Sir, so when if you get it in the millimeters and then you times it by the 1,000,
Yeah.
you get D, and to get the space per split, you put the 1 over D.
Yes. Because this going to be the D, and then that would give you A. And then the only other complicated thing for this is that so let's say I have so I think the only thing was, yeah, this is the only thing. Be careful, be mindful that you can do this backwards. Let's say they get a scenario where them ask you to find the amount of lines per millimeter. So they never give the lines per millimeter this time. Because usually it's two scenarios. Is either they're going to give you the lines per millimeter, and then you're going to use that to calculate one of these variables, because you're going to use it to calculate A so that you can plug it into this and then find one of these variables. Or you can do the opposite. Then you can give A and then ask you to find the lines per millimeter. So you would have known say A is equal to 1 over D, therefore D would be 1 over A. And once you get D, since D, how you would have convert D back into lines per millimeter? You have to divide it by 1,000. So that's something you want to keep in mind as well. And that was on a paper, I don't remember which one. So backtrack, know if you can backtrack. And then let's say I have a so it's like this. Where it go? So 0th fringe. And let's say this a 1. And let's say this a 2. I come row like that as well over here. So 1 and 2. If it is that you get the angle, know about this. Right. Wait, go again. Let's say them asking for the maximum number of bright fringes. There's another word for it. I think they call them maximas. Asking for the maximum number of bright fringes. What they'll do, what you can do actually to find it, is use this formula, and for the angle you plug in 90 degrees. Because when you use an angle of 90 degrees, the 90 degrees is going to correspond to when the fringes go all the way back here. So if you use an angle of 90 degrees, that will correspond to the maximum N that you can get. But careful with this, because if, let's say you get the value at 7.9, what they told us is that you cannot round up, because 90 degrees already is at the limit of the fringe, of the diffraction thingy, because you can't make light go back around here. So 90 degrees is the limit. So if you work it out at an angle of 90 degrees and you get something that look like it round up, you know, for round it up, because round it up would suggest that you go behind the 90 degrees. That's the only other trick when it comes to diffraction grating. We okay? Let's test it out. All right, so this now, light source of, what is, I'm gonna say them questions are typical. Light from a source is incident normally on a diffraction grating which has 2,000 lines per millimeter. What is the wavelength of the light if the first order maximum makes an angle of 30 degrees with the 0 order? Right? So you notice them being very descriptive. Notice how the angle is described. So it's first order maxima make a 30 degrees with the 0 order maxima. They may have said it differently. They may have said the angle was between the first order on both sides. And then you know that just from here to here would have been half of that 15 degrees. So you have to be careful with how they word the angle part. Because you look for this angle between n where you're gonna use. So read it again. We say, what is the wavelength if the first order maximize that? So we know the formula. Ignoring. So we know the formula is what? A sine theta equal n times lambda. And we know the n. So we can pull over n over here. We'll try to find a wavelength, right? Right. So looking at the information, we just want to plug into that formula. So we're gonna try to get A, we know the angle, we know N. What them give you though? Them give you the lines per millimeter. If you are converting lines per millimeter to lines per meter, first thing you do, you go divide by 1,000. So you divide by 1,000, and you get where is it? Make sure I'm not no, it's not divided by 1,000, sorry, it's multiplied by 1,000, remember? Sorry, my bad. You multiply it by 1,000 to get from lines per millimeter to lines per meter. And then you put that under here. So use these for simple sake. And you put that under there so you get A. And once you get A, you just plug it into the formula and you get your answer. But notice you get your answer in meters. So how you convert it to nanometers? Remember that nanometers is 10 to the negative 9 meters. So what you could do is times this by 10 to the negative 9. Just times it by the power of that thingy. The power of that prefix 10 to negative 9. If it was picometer, you could have times it by 10 to negative 12. But this is nanometer. So when you do that, you actually get it coming out to be like a hundreds value, 250 nanometers. So you get 250 nanometers. We're good? We said that a while ago? Come, guys. Feedback, please. We're good?
Sir, hold on, I'm still working it out.
Oh, all right, cool. Sorry for the bug writing. Come they work it out already and then but I just want to make sure you catch how we did do it. So the first thing I do, I look at what I have to see if I can get what I need. They gave me the lines per millimeter, they gave me the number for the N, they gave me the angle. And I made sure that it's the angle that corresponds to that N. And I want to find wavelength. So I know the formula is A sine theta equal N times lambda. So I can transpose that for wavelength. But I realize I don't have A. So I start wondering how I'm going to get A. I know that A is equal to 1 over D. So I'm trying to get D. I know that D is going to be this lines per millimeter times 1,000. So I plug that in, I get A, and I plug that in, I get the wavelength. But you have to remember that the wavelength is in meter. So you're going to times it by 10 to the negative 9.
Sir, what was N?
Repeat.
Sir, what was the N?
What was the N?
Yes, sir.
Oh, I was saying that once you get it in meters, you have to convert it to nanometers because that's what they have it in. So we got an answer of 2.5 times 10 to the negative 7 meters. If you times that by 10 to the negative 9, you're going to get it should give you it in 250 nanometers. Let's try that. I don't want to make a mistake there. So use your brackets then when you have the standard form. Never worked. Let me try it again. Alright, so I could give you an easier way because I don't know why the transposition not working. I probably make a mistake. Alright, so what is this? Big to small? Okay, big to small is divide. So you have to divide it by 10 to the negative 7. Right. See, basics. Ten to the negative 9, not 7. You follow me, guys? And when I do that, I get 250. You follow me, guys? Ask me questions.
Yes, sir, I got it.
All right, so make sure you can keep getting it, because them questions they come out good. Good. So you can move now to this now. Typical lens question. You know the lens equation. I don't like how this. All right, so you need to be comfortable with the lens equation, and I can tell you a couple things about lens that should help. Ray diagrams are useful. So what is a ray diagram? So first, you have two types of lens. You know, you have converging lens and diverging lens. The converging lens are the ones that put the image by fixing everything at a point, raise them meet at a point. Diverging lens, they diverge, and because they diverge, what happens is that you trace back the line from the diverging lens, from the diverging rays, sorry, so that they can meet at a point, quote unquote. They don't actually meet there, but they seem to meet there. And the difference is that when you put a screen at that point where you see them meet, quote unquote, you wouldn't see an image there. But if you were to put a screen where a real image created by a converging lens is formed, you would actually see an image. So let me repeat. I was trying to say that let me repeat. Not much for lens, you know. For the most part, they just ask you like the formula. But you still won't have a general idea how lens work. Converging, you know, them converged lights, diverging, them diverging. I was saying that for the diverging lens, what them do is that them trace back the light to the point where them would meet, and then that would be the virtual image. The real image is created with the converging lens when the light come to one place. And a converging lens real image, that when you put a screen at that point where them light they meet, you'd actually see an image. But for a virtual image, you wouldn't see an image when you put the screen there. So that's differentiation. So, but the most part, you just need to remember this. So a converging lens has a focal length of 12 centimeters. If an object is placed 20 centimeters from the lens, the image would be, so you know the formula, 1/f. All right, so let's transpose it first. So I'm going to give you something for this too. So this is 1/12. 1/12. 1/12, give me 8.3. SI units might be an issue here. So if you convert it in meters, that would give you a different value. Yeah, so it's 0.083, not that. Should be able to show you this somewhere else though. Let me just specimen paper when you need it. We okay with this, guys? We okay with this? The key with the lens equation, just make sure that you're following the equation and it transposes properly. It's 1 over the values. For some reason, inverse kind of trick people. Make sure you say work it out as 1 over the values and then reciprocate where you need to reciprocate. And this work out to be 30 centimeters from the lens. So I'm going to tell you one thing now. Converging versus diverging lens. The diverging lens, them full of negatives. You have negative focal length. You have negative image distance. Remember, say you have object distance is u and image distance is v. When you have a divergent lens, image distance is negative, focal length is negative. The D no, the diopters is negative. Remember, diopters is how you measure the power of a lens. Who can remind me of the formula?
1 over the focal length.
Right, good. And all of this makes sense because I mean for this, and the last one is magnification. So I made a cheesy mnemonic for this. Yeah. I'm not sharing that mnemonic. It's not But you want to remember that for the diverging lens, most things are negative. The only thing that doesn't get negative is the object distance. The object distance now go negative. Now let's explore why these are negative. Because with a diverging lens, you have a virtual image. And with the virtual image, the object is formed, the image, is formed in front of the lens and not behind it, which is not normal. Usually the image is formed behind the lens. But with a virtual image, you end up having the image in front of the lens. You don't need to overthink it, but just imagine you have a lens, and you did put the object right here. This is object. If it was like, for instance, a concave lens, it would be spreading out, and they do the intersection, and then you'd see the image being formed in front of the lens. It's usually more diminished. And the funny thing as well, a diverging lens can only produce a virtual image. But a converging lens can produce both a virtual and a real image. So just putting all of this together. And so what I said, diverging of negative focal length, negative image distance, negative power in that plus negative magnitude. Magnification, not magnitude. And how you calculate magnification is by saying image distance divided by, image height divided by object height, because you can look at the height after divided by the before to see if there was a big difference. The only thing that's not affected is the object distance, u, because that object distance is going to be the same regardless. It's not something that changes. The image is made by the object. The object doesn't change. Therefore, you don't need to put in the negative beside the object distance. Everything else negative for a diverging lens. Opposite for a converging lens. A converging lens, everything positive. So why I'm saying this is because if you work out with the lens equation and you get a negative something, that means there's a diverging lens. And if it's a diverging lens, what kind of condition you can treat with it? What we treat with the diverging lens?
Short-sightedness.
Supposed to. Very good. Yes, it is. Let me show you why. I used to have problems with this a lot. That's why I asked, and I'm going to ask you this. So let's start with converging. As the name suggests, a converging lens converge light to a point. So let's imagine this for our eyeball. So our eyeball, and then the point would be the retina around the back. Now, a person who needs a converging lens, so let's understand why they need it first, and then let's give a pathology a name. A person who need a converging lens need it because when the light are coming at them eye, it'll focus itself behind the eyeball. And this is common in a case when somebody have so let me be careful. I had a mnemonic for this, just in case if the brain stopped working. NDLC. Converging lens is for long-sightedness. Nearsightedness is for diverging lens. So why? Because when you have a long-sighted person, just imagine that image coming in from all the way away. When it come in, it now go focus on the retina. It will go at the back of the eye. So that long-sighted person needs a converging lens to bring it up on the retina. So NDLC, long-sighted person, need a converging lens so that it can focus on the retina. Usually what causes this, so you need to know the causes as well. Why would you have the image focus behind the eye? Two reasons. It's either the eyeball too small, which makes sense because if it fall behind the eye, that means that the eyeball is too small, which can happen. Or it means that the lens itself too weak because it now focus it right. We're good? This is ask. They like to ask this. We're good? We okay? Guys? All right, I'm gonna go through. When the light them come in now for the nearsighted person, for the nearsighted person, the image is forming in front of the retina. So we give them ND, we give them a diverging lens so that it can diverge onto the retina. And why would this happen? Is either the eyeball too long or the lens too strong. That rhyme. So maybe that helps. They did ask this one time, so that's why I make sure I said this. So this is as much as you want to know for the eye. How do you treat astigmatism? Which lens? Let's see if anybody knows. Some of us probably all have astigmatism. I remember this coming on an MCQ. So there's a lens called a cylindrical lens used for astigmatism. And if you have cataract, then just take out the lens because the lens get clouded, then just replace it with surgery. All right, let's move. Guys, we okay? I realize the numbers dwindling. I'm here as long as you guys are here. But let me know if we're good.
The question before that, I'm still not getting the answer.
Which one? This?
No, the one before that one.
Before, as in this one down here, we did this one.
Yes, sir.
All right, remember about them and go again. All right, so tell me how you work it out. Let me see if you catch the part of how we do it though.
Sir, I changed the 2,000 lines per millimeter to the lines per meters and put it, and I say A equal to 1 over the D, and I got the 5 times 10 to the negative 7. And then I times that by the sine 30 and divide it by the 2,000.
I wonder if it's a brackets problem you're having. Cause sometimes it's really brackets cause issues with the numbers. Let's try to do it together. All right, so we'll have so how many reason this out? First, look at the given information. Them give you the diffraction. Them say we have a diffraction grating on 2,000 lines per millimeter. Want to find the wavelength, first order, 30 degrees. So I know that the ultimate formula to go to is A sine theta n times lambda. So I want to find A. I will say A is 1 over D. I will say D. So it's 1 over, what would that be? 2.0 times 10 to the 6. Because we said 2,000. So it's a 1 over that big value. So 2 million basically. And you get 5 times 10 to the 7, right? Negative 7.
Yes, sir.
Yeah, it's in meters. And now we're trying to plug that in. So we say, therefore, so now I plug that in on calculator. You see, when you have them standard forms, put them in brackets. That's what usually cause problems. So I just make sure I put it in brackets. Set to the -9 or to the -7. So I put 5.0 times 10 or put arrow up to the -7. and then I say multiply. I then just put the sign, and we are go with sine 30, which is 0.5. When we do a sine theta, I get 2.5 times 10 to the negative 7. You get that? As in, like, when we times this by sine 30, we get 2.5 times 10 to negative 7. You get that?
Yes, sir.
Sure, good.
Yes, sir.
All right. And once you get that, now we say, all right. That's why the whole simplification of the big to small. When I did so, I'm gonna do the big to small thing. Cause that they tripped me up at this point right here now. So this is big to small. Cause you want to go to nanometers. And what you do is you put your hands together. You go, if it's big to small, that means your hands would be outside and you're gonna bring your hands in for small. Big to small, and you bring your hands in, you end up make a cross. That means you multiply. Hold on. Make sure I'm doing the right thing.
Sir, so what happened to dividing it by n?
Because n is 1, so it wouldn't be because the first order maximum.
Oh,
Is it something to know? Because this is what? Meters to nanometers, that's big to small. Big to small is multiply. Why am I having a problem with this? What happened?
so sir, if it was between the first and the second one, would it be 2? The n.
Repeat?
I'm
Oh.
asking if n was between the first and the second, if it would be 2.
Yeah, cause if they give you this value, that would be the angle corresponds to 2.
Oh,
So
okay.
if they give you like the second order maximum, you'd have to use all of this angle. But sometimes the way that they word the question, they give you make it sound like this. They tell it going from second order to second order. So if they tell you all of this is 30, that means this is 15, and it's the 15 that you're going to use. So in situation like that, why may I have a problem with the transpose? All right, make sure. Don't doubt it. So let's say what? That is big value to smaller value. So I'm gonna put it in the calculator and see what I get. I feel like I should be dividing those, so maybe some maths along the way. No, it's not that. That's not working. It's divided by the 10 to the negative 9 in order to get the 250. But I'm not seeing how it work out in terms of the maths. So this is in meters. Meters to nanometers is from big to small. All right, leave that alone. But this is what I usually do though. Cause this is actually a very typical thing. Cause once you have it in meters, once you have it in meters, I did write this down and it got disappear. But anyway, once you have it in meters, as a matter of fact, let me check it here. I didn't convert. Once you see it in meters, all you need to do is put it as a hundreds value. Because this gonna come out to be it in nanometers. This is something that it's a maths thing. It's gonna be in nanometers when you put it as 100 values. So if this was 1.5, that would be 150. This is 2.5 to the negative 7. That would be 250. For some reason, I'm having a hiccup with the maths here, but call it that. This is a very typical thing, converting from meters to nanometers. If it's like this in meters, you can get it back to nanometers. by looking at it as a hundreds value. Well, I'm not sure why the math's not working out. I'm gonna make a note of that and come back to it. But we're good now.
Yes,
No
sir.
good.
Thank you.
No, we'll go through. This now. Value of a possible wavelength of radiation of visible region in the electromagnetic spectrum. All right, so this is knowledge now. This is a question based on your knowledge. First of all, the EM spec. You know them in order? So the electromagnetic spectrum, all of them are EMR. And what means that all of them have a wave speed of light. It starts at gamma, then you have X-ray, then you have UV rays, then you have visible light. It's 7 of them in total. Visible light. Then you have infrared. Then you have microwave. And then after that, you have radio wave. So like my key to remembering them in order is kind of just knowing what each of them do. What happens is that firstly, and you did this in chemistry as well, as you go up this, the energy is increasing. And as the energy increases, the frequency is increasing. But frequency is inversely proportional to wavelength. So the wavelength would be decreasing as you go up as well. So it's like you're having a wave that has a smaller wavelength, but it has a greater frequency going through. Vice versa when you're going down. So they ask you about one possibly in the visible spectrum. Visible spectrum. So you see at the visible spectrum, this is where Roy G. Biff comes in. So Roy starts here. So you notice that blue light is all the way up, which means there's more in the part where you have high energy and high frequency, but lower wavelength. Specifically, what did I say was the wavelength of blue light?
Sir, I think they said 400.
Right, 400 nanometers. Okay, so I'm gonna try to trick you with the nanometers thing down there as well. So it's 400 nanometers. If I convert 400 nanometers to meters, that would be 4.0 times 10 to the 7 meters. Don't need a calculator for that. Once you see nanometers to meters is a very standard conversion. It's hundreds in the nanometers, and then it going to be times 10 to the 7 in the meters. Always remember that. So blue light is 400 nanometers, and then red light is about how much? About 750 nanometers, right? Back in the day, I even did notice that this was orange. So the key to this, you look for the one that have 10 to negative 7. This color is orange. About 600, 800 them, not 800, 600, 650 them, about it. So look at this one. Good question. I have too much things right here now. This is why I always have to write over about this. All right, easy question. And them love to ask this type of question. So them give you two waves and them come together. There's another question like this. 2 waves and them come together. And they show you that both of them have a particular length from a point P. And they told you that they have a wavelength of this. And then they ask you for the phase difference between the waves. So now to talk about phase difference, just to make sure that we remember how you do it. So you have to remember now that what is phase difference? Phase difference is a fraction of a cycle separating 2 waves. That's what phase difference is. Fraction of a cycle separate 2 waves. Phase difference, right? And it's like 2 cars driving. You want to know what fraction of a car, for example, separates the 2 cars. What fraction of a cycle separates the 2 waves? And it can be represented in different ways. It can be represented using radians. knowing that one entire cycle is 2 pi, they can represent it in period, where that, and in angle, where this is that. So there are 3 steps to this. I'll show you guys. First step, let me try to draw a proper one. I have a lot of these questions. If you go through, you realize that there's a lot of them. So you have to be comfortable with phase difference. All right, so I'll use this. This is good. All right, so I have these 2 waves and I want to find a phase difference between them. First step, identify 2 same points on both waves. So looking at this wave, when it go up there, so, and looking at this wave, when it go up here, so, 2 same points. Imagine 2 of them your car and them a travel. You want to find out what the space between the 2 cars. So you pick 2 same points on both waves so that you can just match up what's the space between them. That space between them is representing the phase difference. But you need to find out what fraction of a cycle it represents, because that's what phase difference is, a fraction of a cycle. So the first step is identify that space. The next step would be to actually identify what a fraction of a cycle is, or what fraction of a cycle it is. So if one cycle is this, it should be this. Am I wrong? Yeah, am I wrong? Wrong. One cycle would be all of this over this. So start from here, go up, come down, go up, 1 cycle. And what I do is I'll split it up in 4s. So you can see quarter. And when I look at it, I can find out what fraction of a cycle this take up. So this isn't drawn to scale, but let's say this take up a quarter of a cycle. Say just take up here, so. So the second step, identify what fraction of a cycle it take up. And now that you know that it's a quarter of a cycle, the next thing is to find out how you represent that in terms of phase difference. You have 3 ways to represent a cycle. So if you're doing it as 2 pi, a quarter of 2 pi would be pi over 2. And that would represent the phase difference here in radians. Or that would be 90 degrees in angle, or that can be t over 4 in period. Am I making sense? Am I making sense?
Yes, sir.
Good. So this is very important. All right, so this question, tricky question. So you have 2 waves and them don't overlap each other like normal waves do. But you realize them have a space between them. So using the steps, first thing you identify the space between them. You see that the space between them is this space, and you can actually calculate that space using the values that you get. So that's the first thing I did. The space between them, 120 minus the 50, 70 nanometers, or millimeters as they have it. Might have to convert. Never convert. All right, so I guess we never convert. Let me see if it matters. So why am I find out what the space is? Once we find out what that space is, we need to find out what fraction of a cycle this represents. So what is 1 cycle? 1 cycle is the entire wavelength. They gave me the distance of the wavelength. So I want to find out what fraction of a cycle does 70 millimeter represent. So how am I going to do that? I know overall at 70 millimeters. I want to know how much cycle I can get out of 70 millimeters. So I'm going to divide the 70 by the 20 millimeters, which will tell me how many cycles I can get out of it. No matter if it was a small value or a big value, if I find out how much of something I want to get out of it, I divide it by it. So I divide it and I get say a 3.5 wavelengths or cycles we could have get out of that, which means that the wave. So notice this is the trick now. This is memory. You get the answer as 3.5 wavelength. So you're looking at the thing now and wondering where is that answer? You realize them give you these. What do you remember? When you have a interference of a whole number and a half between the two waves, because that's basically what's happening here. The two waves are coming together. This is really part difference, if you think about it like a Young's double slit. If you have an interference that is a whole number and a half separating them, it's going to be an out of phase interference, destructive interference. And destructive interference is represented with 180 degrees, or you can say pi. And in one of the questions, I actually said them put 0 for the amplitude. Should show you that if it's destructive interference, it would cancel out the amplitudes. We're good?
Sir, could you go over the last part, please?
Right, so the last part, we found out what fraction of a cycle was between two waves. So think about it like a phase, like a Young's double slit thing where we did say we have the part difference, and then we have, you know, so if it's destructive, it would be a whole number and a half separating them. If it's constructive, it's just a whole number of a wavelength. So that is, you see, that is important. So looking at this, you can see that it's a whole number and a half of a wavelength between them, which means that it's out of phase. And an out of phase wave is 180 degrees apart. So this was actually part difference that we were calculating. We found that it was a 3.5 part difference, 3.5 wavelength of a part difference. And that part difference tells me that it's out of phase. Therefore, you have a phase difference of 180 degrees. Too much thinking? We're good?
Yes, sir.
Right. So let's move. How come I don't know hear anybody else? We're done? I must say exam tomorrow, you know, basically. So better know than never. I know you guys have other things to do still, but hopefully the recording can be up by tonight because it's streaming on YouTube, so it should be up. And then tomorrow's session should start 4 o'clock, so you have time. All right, so this now, threshold of hearing. Remember the formula for the way you call it, sound level. Very important formula. 10 log. You're going to put the intensity of the sound level in question over the intensity of a threshold of hearing, which we know is 1.0 times 10 to the negative 12 watts per meter squared. Intensity in watt per meter squared. So this is threshold of hearing, easy. Which of the following is not a condition necessary for the formation of stationary waves? So we're going to stationary waves, and I'm going to just use this opportunity to explain it on the whiteboard. Who remembers what a stationary wave is?
Sir, it's a wave with the same amplitude, wavelength, and its frequency and speed.
Close. Yeah. Yeah, you would get a 1 point for that because a couple more conditions, but yeah. Yeah, yeah, but you remember though.
Directions, I suppose.
Yes, that's one more.
And the superposition?
Yes, and the superpose. That could give you a full match. Excellent. But I'm gonna tell you the definition with something else as well. So when you think about waves, technically you have 2 types of waves. Well, aside from, because you have different ways to categorize things. Remember earlier we did say you have transverse versus longitudinal waves. That was cool. And then there's this other categorization. You could categorize waves as being progressive. Progressive waves are waves that transport energy, which is your longitudinal and your transverse wave. That's a progressive wave. But then you have another category called a standing wave. which carries the entire topic. What a standing wave is, as friend said, I define it as a wave created when two progressive waves, so two normal waves traveling in opposite directions, superpose with equal phase. So they're coming from opposite directions. They're both progressive waves, and they're going to have equal phase, frequency, amplitude, and velocity. Phase. This is our MCQ. So opposite direction, progressive, equal phase, and also when they superpose, they create a wave profile that's stationary. That's why they call it a stationary wave. When you look at it, it looks like it's not moving as much. So this is the definition for standing wave. And I can draw it now. This example is when you pluck a guitar string. When you pluck a guitar string, what happens is that it starts to go up, oscillate. And when the wave reach at the end, it's going to reflect off the wall and then come back. And basically, it'll come back as a progressive wave that will superpose on itself with equal frequency, amplitude, and speed, thus creating a standing wave. And then you have points along the standing waves where the amplitude is maximum and then amplitude is minimum. And then the distance between antinodes, we said, is half a wavelength. And the distance between nodes are half a wavelength. Very important. So I'm going to just go through 3 things under this topic. 3 very important things.
Sorry, you said the distance between the nodes was half a wavelength,
Right.
and the same for the antinodes.
Because when you look at it, the so if it was a tracing out one cycle, you realize distance from node to node only take up half of a cycle. And distance from antinode to antinode only take up half of a cycle. So them take up half a wavelength. And that's important for calculation. So we have 3 scenarios. I did go through them more detail on the paper 2 marathon, but I'm just going to show you the formulas. Think about it like you're calculating stuff for instruments. You have 3 types of instruments, either a string instrument or a wind instrument, where one wind instrument is a closed-ended wind instrument and one is an open-ended. So let me show you the 3. First is string. All right, so what happens is that you see when I have a string, be careful with this. So if you never see this before, make sure you pay attention. When you have a string, what we can do is plot the string and create standing waves, right? But you can actually create different, what they call harmonics of standing waves. What we mean by that? The number of these that we create, the number of bulges that we create, they affect the sound of the music. So when you see one of them, or a basic amount of them, harmonic. And what we can do is increase the number of these that we have. So when you pluck it more, it can make more of them, right? More harmonics. And what we noticed was that when you make more harmonics, the frequency increase and the wavelength decrease because they're inversely related. So what we need to do now is find out formulas to calculate harmonics. That's our job. It's actually easy. So first harmonic. So when I say the first harmonic is the one that is the most basic. So it's the most basic standing wave that you can create. Another word for the first harmonic is the fundamental. And it will look in the string, it looks like this. There's a big bulge. And yes, they love to ask questions about this topic. Promise you that. A lot of them. So just master the topic. So this is the simplest standing wave that I can create in a string, and that's the first harmonic or fundamental. So what am I going to do with it? I'm going to find out what the length of this will be. and I'm going to find out what the wavelength is going to be as a result. And then I'm going to find out what the frequency is. So how am I going to do all of this? Because length is going to correspond to a certain amount of wavelengths. The length is going to correspond to a certain fraction of wavelengths. So it's easy. Look at it. You can see, all right, this is a node, and this is a node, and this is an antinode, which means that the length itself is corresponding to how many wavelengths?
Half a wavelength.
Exactly. So you're going to plug it in. You see this topic, I've never tried to study the formulas. Just understand it, because most of the time they give you new scenarios and you have to just use the understanding. So I'm going to solve for the wavelength by knowing, so, all right, the first thing I did was find out what length is there and what that length corresponds to in terms of wavelength. Based on breaking it down, I see that the length corresponds to half a wavelength. Therefore, the wavelength is equal to 2 times length. Nice. That's in the first harmonic. That not change. The frequency now. Remember that speed is equal to frequency times lambda. Therefore, frequency would be equal to speed divided by wavelength. Now, the speed of a wave along a string is a unique formula. It's the square root of tension divided by the mass per unit length. It's literally, as the name suggests, the mass of the string divided by its length. It's very basic. TM, however you want to remember that, they do ask this. I remember answering this. Mass per unit length. So just remember that this is where you find the speed of a wave along a string. Think about playing a guitar if you get one, and then if you were to pluck a string, you can actually find the speed of it going down. This formula. If it's not mass per unit length, another formula is there. Density times air, I believe. But this one is more popular. Right. So would get the tension in the string, you'd get the mass and divide it by the length, and the wavelength would be 2L. Easy. What about the second harmonic now? So you see, as I go up in harmonics, what I'll be doing is adding more and more of those harmonics, which means I'm going to add more and more of these.
What you said the frequency would be?
Oh, the frequency would be, we said the frequency would be the speed over the wavelength. So you find the speed using the formula and then divide it by that wavelength. And that's it.
Okay, sir.
Oh, good thing you tell me that. There's a formula that can help. Let's say you want to find the frequency at any harmonic, because you have first harmonic to straight up. What we found was that the harmonics are a multiple of the first harmonic. So let's call it first harmonic F0. If you want to find the frequency at the 7th harmonic, all you have to do is times the first harmonic by 7, because they're all a multiple of the first harmonic. You're beginning from the first harmonic. It's like you're just adding up as a multiple. Because when we go to second harmonic, all I'm going to do is add one more to it. And then third harmonic, add one more to it. So they're all multiples of each other. Very important formula. So doing the second harmonic now, what I want to do, I want to find out what the wavelength is. So I'm going to do the same thing again. The length doesn't change. Unless I tell you the length change, the length never change. And going to say, all right, L will say how many wavelengths?
1 wavelength.
Very good. You can see that it's 1 wavelength because it's half plus half. And then therefore the frequency gonna be, we said that what we're putting wave speed, which you know is that same formula, square root of T over M, capital M for the mass per unit length, and then you divide it by the wavelength, which we just calculated as L. That's the second harmonic. So when you understand it, you don't have to remember these formulas. And then the third harmonic, you're just gonna add one more bulge to it. I made that a little too much. Crazy. Might as well, whatever. I'm going to put node, 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 then antinode, 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 and I put a node in the corner here. And then we're going to find what the L going to be equal to in terms of wavelength. Can you see what the L going to be equal to, or the drawing too bad? So half a wavelength plus half a wavelength plus half a wavelength. Where you get there?
One and a half wavelength.
Right. You get 1.5 wavelengths. So this now tells you if you're good on your maths from basic school, improper fractions. So I'm going to convert this now find out what the wavelength is, right? So first thing, I'm going to convert this in an improper fraction. So 3 times 1, well, 2 times 1 plus 1, we get 3/2, easy things. And then, oh, what's this going on? I make a mistake. So once you know what you're doing, you'll be fine for this topic. Three over 2 times wavelength. Good. So I want to find the wavelength. So the wavelength going to be 2L over 3. You see that? I'm going to give you something that make that easier to see as well. You see that?
Yes, sir.
So watch how this makes sense now. What did I tell you initially? As you go up, your frequency increase, and therefore your wavelengths decrease. That's what happened. As you went up, your frequency is in fact increasing. It's going to increase because everyone is going to be a multiple of the first one. But watch the wavelength. Initially, the wavelength was 2L, not true, 2 times the length. Then when you reach second harmonic, it halved. The wavelength became L. When you reach third harmonic, it became 2 over 3L. And you realize that it keeps decreasing, confirming that you're going up the harmonics. And because you're having a smaller denominator, and the numerator is remaining the same, frequency is increasing. So all of that making sense. So I'm going to show you the next instrument now. Strings finish now. I'm going to show you.
When the length increases, the wavelength increases.
Repeat?
I'm asking if you said that when the length increases, the wavelength decreases.
Not the length, the frequency.
The frequency?
You see that? Why is that the case? There's an image I can show you. First of all, the speed equation says speed is equal to frequency times lambda. If I was to look at a relationship between frequency and lambda, so let's make frequency the subject. You realize that they're inversely related. But on top of that, what I like to see is this. Imagine 2 waves. So that's wave 1, and then you have this wave. And then you have wave 2. So what happens is this. Notice wave 1 have a greater frequency. But in terms of its wavelengths, distance between 2 successive points, they're smaller. Wave 2 have a smaller frequency, but it have a greater wavelength. You see that?
Yes, sir.
So it makes sense. So going to this now, so I go to the which one first? Closed pipes first. So we do strings, so we have closed pipes. All right, so closed pipes is the key to it. Notice what the first harmonic look like, and then everything is a build-up of it. The first harmonic look like this. One side open, one side closed. That's why it's closed pipe. The other one going to have both sides open. That one will be an open pipe. You see the point where the one side closed, that will have a node. And then up here we'll have an antinode. There is a question where they showed you like some lines like this, and they asked you to tell them if it would represent the closed pipe in terms of the first harmonic, and they asked which one of the examples it matched. It's coming from this logic. The bottom part is a node, 0 amplitude. The top part is an antinode, maximum amplitude. So in that question, them did have like lines with a small amplitude here, then it get bigger and bigger and bigger. All right, so going back to business, what we are trying to do, we are trying to make the first harmonic, which means we are trying to make the simplest standing wave in this. But you realize one side open. A standing wave looks like this. We are trying to put this in there, a simple standing wave. But you realize in order to do that, you're going to have to compromise up here. This can go in it because the simplest thing we can go in and still have an antinode here and a node here without making any more twists. It just going to have to be that. So I want you to appreciate why it looks like this. The simplest standing wave, the first harmonic of a closed pipe is this. Easy. Now we do the same thing as before. What we're going to find is the wavelength. So how much wavelength is this corresponding to?
A quarter wavelength.
Very good, because node to node is half, so node to antinode is quarter. And this is big MCQ. So so I'd say that the length is equal to quarter of a wavelength. Therefore, wavelength is equal to 4 times L. Good. And then the speed now. Not speed, frequency rather. Because we know we transpose started to find frequency, speed over wavelength. But you see the speed of sound is what we're using now. And the speed of sound in ear is about, I did say a mistake earlier now. The speed of sound in ear is 340 meters per second. I did tell you this was water, it's actually air. This will come on the paper, hopefully. Speed of sound in air is 340. When it's in water, it gets faster. And then it gets solid more faster. And then the wavelength is this. All right, so this now. So this is the next harmonic. Watch the trick with the next harmonic. What am I gonna try to do? I'm gonna try put in a so maybe I'll explain this properly. Right. If I'm putting in a next one, I need it to be in such a way that it has this at the end because the end is an antinode. So in order to do that and still have a node at the end here and an antinode up here, I will have to put in an entire one and then make it open up like this. And this has its complications. So this will be antinode, this is a node, this is an antinode. And then working it out, length. So how many wavelengths we can get from here? How many wavelengths?
3/4. Yeah.
Very good. Sorry. Probably 3/4. Okay. And then you can solve for wavelength to be 4L over 3. So here's the easy way. As you go up, you're going to put, it's always going to be 4 on the numerator, but you're going to put the harmonic number under it, which is what I want to tell you now. This is the third harmonic. So you wonder what happened to second? How we jump a third? Because if you look at it, the first harmonic is actually this. This is the simplest thing that was a first harmonic. So in order to get a second harmonic, we would have to put one more of this in it, and one more of that would have looked like this. This would have been second harmonic, but we cannot have that because this is a open, this is a closed pipe. So what we did instead was put one more of that plus one more. So instead of a second harmonic, we ended up with a third harmonic. You see that? So in other words, closed
Yeah.
pipes, they increase by odd numbers. Good. Closed pipes that increase by odd numbers. You're going to jump from first harmonic to third harmonic to fifth harmonic to seventh harmonic. And then there's this thing called overtone. So you can have the first harmonic being called the fundamental, and then the second harmonic is called the first overtone, and then you have third you get the idea. The overtone is how them do the other alternative names. Sometimes they like to throw in the other word just to trick up people. So it's first harmonic, second harmonic, or fundamental and then overtones. But you realize closed pipes are odd numbers because of how it's set up. It take a long while before me realize, yeah, that's why we used to just swat it. So keep thanks. Right? And then that's all right. When you do the if you were to do the fifth harmonic, is the same thing. What you do is add this to it, and then you're gonna work it out. You're gonna end up with 5/4 wavelength, or about 2 1/4 or something like that. And then when you work it out, you end up with 4/5. L is equal to wavelength. No surprise, because remember we say it's going to be always 4 over the number of the harmonic. So it's going to be 4 over the fifth L. And when you reach seventh harmonic, it's going to be 4/7 L. And when ninth harmonic, 4/9 L. So that's your closed pipes. Not bad. Oh, it look like I run out of whiteboards. Interesting. I didn't know I could run out of whiteboards. So how do I refresh whiteboards? All right, so I can just clear. We're good though, guys? We're good?
Yes, sir.
All right.
Yes, sir.
Fair. Let's clear off these.
So, sir, for the closed pipe, it's for the frequency, it's still going to be the V over the lambda.
Repeat.
Sir, for the closed pipe, it's going to be, for the frequency, it's going to be the V over lambda.
Yeah.
And the speed would be 340 meters per second.
This is the speed of sound in air.
Okay.
Right. Good. So you can actually use a closed pipe to calculate the speed of sound in air by transposing the formula. So what about a open pipe? Last one. All right. What about my open pipe? Open pipe is very similar to the strings in formulas. It's literally the same as the strings in formulas by accident. This is how open pipe look. First harmonic. Both ends are open, which means you have an antinode at both ends. Very important. If I was to put the simplest setup in this, the simplest standing wave, it would have to look like this. Would have to look like this. Come off both end open, and this is the simplest it can be, right? So now I just need to figure out what's happening for this. And as I said, the formulas for this is very much just like strings. So it's antinode to antinode. You're going to get am I doing this right? Yeah, half a wavelength. So wavelength would be 2 over L, just like in string, but it's backups. Frequency is going to be speed over wavelength. Speed of sound, wavelength is 2L. As I said, the formulas them are going to be just like in strings by chance. It just happens to be like that. So for this now, we're going to add one more in the middle. So I'm going to add one in the middle. so it can get a second harmonic. And then that now if you work it out. So that would be so this is antinode and antinode, so that's half a wavelength, and then you have antinode to antinode, another half a wavelength. So L would correspond to wavelength, and then you know the frequency thing. And then you can do the same thing for your this now. All right, so this now, let me see now if I miss out any no. So it'll be antinode to antinode to antinode to antinode. So it'll be half plus half is 1 plus a half, so it's 1.5. And you realize it works out just like the third harmonic for the strings. So this is harmonics. If you master harmonics, you're not getting harmonics question wrong. So let's go back and tackle our first one. First of many, literally. All right, so this one is good. Let's reason it out. A glass tube of effective length, just think out it as length. Because what happens is that sometimes there is an additional distance considered at the end of the tube called the end correction. So if you've been reading the text card, you will have seen it, but it's not that important. It's like you have a additional distance where the sound can travel out, especially if it's a closing or opening pipe. The sound come out at the edge and it's an end correction. And why I bring up that is because when you add the length of the pipe with the end correction, that's when you get something called effective length, which is just another represent the total length, the actual length of the system. So it's more accurate. So you know you're factoring in the effective, you're factoring in the end correction as well when you do the effective length. Right. So what am I saying? A glass tube of effective length 0.6 meters is closed at one end. So that's a closed pipe. Given that the speed of the sound is 300 meters per second, the lowest resonant frequencies are, so what am I asking for? Them are asking for which two harmonics? So we identified this a closed pipe, which two harmonics?
Would it be the first and second?
The first and who?
Second.
This is which harmonic? Third harmonic. No, the let's say it. This is closed pipes. Okay, see them so one
Oh, yes, sir. So the
Yes.
first and the third one.
So to avoid that, you know, I always do, no matter how confident I feel about this topic, I always do it. When you see a question we have to do with harmonics, once this is a harmonic question, first thing you do, you look away you get. You get the distance, cool. You get the velocity, cool. You write down given information. And what you're going to do is draw the diagram. So all of them, something that I draw from your head is because every time we do a harmonic question, we draw it. You draw that diagram. So the first harmonic look like this. And then you can say, all right, what was the wavelength of this again? L corresponds to quarter of a wavelength. Therefore, wavelength is equal to 4L. And then therefore, what we are trying to find, frequency is equal to the speed we will say is 300 divided by that 4L. And we get 125 hertz. And then if it's a third harmonic, we just gotta add one more into it. And if we do that, we get a wavelength of about 4 over. So if you don't want to do that all the time, you remember the logic method, put it over 3. So 4 over 3L, and then the frequency would be that speed over that wavelength. Also notice the third harmonic frequency. Notice the third harmonic frequency is 3 times the first harmonic frequency, which is what we expect because of this. We see it? We got it? We get it? Now move on. So I was saying that this is the key thing. This is for make you never get it wrong. You realize that we're trying to find the 2 lowest resonant frequencies. In other words, we're trying to find the 2 lowest harmonics. First harmonic and third harmonic. Because remember, this is a closed pipe. So you jump odd numbers, and I showed you why. And How we do it? We find the frequency by saying speed over wavelength. And we know if we find the wavelength in the two scenarios, draw it out and work it out. 4 over whatever the harmonic number is time L, and you get the wavelength. You plug it into the formula for the frequency, you get the frequency. What I want you to observe is that the first harmonic and the third harmonic, 3 times 125 is 375. What I told you is that all of the upcoming harmonics are just multiples of the first harmonic. So the third harmonic is literally the third harmonic because it's 3 times the first harmonic in terms of its frequency. Make sense?
Yes, sir.
So you're not getting these questions wrong. Good. So go to this question now. Typical type transmitter type question. You see, when I see a question like this, the first thing come to my mind, because this is a typical question. You see, from them say microwave, I need you to understand this. A microwave is one of the 7 EMRs. Remember, you have the order. If it would be nice if you know the order of them, but it's not that high yield. But it is one of the 7 EMRs, which means that it, among the rest of them, travel at the speed of light. So even though they don't tell you what the speed of this wave is, you know the speed should be the speed of light. So from the city setup, I'm going to say microwave. Remember, say its speed is speed of light. So the next thing, microwave transmitter sends, microwave transmitter X sends radio waves to a metal heat Y. So radio waves is what it's being sent. Still speed of light, no difference. A probe P is placed between Y and that. So the probe is there to detect stuff. I think, yeah. It's there and it's moving so that it can move from one node through 20 antinodes to a node 0.3 meters away. Don't get frightened. This is typical. What is the frequency of the microwave emitted by the da-da-da? So the first thing, so what they're telling you is that this probe go from here so to here so. And if first thing, this is a, how you know that this is a standing wave scenario is because when the microwave emits between the metal sheet, it will eventually go to the metal sheet and hit this surface and then reflect back on itself. And the fact that it's the same microwave, it's going to come back with the same frequency, amplitude, and speed wave. And then the probe is just there to determine, as them telling nodes and antinodes, saying no is a standing wave scenario. But look what they said. That probe moved from one node through 20 antinodes to the next node. In other words, them say a jump all the way from node to node, and remember, say in between nodes, you always have antinodes. So here's the formula. If you want to find just the space between, so let's say them give you the total distance traveled by a series of nodes or a series of antinodes. This is a repeat thing. If them give the total distance of a series of nodes or antinodes, and you just want to find the distance between 2 antinodes, just 2, because you know the distance between 2 antinodes correspond to half a wavelength. What you can do is say the total number, the total distance of nodes or antinodes, and divide it by the number of nodes or antinodes, depending on what they gave you, and that will give you just the distance between 2 nodes. Am I making sense? Or 2 antinodes. Am I making sense? So it's like total distance divided by the total number. So you can just get 1. That's what I'm trying to say.
Sir, convoluted in my brain.
All right, so we need it for unconvolute. Take a second. Oh. All right, what will I try to do? We'll try to find the frequency. So go back to the basics. We'll try to find frequency. How will I find frequency? What would you do to find frequency?
Sir, would it be the speed over the wavelength?
Exactly, because I trained you to say, all right, anytime you see a wave equation, the first equation should come to mind is the wave formula. So first equation should always be the wave formula. So you know, say this you're going up a go to. And you realize that in this formula, what don't you have? You know that the speed is speed of light. You don't have the wavelength. So what you're like trying to do is find the wavelength. So you look at what you have to say you can get what you need. That's why you're given information. You look and you realize that you have the total distance traveled by a series of nodes and antinodes. Then you get the total distance and you know the number of them. So if you divide total distance by the number of them, you're going to find the distance just between two of them. That's what I'm trying to say. And the distance between two nodes is what?
Half a wavelength.
Exactly. And this is a thing. Anytime you see them give you one bag on, them give the total distance for one bag of nodes and one bag of antinodes, just divide that total distance by the number of nodes or antinodes that they gave you, and that will give you the distance between the two of them. And that will be half a wavelength. So that's what I did. You get the total and it's in meters divided by the number that give you half a wavelength. And then you multiply that by 2 so that you can get the wavelength. And then you put it in your formula. And the best part about this question, you can actually go online and type in what is the frequency of a microwave. This is it actually. So which of the following quantities do not remain constant when a particle moves in simple harmonic motion? All right, so let's talk about oscillation quickly. I hope this is helping though, guys. Now I know we're going longer than anticipated, but the idea is that we're covering the topics then, so hopefully it can make a difference. And you will realize once you know the stuff, it's easier to go through the past paper questions. Look like I ran out of whiteboards. Oh, I didn't. Good. All right, so I talk about simple harmonic motion. Somebody quick, how you define oscillation? Simple harmonic motion. All right, man, we'll figure it out. We have to know simple harmonic motion. It's the best topic, my favorite topic, and a lot of questions come from it. Not a bad topic. So what is oscillation? I'll just show you the basics and the formulas, and then we answer questions. So simple harmonic motion is a motion where the acceleration of a body is proportional to the displacement of that body from a fixed point or equilibrium position. From a fixed point or equilibrium position. So what I mean by that, quick. Two scenarios, pendulum, spring. Not going too deep. But you have to understand it for MCQ actually. Pendulum. Now, what I mean by acceleration, directly proportional to displacement from fixed point. What happens is that so this is my body at the equilibrium position when it's not moving. If I were to displace it, displacement literally means movement from starting point in a particular direction. So displacement would be in pushing it from the equilibrium position or lifting it from the EP. Now, a funny thing happens. When you displace it from the equilibrium position, what will happen is that if you were to pull it to a certain point and release it, you realize there's a force that will pull it back to the equilibrium position. And that force is the restoring force. When a string is oscillating, because this is what it's all about, oscillation. We're mastering oscillation now. When a string is oscillating, you must have some force to pull it back so that it can keep going back and forth in simple harmonic motion. That's your restoring force. But you see that restoring force, it have a unique relationship with displacement. You see what happens is that you see the further you displace the object, the further away you pull it, is the more force required to pull it back. So what we can say from that, because we understand proportionality well, we can say from that that the restoring force is proportional to the displacement. We can agree?
Yes, sir.
So this restoring force is proportional to the displacement. But notice, while the displacement is increasing and that restoring force is increasing to pull it back, notice they're in opposite directions to each other. Very important. When you pull it away, the farther you pull it away is the more force I go pull in. They're opposite directions to each other. And therefore, I'm going to put negative right here to suggest that they're in opposite directions. So that restoring force is in opposing directions to the displacement. Now, restoring force will provide an acceleration, which is where it's all coming to. That restoring force provides an acceleration based on Newton's second law. So that acceleration will also be proportional to the displacement because it's going to go this way and then displacement going to be going this way. More this, more this. And then using proportionality, that will be equal to a proportionality constant, put the negative sign, times x. And what we found was that the proportionality constant for simple harmonic motion is omega squared. And then you just multiply that by x. And this is how we get the infamous SHM equation. So omega squared times x, where omega squared is representing that proportionality constant between the acceleration of a body in simple harmonic motion and its displacement from its fixed point, equilibrium position. It makes sense? So in order to oscillate back and forth, when you pull out, one force is going to pull you back in with an acceleration that is also proportional to that displacement, but they're in opposite directions. That is simple harmonic motion. And with this, you're able to go up, and the maximum displacement, we call it amplitude, and you're able to go back to the equilibrium, and then you go to the other amplitude, and then you go back to the equilibrium. All good? All good?
Yes, sir.
Yes, sir.
All right. Why you guys sound more sad than me? That's not fair. We're going to finish. So I'm tired. I had to do a research thing earlier. Just trying to finish early. See if we can finish. All right. So important. What about a spring? So the spring is like this, and this is normal spring. Let's say add a mass to the spring. So the spring was normally by itself, but let's say add a mass to the spring. What the spring will do then is start to extend based on Hooke's law. So it extend by Hooke's law, and then you have extension. Good. So this would be Hooke's law. Now, when the mass step on it and it just there like that, that would be when it reached equilibrium position. But let's say you now decided when you see the mass step on it, you decide to pull it even further. You start to pull it from the EP. In other words, you decided to displace it. You pull it from the DP, so it displaces. And it reaches a maximum displacement, which is its amplitude. And then when you let it go oscillate back and forth in simple harmonic motion. Because what happens is that when you have a displacement, you know that there's a restoring force that is going to be countering that displacement. Pulling it out, you have a force where you're going to pull it back in, and an acceleration directed that way as well. So it's the same principle. The acceleration is directly proportional to the negative displacement from a fixed point in the opposite direction. So this is the spring. So look at formulas. Not a lot of formulas actually. Let's see if I can fit them on the page. So the first couple formulas, general formulas, Then you have formulas specific for the string and the pendulum. That's it. And formula for energy. So the first formula, we're going to look at a formula for displacement at a specific time. So X is equal to go again. A cos omega t. How we get the formula here? Then do something. I would suggest just swat it because you know really need to know. But my trick to this formula is that look at what they do. Let me be careful. If you're having problems with it for real, though, I can show you, but see, let's just swat it at this stage. But the derivation, I think, is in the book. So if you want to look at it at another time, you can do that. What? So let me explain. So note, you see these two formulas? These are the only two formulas they put in radians. Anytime you see these formulas being used, you put a calculator in radians. Otherwise from that, don't put it in radians. Never again. And the thing is, this formula is good for when you want to find a displacement at a specific time. Simple harmonic motion. This formula is when you want to find a velocity at a specific time. Simple harmonic motion. And notice it says displacement equal A cos omega t. So A being amplitude. So it's like it'll show you the maximum displacement. And then V naught here. So V equal V naught cos omega t. V naught here is representing the maximum velocity. So it's like the same pattern with the formula. So X equal A cos omega t. V equal V naught, which is max velocity omega t, because they're both maximums of the thing. And then it's cos omega t or sine omega t. So what's the difference? Why you have cos and sine? Because there are two different graphs. A sine graph, we know, starts at the equilibrium. Sine graph starts at the equilibrium position, and the cosine graph starts at the amplitude. We're good?
Yes, sir.
All right. So that something I should have added. Very, very important. When you're doing the pendulum and it's also in the spring, very, very important. We need to know what happened at the amplitude versus the equilibrium position. It's when you're at the amplitude versus EP, looking at the velocity and what happened to the velocity and what happened to the displacement. That's what we need to know. So when you're at the EP, the displacement is 0 because you don't start moving yet. But what you realize is that the velocity is actually maximum here. When it oscillates back and forth, it reaches its maximum velocity when it reaches at the equilibrium. When it go up, think about it like going to max height. As you go up, you get slower until eventually your velocity becomes 0. But then your displacement becomes max. So they're inversely related. And let's drop in energy. Energy formula, if the velocity is maximum at the equilibrium, you also expect kinetic energy to be maximum at the equilibrium, right? And if the displacement is maximum at equilibrium, you expect potential energy to be max at amplitude, amplitude. But you have to understand the idea of total energy. Overall is a set amount of energy, and it's the sum of the kinetic and potential energy. At any given point, it's just the sum of the kinetic and potential energy. So let's say they're at the midpoint. You know what actually happened? At the equilibrium, all of your energy would be in the form of kinetic energy. But as you go up to the amplitude, you're converting that kinetic energy into potential energy so that you can have the same total at the end of the day. You need to balance between the two. When you reach the equilibrium, you have max kinetic. As you go up, you decrease the kinetic and increase the potential. When you reach halfway, you have half of each so that you have the same total. And when you reach at the max, the amplitude, you would have done the kinetic and only have potential. So that's the idea of the total energy there. So I bring that up because I wanted to say this, the graph. So this is a displacement time graph. We still with me, guys? I realize I don't like silence here.
Kinda.
You sure? You shouldn't make me be telling you things where you're not understanding it. Makes no sense. Which part? The key, I know it's the memory aspect you're worried about, but try to understand it and see how we use it in questions. If you stay, you're going to see a lot of questions with this type of thing.
Sir, you lost my friend. You start the pendulum.
Oh, so I need you to understand this pendulum. What I was saying is that at the equilibrium versus the amplitude, there's a difference in what happened to the kinetic energy, what happened to the velocity and the displacement, and then you can think about its energy stuff. So let's do that again. Let's make it practical. The kinetic energy, no, not kinetic. First thing, when you're at the equilibrium position, there is no displacement because equilibrium is when you start. So there's no displacement from start if you don't start. So displacement is 0. However, when you're at the equilibrium is when you have maximum velocity. The best way to remember this, if you ever see a pendulum or swing, when it reaches the middle or when it moves the fastest, right past the middle, that's when it have the maximum velocity, run right past the middle. But the opposite occurs as you go up, because what happening is that as you go up, your displacement is increasing. And as you go up, think about it like going to max height. What happened at max height? Velocity is 0. It's the same logics kind of for this. When you reach up here, so the velocity becomes 0, but the displacement is max because that's the amplitude. And then I added to it what happened to the kinetic and potential energy. If the velocity is maximum at the equilibrium, that means that the kinetic energy will also be maximum. If at the amplitude, the potential energy is maximum because displacement is maximum. Because what is potential energy? Mass times gravity times height. Displacement. Height, displacement, once you see them there increase, yep. So move. Wait, we're going to do that? Sorry.
Yes, sir.
You sure? So just remember it like how, remember it, where you know the displacement are gonna increase as you go to the amplitude, and you know what happened to the velocity as you go up to max height. Then the kinetic energy is half mv squared. If the velocity max, kinetic energy are gonna max. If the displacement max, the potential energy are gonna max. And then the last thing for add to your brain from that is remember, say, yo, total energy is a thing. When you say total energy, is the sum of potential and kinetic energy. At any point, if you are going to go at any point in this motion and just find out what the kinetic energy is there and the potential energy is there, and you add them up, the total energy should be the same at any point because it balances out. When you reach equilibrium, the kinetic energy becomes maximum and the potential energy becomes 0 so that you have the set total energy. And as you go up to the amplitude, that kinetic energy gets converted into potential energy because you're gaining displacement and you're losing velocity. And eventually you're going to have a maximum potential energy and 0 kinetic energy so that you can end up with a balance. When you're in the middle, both of them are half. Right? So let's look.
The total energy would be like constant.
Is a constant, it's conserved as long as the body is not experiencing any friction.
Okay, sir.
Good. So that would be like a free oscillation. We did a lot of content today now. Wait, take a second. I want to show you the graph. Basically cover all of, well, we have covered all of module 2 topics after this question, after this topic. So going forward, I'm not repeating all of that stuff. Make sure we, despite people not being here, hopefully we'll watch it tomorrow. And when tomorrow come, we can make a progress. I'm willing to stay up until hopefully at least 2009, 2000, well, not 9, 2011, 12. After that, you're kind of in a good waters. All right, so this displacement time graph. So notice if you're at 0 on a displacement time graph, it means you're at the equilibrium position. That makes sense. And then going up here, that would be when you reach the amplitude. And then going back to the equilibrium position, and then you reach the other amplitude, and then you're going back to the original equilibrium position, one complete cycle. That would be a sine wave. This graph is represented by the equation x equal a cos omega t. It's like the equation of this graph. Just like how you have equation for straight line, it's represented by this graph. Because it's like plotting displacement versus time. That's what this graph is all about. That's what this formula is all about. Versus this now. Let's say these are kind of putting together two things. The displacement time graph here starts at the equilibrium position, right? Right, that's it. So look at the velocity time graph. The velocity time graph at that same point is going to be at maximum. They're inversely related. So when you have a sine graph for the displacement time graph, you expect a cosine graph for the velocity time graph. This should actually, this is why I brought up the graphs, because I should show you this now. This formula should actually say a sine omega t. Why? That's why you have two formulas, because this is a sine graph. So when it's a sine graph, that's when you'd see a sine omega t being used. When it's a cosine graph, when you start at the amplitude, then you'd see a cos omega t. That makes sense?
Yes, sir.
Very good. I remember when I went to the physics thing up at UA and that never did connect. So, give thanks. This now, at that same location, we said that the velocity at the equilibrium is max. And then as you reach to the point where, the person would have reached at the amplitude, that's when the velocity would have reached 0. So they're inversely related with each other. And this graph would be represented by V equal V naught cos omega t. If it was a sine graph, then you'd say sine omega t. And as I said, when you see these equations, when you're in the situation where you need to use these equations, put your calculator in radians. We're good? I'm going to show you the rest of the formulas now. All right, so them two formulas they out of the way. Suppose you want to find, let's say I try to find the velocity at a specific displacement in a simple harmonic motion. Okay, I have to think about it like, let's say this is the amplitude. But let's say when you're up on your journey, if you go up, you say you did stop right here. So right here, so let's say you did have the velocity and you did want to find the displacement here. So you can use a formula to do that. Just like how, let's say you did have the displacement and you did want to find the time here. So the best formula to find the time here, so with the displacement would have been x equal a cos or sine omega t. And if it's velocity and you want to find the time, then you use the velocity one. So I'm just showing you how to use them. But let's say you want to find the displacement and your velocity. There's a weird looking formula. But remember this formula, it looks like the one that we use in equations of motion. So it's v squared equal omega squared times a squared minus x squared. Repetition. This formula is similar to the one from equations of motion with us. both of them have the same job. They find a velocity at a specific displacement. But as you can see, there are different formulas. So just try to remember it. V squared equal omega squared times a squared minus x squared. They expect you to remember it. Right. And then let's say you want to find the maximum velocity. May I ask, where is the maximum velocity found?
Sir, at equilibrium.
Excellent. So now we can calculate it. Now I'll show you. At the equilibrium, displacement is 0. And so because displacement is 0 at equilibrium, I can simplify this formula as V being equal to omega A. So when V is equal to omega A, that is when the displacement is 0. And therefore, that is when you're at the equilibrium when velocity is maximum. You see that? Logical. And then the next formula is how you find the acceleration when it's maximum. Where do you have maximum acceleration? I'll ask.
At the amplitude.
Excellent. Why?
Because it's maximum displacement and acceleration is proportional to displacement.
Very good. So which formula would we be using to represent relationship between acceleration and displacement? Which formula connects acceleration and displacement? The simple harmonic motion formula. You see it? That's its job. It's supposed to make you can find an acceleration at a specific displacement. That's the purpose of the SHM job. So specifically, if you want maximum acceleration, you'd be at the maximum displacement, which is A. And these are the most important formulas there. All right, so I'm gonna move. We're good? We're
Yes,
good?
sir.
I want to show you some formulas now for springs. So first, before we go spring, pendulum, one formula in pendulum, well, two formula in pendulum you have to remember. Two formulas. And yes, you have to remember it, unless you don't remember it. So how you find the period of a pendulum? 2 pi square root of L over G. There's a derivation for this, you don't need it for paper 1. 2 pi square root L over G, very important formula. And let's say you want to find omega square of a pendulum, because what we had done to you see what we can do to actually prove say a pendulum exhibit SHM is show that the pendulum's acceleration is equal to omega square times x. So what we're trying to say is that we can show that a pendulum has an acceleration of omega square times x. And what we found was that omega square for a pendulum was equal to the gravity divided by length. And this is a very useful formula. Very useful formula. Have it in your head. The way that they got this derivation is by using that formula, because what they said was that since omega square is equal to, so remember say omega is 2 pi over t, right? 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 Yeah, right. So 2 pi over t is the same as 4 pi square over t square. And then omega square is also g over L. So when you transpose for t, you end up with 2 pi square root of L over g. Very important formula. So I'm going to show you the same formula for the spring. So how you find the tension of a, not tension, the period of a spring? 2 pi square root of m over k. Good formula. And then omega square is equal to k over m. Now what you should notice in the formula, whatever omega square is the inverse of what is in the tension formula, the period formula. And the reason for that is because of how it's derived. Remember, say I equated it off, you equate them, and then transposition did take place and everything switch up. So omega square is g over L for the period of a pendulum. Omega square is k over m for the period of a spring. And you see that it becomes 2 pi square root of m over k. All right, good formulas. So what about very important now? Important. Very important. What about when you have a spring in parallel versus series? Easy. All right, so if it's in parallel versus series, you can say, all right. So when they're in series, they look like this. One on top and then the next one on it, and then like it have a mass attached that both of them is supporting now. And if you're finding the spring constant for both of them, the resultant spring constant, two scenarios is either, let's say you're talking about two springs of different spring constant. If they have different spring constants, it's going to be 1 over k equal 1 over k1 plus 1 over k2. Very, very useful formula. Comes up from time to time in the class papers. So why is this the case? When you put two springs together, if you ever do that in real life, you realize that it becomes very stretchy. It's like you allowed more support. It no need to do all of the work anymore. Two of them they do the work. So it's like it becomes very stretchy, and that is because there's less force now that's required to extend it per meter. The K is less. Less K, less force per meter. Therefore, it can stretch more. So once you have two of them put together, like both of them will do it, you need is less force per unit meter to extend it. Am I making sense? So the K is less. And it becomes therefore stretchier. If you have a smaller K, it means you have less force needed to extend it. Therefore, it's stretchier. Am I making sense?
Yes, sir.
All right. So you see that formula? Very good. And then there's another way to represent it. Let's say the spring constants were the same, which is usually what they are, but sometimes they put them as different. You have to remember the formula there. If they're the same, you can just divide the one. Divide it by 2 because it's going to be halved. So like if both of them have a spring constant of 5, the resultant spring constant would be 2.5. It'd be half. But remember this formula as well. Suppose you want to find the before we go parallel, suppose you want to find the extension. So I said that the spring, in this case, less force exerted per meter, which means they can extend more. So the extension doubles. So once you understand it, you remember the formulas. What about parallel? If it's in parallel, it's like you make a tougher spring. Tougher spring so that it's tougher, which means it requires more force to extend it per meter. So what you see for the spring constant, the total spring constant is going to be a sum of the two spring constants. Because them group up together and make a tougher spring. It's just tougher and it's harder to stretch. Versus this will just loose. And then also consider, let's say they had the same, just like that other scenario. Let's say it was the same, both of them, same spring constant. Then you could have simply said the total spring constant would be 2 times the original one. So it get doubled. And what would be the extension? Somebody know? What do you think will happen to the extension? Give me some reasoning.
You divide by 2.
Right. Why?
Because both springs are placed together in parallel.
So because they're in parallel, you realize that the spring constant is doubled. So if you have a double spring constant, that means it requires more force to extend it, twice the amount of force to extend it. If it requires twice the amount of force to stretch it, it not gonna stretch as much. It's stretching and get it half. So that's what's happening at half its extension because it requires double the amount of force to extend it. So I want you to understand it so that the formula stick, right? Make sense?
Yes, sir.
All right, and we think we're done, but there is one more set of formula in a simple harmonic motion. Master these formulas and you're good to go. Which are the formulas? We have to know the formulas for energy in simple harmonic motion. Just two formulas, potential energy and kinetic energy, just two, in the hard. All right, because what happens is that if you find kinetic energy at any given displacement, kinetic energy is half mv squared, right? But v squared is what? In simple harmonic motion, v squared is omega squared times a squared minus x squared. So this is a formula for kinetic energy at any displacement. Right. Let's say you want to find maximum kinetic energy. And that maximum kinetic energy formula is popular. And its maximum kinetic energy would be the same as the total energy in the system. Because remember, when you reach maximum KE at equilibrium, your potential is zero. So all of your KE is in the form of potential kinetic energy. So how you find total energy? Just find maximum kinetic energy. So let's do that. When you have maximum kinetic energy, let me ask. Tyler talk. When you have maximum kinetic energy.
When it's at equilibrium.
Right. So it's what me I gonna know. Me I gonna put this as 0 so that me can make a formula for that. So I say half m omega square, and it's not like I cook up a formula, so this is like the official thing. A square. Very good. And this is a beautiful formula because we can represent it another way. What we did say was the formula for the omega square of a spring. There's a question on this exact thing somewhere down the line. I should add the documents in the website link. So if anybody want to use them now, I have the documents. So if anybody want to use them now, they could be using them. But what did I say was omega square? Anybody remember? Remember? Omega square K over M. Useful formula does come up. Want a break? Guys? Feedback? Put that again. MK over M A square. And you see what happened? You end up with half KA square. All right. So you want to find the potential energy at a point. Just swap the formula here. Half. So it's very much like this formula, but it's instead of A square, you put X square. So I just swap the formula here. Omega square times X square. So what the benefit of knowing this? If you did there 1 point and you calculate the kinetic energy at that point and the potential energy at that point and add it up, what you'd be getting is the total energy, which you could calculate by just using this formula. So if you feel like confirming, you can add the total energy, you can add the kinetic and potential energy at that point using that formula, and you'd be getting the same exact thing as if you did use the original total energy formula. Right. Let's take a short break and then come back. Right. But we just finished we basically finished talking about module 2 topics. Mhm. Mhm. All right, let's come back at 9:45. Mhm. Oh, all right, back. Mhm. Well, we did that. We did finish simple harmonic motion, right? Yeah, so finish simple harmonics. And so this question. Go back, go back. Go back. Chant really. Guys. Hold on, me. Go back. Guys.
Yes, sir.
All right, cool. All right, so let's go. Mhm. So this question, which of the following quantities does not remain constant? So does not remain constant when the particle moves in simple harmonic motion. So looking at them, total energy would just spend time spending on how it has to remain constant as long as frictional force is absent. The amplitude is constant and the angular frequency is constant. When them say angular frequency, that's the same as omega. And omega is 2 pi over t or 2 pi f, right? So the only thing here is force. Remember that the force increases as you increase the displacement. So we understand that. Very good. 29. A mass is attached to a wire.
Okay, after the question.
All right, I'm gonna go through. All right, so trust me, guys. After we finish this paper, it should be easier because we would have seen the topics. And I really just didn't want to go forward without going over some of the topics. And I already have the solution, so we can go through them. So we said that force is the only one that wouldn't remain constant. Because remember, as you increase the displacement, that force will increase to bring it back to equilibrium. That's the kind of thing there. And you understand it. Or even if you never fully understand it, you should have been able to figure this out because of how much buses on it a while ago. So that's the goal. Make you know enough, you can answer the question. All right. So come. Good. Look on the question now. This them love to come with. So you have a spring hung up and them say it's attached to a vertical helical distance m, no a, sorry, from an equilibrium as shown. The mass is released so that it oscillates with simple harmonic motion with an angular frequency of omega. So it's like the spring setup, you put the mass on it and then you pull it down. Them say displace it at distance a, and then you allow it to go back and forth in simple harmonic motion. So right here, when the mass on it like that, that would have been when it's at equilibrium position. But then you went forward and displaced it at distance a from EP and then released it, oscillate back in station. So they ask you, which of the following expressions gives the variation of velocity with time? So we can answer this. Yes, we can. Can we answer this? Can we? Let me move this. Well, understand where this is coming from?
Yes, sir.
Yes. If you don't sound excited, you're going to fall asleep. Well, works for me. This, so we know that this is omega. Sorry, this is specifically representing maximum velocity. Because remember, omega A is maximum velocity. It says V equal V naught sine omega T. So the more you remember the stuff then. Once you remember that, this is a repeat question, by the way. So good. This now, look on this one. So a mass undergoes horizontal simple harmonic motion under the action of two springs. Don't get excited. Its execution of motion is this, or equation of motion rather is this, and its amplitude is A. So you just need to understand what they say. Let's reason that out. They gave the equation of its motion and its amplitude is A. Looking at this equation, what's the first thing that comes to mind? A is equal to omega squared times x. And we can see it looks like that. So this region here, we say negative 2k over m would be representing omega squared in this scenario, because this is two springs. So it makes sense, and it actually does, because remember, say one spring omega squared is k over m. So since it's two springs, it's 2k over m. So that's how them get that, right? So they end up in negative 2k over m to represent the omega squared there. So how that relate to price? What is the maximum kinetic energy? We know that kinetic energy max. How you find it again? First, remember that kinetic energy is half mv squared. And v squared in simple harmonic motion is omega squared times a squared minus x squared. X squared going to be 0. That cancels out, so you end up with omega squared a squared, right? And the thing to remember, you look at your options and you realize, well, when I have something will look like this. Of course, it never that easy. So when you realize omega squared is equal to negative 2k over m. So you're going to put that in your formula. Half m 2k over m, and then you want to say a squared. And you cancel stuff. Realize 2's can cancel. Our m's can cancel too. So you end up with what? Kinetic energy being Ka squared. So even though you know the formula in your head for total kinetic energy, you realize them twist it up a little in this scenario. And now you know what two springs look like in a kinetic energy sense. We okay? Quick feedback?
Yes, sir.
All right, good, good. So the fixed points, you realize reach question 30, what that mean? Module 3. So, I have to talk about module 3. Module 3 won't go too deep. I have this here. All right. So module 3, but I really want you guys to get your full marks on module 3 now, because module 3 have a couple topics so weird, but I can show you enough to make you understand it. Trust me. Like thermodynamics and them stuff, they just need to know the formulas. So the fixed point of the thermodynamic scale. So first of all, temperature has the ability to feel heat. That's how they define it. And heat is transferred from a region of higher temperature to a region of colder temperature. Very important. You have these quantities, right, that are able to be proportionally affected by temperature. So when temperature changes, these quantities get affected. These quantities include volume, resistance, EMF, and what the last one? Is that all of it? I feel like one more missing. All right, we'll go with that for now.
Air pressure.
I feel, yeah, there's a constant volume gas thermometer, I know, but that's still volume in a way. No, it's pressure for real. Facts, pressure. It's a, and yeah, that's gonna make sense, so we'll get there. So, right, pressure. Very good. It makes sense. So these four values, they're called thermometric properties. Thermometric, they have a metric relationship with temperature. They're related to temperature. And we use these thermometric properties to create thermometers because we like to do things. And what them says, all right, you see, because temperature affected by volume or vice versa, by Charles' law, and we need to understand that. When you have increased temperature, and we're going to go deeper into this, increased temperature has an effect on the total internal energy in a system. Because you're going to see that those two things are directly proportional. I can probably show you it right now. Watch this. When you increase temperature on a body, what it actually does, or when you add heat to something simply, it increases the total internal energy in the body. And total internal energy is proportional to the average kinetic energy in the body. So these are relationships we have to appreciate. Let me do it the other way around. This is good. When you increase temperature, you increase your total energy. Some of that energy is kinetic energy, so you increase kinetic energy. When you increase kinetic energy, you're going to have increase in velocity. Therefore, you're increasing in collisions. This is what chemistry has been stressing when it comes to the collision theory. Increase temperature, increase total internal energy. Therefore, you increase the kinetic energy in the system and therefore increase the velocity of the bodies so they hit each other more. And this relationship is very important for module 3. So why I'm bringing it up here? Because when you increase temperature, increase U, increase KE, increase velocity, what gonna happen in the system is that because they're colliding more, they're going to increase in volume. And by increasing in volume, you realize the relationship temperature has on volume. Temperature increase volume. That's some more if I understand stuff, right? Increase kinetic energy, increase velocity, increase volume. And you're soon going to see a formula that makes a relationship between these two variables. That's why I'm going to appreciate this. Temperature is proportional to total internal energy, which is proportional to the average kinetic energy in the system. Increase temperature, increase the total energy. Therefore, you increase your average kinetic energy. Just remember that, please. But it's going to make more sense as we go along. And so let me say now. So we understand why volume is directly related. What about resistance? Especially for if it's a metal. So what we use is a platinum resistance thermometer, platinum the metal. When metals get warm, the electrons start to move up more and they collide more, and that resistance therefore increase, because resistance is resistance to flow. When you have more electrons colliding, more resistance. So increase temperature, increase resistance, easy. What about electro EMF? You don't do this yet, but basically when you have a potential difference is due to a difference in the amount of electrons being passed from one point to another. That's literally what it is, because electrons carry current. So you have that potential difference based on the amount of electrons going from one place to the other. So what happens is that when you have a temperature in a particular area, the temperature promotes the electrons to move to one place more than another. And then that causes the EMF. You don't need to overthink this until you reach unit 2. But EMF related to temperature, there's actually a law called Seebeck law about that. And then you have pressure. More temperature, more collisions, more force per unit area, more pressure. It makes sense, right? So those are thermometric properties. And in terms of thermometers, what the volume will do, it creates the classical mercury thermometer. Because what them actually do is then put a volume of mercury in the tube, and then the mercury will go up a particular distance. That's why you see the mercury thermometer have a distance on it, not a volume, because it'll go up a particular distance. But it's a volume of mercury that they're manipulating. We still with me? We still with me?
Yes, sir.
Right, good. Make sure you follow. And then this now, as I said, this is something called a platinum resistance thermometer. Very good thermometer. I feel like I need to be showing you something more, cause what them love to ask about for thermometers, them love to ask advantages and disadvantages. So I'm going to show some of them in. I need to show you that, cause they love to ask it. I don't want to go to the book to show you it. So just let me know if you understand it. But we're going to see that soon. So the platinum resistance thermometer, and then the EMF is something called the thermocouple, Trustill thermocouple. Very useful for small areas and stuff. So I'm going to talk about each of them. And then you have the constant volume gas thermometer. Why it's a constant volume is because you need the volume to be constant so that only pressure is being affected by the temperature. That's why it's a constant volume gas thermometer. So let me just rush through pros and cons. So types of thermometers, with the first one I look on the liquid thing with volume. So liquid thermometers, the thing about liquid thermometers, you need to have a fixed point. Thermometers in general need to have fixed points. It's very important. So they need to have a melting point and a boiling point kind of setup. And there's a problem to that, because guess what? So let me just try make you understand this properly. So this is what we just talked about a while ago on the different thermometric properties. When you talk about measuring temperature, so you have these instruments to measure the temperature, right? But when you talk about measuring temperature, you have these scales of measuring the temperature, scales. So getting into the instruments soon. But in terms of the scales, is that they're measuring temperature in Celsius, Fahrenheit, or Kelvin. Now there's a disadvantage to doing it in Kelvin and Fahrenheit. The disadvantage is that you have to use melting point and boiling point of a liquid. And those things are subjected to change, because if the liquid is impure versus pure, that can affect its melting and boiling point. So that is not as accurate. But then you have this Kelvin scale. The Kelvin scale different, because the Kelvin scale relies on a principle that's, so it's over there, but I'm going to show you right here instead. The Kelvin scale relies on a principle that we learned from the gas laws. The Kelvin scale relies on the fact that for every gas, because it uses a gas, it's a gas thermometer usually use a Kelvin, and we're going to talk more about that. What it relies on is that for every gas, no matter what type of gas it is, hydrogen, helium, lithium, beryllium, no matter what type, every gas is going to make a graph like this, where if you're plotting a graph of volume versus temperature of the gas, every gas will have a zero volume at a temperature, a set temperature called the absolute temperature. And that temperature we know is the negative 273.15 degrees Celsius. Every gas, when it reaches that temperature, there's no more volume. Because what happens is that when you reach that point, you get so cold that everything squeezes up together and it no longer taking up any more volume. Because remember, say heat make you spread and then cold make you come together. So it makes sense. And then the Kelvin scale takes advantage of that. So there's a word that they love to use, and they used it in the question a while ago. Thermodynamic scale. Thermodynamic scale, because it depends on thermodynamic properties. The fact that you have to, when the volume of every gas must reach zero at negative 273. So they can plot a graph like this and determine its corresponding values with temperatures. That's what they do. This scale is the best scale for determining temperatures because it's not affected by other things, right? And one more thing to add, the only thermometer up here that actually really follows the Kelvin thing is the pressure one. So going to thermometers, we said the volume one is mercury, resistance is platinum, EMF is thermocouple. Then you have this pressure one called the constant volume gas thermometer, where you keep the volume constant so that you're only looking at relationship between gas temperature, the temperature of the gas, and the pressure. So just those two variables, temperature and pressure, right? And it's the constant volume gas thermometer that obeys the Kelvin system of the thermodynamic. So it's the world-class thermometer, basically. It's the gold standard. It's the one that follows thermodynamic scale because it uses gas, and every gas comes at zero at negative 273. Am I making sense? Am I making sense? So the MCQ types, come on. Am I making sense?
Yes, sir.
All right, fair. So what else we need to know from this? We said that already. So me tell you already said the Fahrenheit scale and the Celsius scale is flawed because even though it I use two fixed points, it's not very reliable, but well, quote unquote reliable, but it's not very reliable because water can be affected. Thermodynamic scale is more reliable. It's a scientific measurement. It doesn't depend on any property. It only works on the fact that all gases have zero at the same temperature, -273, right? And what about it now in terms of so the question we did just get was asking about its fixed points. So just like how the Celsius and Kelvin scale, the Celsius and Fahrenheit scale had fixed points, boiling and melting point of water. This have a fixed point as well. Just swat it. It's the absolute zero, which would be the lower fixed point, and then the triple point. Honestly, I don't fully understand what they mean by the triple point in terms of the math side of it. Physics-wise, I guess what they're saying is that the triple point is a point when the gas exists as both, well, when the substance exists as a solid, liquid, and a gas. But it's at a temperature of 273.1. So it's the exact opposite of the absolute zero. And they said they do this so that you could have an even 100 scale. I don't want to overthink that. Not important. But this is what the question just asked you a while ago. So the question said, the fixed point in the thermodynamics temperature scale is identified by the absolute zero and the triple point. Where the rest of the question? But it's the absolute zero and the triple point. All right, we'll go. All right, let's stay there. So, all right, so that's so here's this formula not as important. I've never seen it used. If we see it, we'll come back to it. We'll show you the formula you need to know. This formula. All right, guys. You want a free mark? This is the formula to remember. Every year. So I told you that we had the 4 thermometric properties. Thermometric property related to temperature. Now there's a formula that we can use to find a temperature at a thermometric property. So just imagine, so we never have a thermometer and we did just know, say, oh, the pressure at this when it was that temperature, or the volume at this when it was that temperature, or whatever is this when it was that temperature. You could actually use that thermometric property where you just get and determine the unknown temperature where you try to find. And that's where this formula comes in. So what it says is the unknown temperature would be equal to the thermometric property at that unknown temperature minus the thermometric property at 0. Then you're going to say over the thermometric property at 100 minus the thermometric property at 0 again. So it's everything subtracting 0. So 2 big values, subtract 0 out of it, and then you multiply by 100. This is foolproof. And this works with everyone. So let's say you're doing thermocouple. Instead of X here, because this is a liquid one, so it's distance without go here. If it was a thermocouple with EMF, you'd put EMF here. So it would be the EMF at the unknown temperature minus the EMF at 0. EMF at 100 minus EMF at 0. And the graph looks like this. So you have temperature versus the thermometric property. So the thermometric property would correspond to a particular temperature. So if you know the thermometric property, you want to find the particular temperature, that's the formula up there. We good? We good? We good? Good. We good, guys? Well, I need to show you the advantages and disadvantages now. All right, advantages. The thermocouple main advantage is that it's well, not thermocouple. Start from beginning. Mercury and the liquid stuff. So mercury, we have to remember is that if it's a metal, so this is how remember the advantages. The key advantages you want is if something is able to have a wide range, so that would be important. If it can respond quick to changes in temperature, and you can think about affordability and things like that. Wide range is usually with the metal stuff, so like the platinum resistance thermometer, and also the constant volume gas thermometer. The one with the widest range is the constant volume gas thermometer. But in terms of the mercury liquid, the reason why some respond quickly is because of the idea of specific heat capacity. Because imagine if you had determined temperature and you is a metal yourself, as a metal, you are gonna absorb some of the heat. So what happens is that if you have a specific heat capacity, which means you'll take up a lot of heat in order to have your temperature change or rise by a kilogram, it means you're not gonna respond quickly. So some of these have a low specific heat capacity, so it don't respond quickly to changes in temperature. Low specific heat capacity means high specific heat capacity rather means it requires a lot of heat energy in order to rise its temperature by a kilogram. That's what the specific heat capacity tell you. Amount of energy to rise its temperature. That's specific heat capacity. So that would affect when it's a quick responding thing. So summarizing, the thermocouple is the one that you have the best. The thermocouple is the one that have the best in quick response. Quick response, you think thermocouple. Wide range, you're going to think about your platinum resistance thermometer, or you can think about the constant volume gas thermometer. There's one about a geologist. The geologist use a thermocouple. A question about geologists, he use a thermocouple. Even though some resources just say about platinum resistance, but I'm gonna go with thermocouple. Because the thermocouple is beneficial. It can go in a small places. And as we say, it adjusts to rapidly changing temperatures, like underground. Right? I hope you guys following me. So I'm just telling you the stuff is them there. Which next? So thermometers wise, we should be good. All right, so what is now? Two bodies when in equilibrium will have the same temperature. It's the idea of when you're so hot and you're so cold. This will move weird. So when one place hot and one place cold, heat are gonna travel from the hot place to the cold place until eventually everything is at thermal equilibrium. Right? This so as I said, specific heat capacity is the heat energy required to raise 1 kilogram of a substance by 1 Kelvin, right? You can use that to find out the unknown specific heat capacity of another substance. So read this question. The temperature of a 50-gram liquid was raised by 60 Kelvin when it is used to cool a steel ball of mass 100 grams. So it's like them put container and then put in steel and the steel hot. And then them have the liquid in there with cool. So the principle is that the heat lost from the steel bar is going to be equivalent to the heat gained by the water. So the heat loss would be equal to the heat gain. And if you want to find change in heat energy, is always MCAT. That's the best formula. Change in heat energy is MCAT, mass times specific heat capacity times delta T. So we say, all right, the so on one side here, I find the heat change from the liquid. So it's a 50, notice I convert it to kilograms. And I get its specific heat capacity, did I? No. So this is the unknown specific heat capacity. And then it have a temperature change, they tell us. Not yet. Go and break at 11. And then this is the mass for the other one. This is its specific heat capacity, and it transpose to find C. When you do that, you get the answer as 1,200. You guys get that? We get it?
Yes, sir.
Yeah, as in try to work it out, you know, because but you try to work it out and see it. Trust me. Right, I don't think you're gonna remember this, but by the time you reach 2019, you're not remembering this. So work it out. So once you transpose, you get it 1,200. That. So that's a method where them can use. You can use this method to find the unknown specific heat capacity of a substance by pouring another substance on it so that it can transfer its heat into it. And then you know that each change is equal. So this other thing now, conductivity. Easy. Remember you have three methods of heat transfer: conduction, convection, radiation, and formulas for two of them. So for conduction, the formula is, follow me. The formula in terms of amount of energy passing through the substance per unit time, which is the same as power. Keep that in mind. That rate of change of energy through it is going to be equal to the thermal conductivity coefficient K. It's a negative here. Going to be A, the proportional to area as well. And then you have a gradient of temperature over length. This is a formula, good formula. In this question, them say I have a brick wall of 10 meters long, 4 meters high, insulated by a material of thermal conductivity this. And you see K, you see when K larger, the larger the K is the greater the amount of heat transfer, which means the metals have a greater K than non-metals, aka insulators. So this is good because when you look at a K value, you're supposed to can guess if it's going to be a good conductor or a bad conductor. If you see a small K value, it means it have a small amount of rate of flow, bad conductor, insulator type things, right? So just make sure you can plug that in the formula. Or you find the area 10 times 4, say would I get this times that. Did I work it out? Or just transpose the formula first so that you can see what's going on. So we're transposing for what? What did they ask us for? Insulating. And this is key. Notice so one side is here. So a brick wall 10 meters long, insulated by a material of thermal conductivity that. So this is the wall and then wrap it around in the material. And then the material is this thick. So I guess this is the material. Maybe the wall is on the inside. Yeah. So this is the material and it's this thick. And then interface between the wall and the material is 95 degrees. So this is the wall where the material insulate, and this is the insulator, and then 95 degrees right here. And then outside would that be a different temperature, hopefully a cooler temperature, suggesting that you're not allowing heat to flow through quickly, right? Because an insulator, that would be a bad job. What I'm trying to say is that this thickness here is representing the length that it travels, because this here is a temperature gradient with respect to length. So the temperature difference that occurs over the length that it's conducting across. So conduction is occurring through its thickness, and you're gonna have a difference in temperature across that length. Very important. And you plug that in the formula. Yeah, try find. So I did do it like this. Yeah, try find T2. So I transpose. And I bring over this. So you get 30 minus. When I do all of this, all of this turned out to be 30, and then minus 95 from it, which was what the initial thing is. And that gives you negative 65 equal negative T2. Negatives cancel. That the temperature is 65 degrees. Work it out yourself. Trust me. All right, guys, we okay? Still going? Hmm? Hmm? Yeah? No? Mm-hmm. All right, cool. Good. Let's go. So that's make sure you work that out, because when you're in an exam problem, so make sure you work that out yourself. You see how I get it and work it out yourself. This type of question. Base SI units, and I should know base SI units work. First thing, what is specific heat capacity? It's the amount of somebody tell me quick. Where's my phone? Hey guys, remember also keep in mind we don't have a lot of time. So that's why I kind of push it. If you're not willing to stay up, we'll stay up. And as I said, the recording won't be available. So let's push as much as we can. After the first paper, it should get a lot easier. I said this from experience. Somebody telling me the base SI unit? As in what specific key capacity is? Sending out message. All right, come in. Heat required to increase the temperature of a substance by 1 kilogram. All right, so there's something I want to clarify. Change in temperature. I want you to see that change in temperature is not affected by the SI unit. Let's say I had the temperature of 25 degrees. Put it in Kelvin. 25 degrees in Kelvin is about, okay, add 273 to it, you'd get about 298. 0 degrees in Kelvin is about 273. When you subtract that from each other, you get 25 degrees. If you were to do that in Celsius, so it's 25 minus 0, you still get 25 degrees. So most of these formulas, because MCAT that's in it, and CAT is the delta T is saying change in temperature. Change in temperature is unaffected by the SI unit. So that's why you see them put Kelvin sometime and then put Celsius sometime, because as you can see, if you're subtracting a Kelvin or degrees, it doesn't matter. You still end up with a difference between the two values. So I hope that makes sense, right? So it's joules, the amount of energy per kilogram per Kelvin. or Celsius. So they have it in Kelvin. So what is joules now? Love this type of question. Joules is energy, right? Energy is force times distance. That's how you remember that. And I'll just rub out this down here. Why I'm going like that is because I want you to remember this. This is kilogram and this is Kelvin. So energy is force times distance, generally speaking, work done. And force, it would be mass times acceleration. So newtons is just the fancy way of saying kilogram meters per second square, right? We know that, right? CSEC, we know that though. Kilogram meters per second square. So let me write that properly. We know that, we're good. Guys, mass times acceleration, kilogram meters per second square. And then you're going to multiply by that distance over there right there. What I try to do is find the SI units. So it's joules per kilograms per Kelvin. Joules is energy, that's force times distance. So it's kilogram meters per second square. In times by distance, so you get kilogram. So you should remember this off your head. Energy represented the SI unit is kilograms meter square per second square. Force is kilogram meter per second square. But when you put energy in the mix, you're adding one more distance. And then you're saying divided by, which is the same as multiply by 1 over kilogram and Kelvin. And then you're going to break it down. So you cancel out the kilograms. So you end up with m square per second square per Kelvin. Both, right? Well, follow me? Guys? Guys? Need feedback? Guys? Guys?
Yes, sir.
Come guys, remember. This, so we're good on this. All right, now move them. You have several SI unit type questions. There shouldn't be a problem for you. It's usually the same things again and again. Remember, so force is kilogram meters per second square, and you know why. Energy is kilogram meter square per second square, and you just have sense when you do it. Simple. So you don't second guess them question, and you know you have to get it right. This now, some formulas. So there's some formulas I want you to remember. I'm just going to write them up in the corner right here. So you remember who the gas law business. I want to start with this one. We're so done with formulas now, guys. We reached literally module 3, which means the hard part is over in terms of remembering stuff. It's just now for getting things out of the way. So this is the first formula. PV over T. Because what them do is say that since P1 times V1 was equal to K, and since V1 over T1 was equal to K, if you fuse them together, you get P1 times V1 over T1 equal to K. And that means in another situation, that is that. And this is a useful formula. And then you can say PV equal nRT. Good. Which other one? Suppose you try to find it with a number of molecules, capital N, like Avogadro's kind of thing. It would have be NKT, where K is the Boltzmann constant. 1.3 something, 38 times 10 to the whatever. Which one next? So there's this weird topic in module 3 where you have to make a formula for root mean square and all of them something there. So I'm gonna show you the simplified version. And I made a mnemonic today. So PV equal no miss. That's the mnemonic. No miss. Yeah, tell miss no. What do I mean by that? Right, I'm going to show you. PV equal no miss. You realize all of these are some PV variation business, so it's kind of sus. Guys, remember, give feedback so I can know that you're awake. I don't really want to be teaching myself. But why am I saying no miss for this? This formula is a wiki derivation, but just remember this formula. So N, call it no, and then M, call it miss. But you see, this here, this represents something called mean square speed. Mean square speed is, as the name suggests, it's so let's say I have several molecules bouncing together. That's what we're at when we look at this type of formula. When you look at this formula, this is formula when you're looking at deep to molecule level. And you're looking at the pressure and volume and all that stuff at the molecule level. And if you know the speed of all your molecules, and you say, all right, you square all of those speeds, and then you average those squares, that's what they call the mean square speed, as the name suggests. So that's how I made this mnemonic, no miss, where N is the number of molecules, like Avogadro's kind of thing. M is the mass of each molecules, and then this is mean square speed. So no miss. This is a good formula to keep in the back of your head. But even more good is this one. So remember, say, what is density? Mass over volume, right? So let's say you bring this under this. Number of molecules times the mass is going to give you the total mass of all of your molecules. So mass over volume is density. So let me write that properly. You have this more important formula. Pressure is equal to density times mean square speed. Not leaving out anything. Yeah, man, that formula is very important. And there are two more formulas, two more ideal gas formulas. Let's say I want to find and that's where this question comes, the energy of a single molecule, right? After this, I'm going to take a break, or no, when I finish the paper, then take a break, eat something, and then come back. I'm going to do that. As long as you guys hear it. If you want to find the kinetic energy of a single molecule, the formula is 3/2 kT. If you want to find the kinetic energy of all of the gas molecules, like that would be like your total energy in the system. Because here's the thing. When you look at molecules like in constant random motion, it's assumed that all of their energy is in the form of kinetic energy. So their internal energy, which is the sum of kinetic and potential, their total energy is only kinetic energy. That's what we get at with this. So I want you to see this. The total energy is equal to kinetic energy. Overall energy, if you want to calculate it, the formula is 3/2 nRT. And that's it. If you can commit these formulas to memory, you're not going to have a problem with that topic. We're good?
Yes, sir.
So let me be careful with something. There was something I wanted to say a while ago. Yes, I wanted to show you this relationship. Notice the kinetic energy is directly proportional to what? Temperature. The kinetic energy of a molecule is proportional to its temperature, and the kinetic energy is proportional to the internal energy. So when you heat up something, its kinetic energy rises and its internal energy rises. Those three things you need to connect in your head. All right, so remember these formulas. All right, drink some water. Try to take these formulas, please. Save yourself some stress.
Could you scroll back to question 33 before you leave?
No, I just drinking water, not really.
Okay.
No problem. So that scenario is when you want to find the unknown specific heat capacity. So you know the heat gain is the heat loss. And how you find heat transfer or heat change is MCAT. Mass times specific heat capacity times change in temperature. Delta is the weird letter. All right, so we basically finished most of module 3. The only thing left is to talk about law of thermodynamics. Well, say it in the group. Hey, never mind. Nicholas is okay with 10 o'clock. So 10 o'clock tomorrow, sharp. All right, so that we're good. Move on. Remember, ask questions, because this is how the rest of them stays. The same types of questions again and again and again. Some tricky, yes, and we try to work them out. But you have to understand it. So I'm hoping after this and have a strong foundation with the content. So tomorrow, but let's try to do as much as we can tonight. I want to stop at 2012. I'd like to stop at 2012, which is possible. So we're good?
Yes.
All right, so ready? You ready? All right, then could push through. So remember those formulas. This is literally all of the complicated formulas for that topic. Just remember them, or try to make mnemonics like I do. So with the question, the average kinetic energy of helium atoms. You see, from them I say where it's like average kinetic energy, and then you see them give you one type of atom. They're asking you for the kinetic energy of one atom of gas. That formula is which one again? Which one? Somebody tell me quick. Let me see if I can work it out.
PV equals 3/2 nRT.
Remember, we'll try to find energies at the end of it. So first, let's analyze which formula you gave me a while ago. Going again, when do we use these formulas? This first formula that I give you, so all of these are ideal gas formulas, whatever. And this first formula I give you is when you get a pressure, a volume, a temperature in one scenario, and then you get it in second, but you want to find one of the unknowns. You see these two formulas here, PV equal nRT and PV equal nKT. This is like when you get it in one scenario. So you get a pressure of a gas at a particular volume at a particular temperature. What is its number of moles? Or what is its volume? That kind of situation. And then PV equal nKT, what is its number of atoms? So you have to look out for the word atoms when you say N. And you know Avogadro's, we're going to use that. Trust me, we'll have a question to use that. This formula is kind of like you don't really use him a lot, but you want to have him in your memory. PV equal no miss. N, M, mean square speed, no miss. This one you use all the time. Pressure is equal to density times mean square speed. And then these two formulas. If you want to find the kinetic energy at one atom, it's going to be 3/2 kT. If you want to find the kinetic energy of all the atoms, it's 3/2 nRT. So how are we going to remember that? You notice this is a slight variation of these up here, where it's a PV equal nRT and PV equal nKT. It's basically a slight variation in a way. Just think about the K as saying one molecule. NK is just one molecule, but then the nRT is everybody. It's a bigger word. So Hope that helps. So the formula here would be 3/2 NK, 3/2 KT. So we need to use the Stefan's constant to do that. So you want to try this out. So it's 3/2, where, what will I say? 3/2 KT, not NKT. So you have to be careful with these formulas, very careful. 3/2 KT, 3/2 NRT. Two different formulas, two different responsibility. So K is 1.38. I don't remember what it's raised to the power of. There's a big value, negative value. And then you put it temperature. But you see that temperature here, you convert it in kelvins. So you have to add 273 to it. Yeah, try it. Let me find the value for the Stefan's constant. A Stefan's constant? A Stefan?
Oh, sorry.
No, I'm not Stefan. Stefan is the wrong person. What a K this stand for again? So much constants in the physics now. I think it's Boltzmann constant. Yeah, it's Boltzmann. Much constants. Guys, if you're feeling stressed, that's okay. If you need to take a break, take a break. Remember, we're not starting again until 4 o'clock tomorrow. So if you need to pause, pause. But I'm going to try, as long as people here, I want to try and cover the stuff because we don't have a lot of time. The Boltzmann constant is K. All right, so where is it? See it here, see it right here. 1.38 times 10 to negative 23. I should have guessed that because what name again? Avogadro's is 10 to negative 23 as well. So let's try that. Plug it in. So you get your card sheet. We'll get the answer. Anybody try it? Anybody try it? Guys? 27 plus 27315. I got it. I got 6.213 times 10 to negative 21 joules. So try it, guys. You need to try the stuff them. That's how you're gonna remember that. That's how you end up remember your values. So it become easier for swap them stuff here. So try it. So you know how to work it out. The formula is the average KE equals 3/2 and 3/2 KT. Very basic formula showing you that average kinetic energy is proportional to temperature. Everything else is like constant. Right up here. All right, moving on. Which of the following is not an assumption of the kinetic theory of gases? So what are the kinetic theory of gases assumptions? Anybody? Guys, anything? I really want to be teaching myself now, guys. That's the thing. As already a small group says that they can participate and like talk.
Collision between particles perfectly elastic.
Right, that is very true. I remember we did see the types of collisions earlier. So that was the first one. Very good. So first, and this is a chemistry thing. So if I remember correctly, so kinetic theory is about 4 of them, but collisions are perfectly elastic. And we said that the volume of space between collisions is infinite in comparison to the volume during collision, something like that, or duration during collision. And there's a constant random motion. So just looking at this now, we can easily spot the imposter. That's what we did. So a gas consists of large number of molecules. That's true. The gas molecules are in constant random motion, don't know. But they're not in inelastic collision. It's the opposite. It's elastic collision. So that's easy. Monoatomic gas, 18 degrees Celsius, pressure is given in a container of capacity 1 cubic meter. What is the approximate number of molecules? So clean, you look at what they give you to see what you need to do. You get temperature, you get pressure, you get volume, and you want to find number of molecules, N. If you know the formula, that's a click. So the problem with this topic, you have to remember transposing it, not transpose. You have to remember SI units, or you get knock. 18, you have to convert it to Kelvin. The Pascal already in Pascal, so that good. The volume is already in cubic meters, so that good as well. But just make sure you convert that into Kelvin, and you should get this. Easy. So try that when you get the time. Please try the questions. Or you're gonna see them and you're gonna feel like it's the first time. All right, so I'm moving forward. All right, so this now. So a little bit of thermodynamics. So thermodynamics actually pretty simple. It's literally the last hard topic in module 3. Once you get this, it's just using the information, hopefully. So thermodynamics states that the internal energy of a body is equal to the work done, the change in work done. So change in internal energy is equal to the change in work done plus the heat energy supplied to the system. Very important. You see work done now is either work can be done by the system. Always the work is done by the system. That means that the system do things. It have to be the one where I push. So just imagine like a cylinder now. And so this is top of the cylinder. And just imagine gas is inside cylinder. Very important. Gas is inside cylinder. When the gas itself is doing the work, it means that the gas have to push on the cylinder. So work is done by the cylinder. And if it's the gas that's exerting energy to do that work, that means the work done is going to be negative. Very important. So it's like that keyword too. You're looking for the word by. Once you see by, work done by the system, that means that the system after do it, negative. And also, if work is being done by the system, what you realize is that you have expansion because the system is now pushing it out so that you have a increase in volume. So you look out for things like work done by the system, you look out for negative work, and you look out for expansion so that you know that work is done by the system. Because that's going to affect the formula up here. Makes sense. And then when you work done on the system, it's the opposite. Because that's like somebody pushing on the system, positive work, you're giving the system energy there, so and you decrease its volume, you're compressing the system. Right? So the next thing there is you have to remember work done can be calculated using the formula pressure times change in volume. Reason being change in volume, what them they do is say, all right, let's say this is system, and let's say I had a change in distance as S as they push the thing back or forward, right? And what they do now, we say that firstly, wait, go again. Probably not important. Forget though. All right, let me see if I can like so it's not safe. So remember so force, and then you have that, and you have area. So what is pressure? Pressure is equal to force per unit area. And right. Again. All right, maybe not important. There's a derivation for this about it's in the book. If you want to see it, it's there. But just remember that work done is equal to the pressure during that work times the change in volume. So that is important. And then in the last thing in thermodynamics, you need to know is the graphs, then PV graphs. So you know your PV graphs is 4 types. Is either you have an iso, so pressure times volume. Iso means same. So you can have an isovolumetric graph where you have a constant volume. So what you have to think about is what happened to all your variables. Volume going to be 0. The work done is going to be equal to 0 as well. Why? Because there's no change in volume. There's no change in volume. So I should specify and say change in volume is 0. If there's no change in volume, there's no work done. There is a pressure that would be changing. Pressure is there. Pressure is doing pressure things. And right. That's basically how that would go. That's an isovolumetric. IV, isovolumetric, cause same volume. And then you can have an isobaric, where you have a same pressure because baric mean pressure. So isobaric look like this. Isobaric, same pressure. And in this case, you realize volume, there is a change in volume. Therefore, there is work being done. And that's that. You have something called isothermal. So this is usually cause problem. Isothermal versus adiabatic. Easy. What's the difference? And they did ask questions about this. Isothermal is when you have no temperature added. And if there is no change in temperature, there will be no change in the internal energy in the system, which we said was proportional to the average kinetic energy. So that's why I keep stressing that for this exact moment. To say change in temperature is proportional to internal energy in the system, which is proportional to average kinetic. So what I'm trying to say is that in this scenario, no temperature added. So the formula for the internal energy would look something like W equal Q, because U get knocked out, so the W carry over. So it would be look like this. This is important. And then the adiabatic is when you have no, so with an adiabatic, it would have no change in Q. There would be no heat supply to the system. No heat supply. So just imagine the formula like this, but then the heat supplied is 0. So it's something like this. And that's adiabatic. Both of these graphs kind of have a curvish like this. All right, so I can move to so I say thermodynamic. Do you have any question, guys? Remember this one, I get as much out as I remember, especially since it's being recorded, I can just go and finish hopefully as much as possible. But in the sense of teaching myself. And tomorrow I have to start late because I'm not going to be available until about 4. So just do after the. All right, so look at this. So that's information I know is enough for the paper one for thermodynamics, nothing else. So look at this PV graph. And they said the above PV graph represents a gas being taken through 3 processes. One, la la la, la 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 la. So them ask me, when is work being done on the system? So here's what you need to know. If work is done on the system, that means they have compression, right? That's when they have a decrease in volume because you have compressed the system. So always remember that cylinder. Always remember that like syringe kind of thing to help you remember on versus by. If work done on the system, you compress it. So what you expect is on the PV graph, you expect volume to be decreasing. So what I do, whenever you see the graph having a clockwise direction, so this is clockwise correspond to compression. And that compression will correspond to work being done on the system. Vice versa, if the graph is going in an anti-clockwise direction, make sure I'm doing the right way. Like it's going this direction, like it's want to go outward, that would be anti-clockwise. Anti-clockwise would suggest expansion, and therefore work done by the system. So you can look for the directions of the arrows to know if it's work done on or work done by. If it's work done on, you expect it to be going inwards, compression. So from 1 to 2 and from 2 to 3. So you look for that from 1 to 2 and from 2 to 3. Good. We okay? I think this is the coming up to last ones. Look at this PV graph. Notice the graph is having an overall which direction this is anti-clockwise. There's like an overall anti-clockwise motion you're seeing, because it's going outward, which means that overall you expect this graph to have a expansion occurring, work done by this system. So them little tips they can use to realize what the graph doing. So the question asks, an ideal gas initially at 2 meters cube and a pressure of that is taken through a cycle as shown above. So it was initially here and it pressurized and then it constant pressure and it go down isovolumetric, isobaric, make a constant cycle. And then they ask what is the work done on the gas in the complete cycle. So there are 2 ways to work out this. The area under the graph represents work done in this situation. So you could have said you would have do that now. So this is length times width. area done on the graph, under the graph, you would have subtract the 2 from the 8, so you get 6 times 10 to the, this look like 5. And then multiply that by 2 from the 10, so that's 8. And that would give you a difference to show you the area under the graph there. But you see the problem with doing it like that, you have to know, say, this is going to be a compression, because you see that it's going, not compression, sorry, expansion, because you see that it's going in the anti-clockwise direction. Clockwise would have been this way, anti-clockwise is this way. So when you work this out, your problem is now, should I pick the negative or should I pick the positive? Should I pick the negative or the positive? Oh, you know, since it's going in the anti-clockwise direction, overall, this is a expansion that is occurring. Going this way, expansion. Going this way, compression. Overall, this is expansion. That is compression. So another way to have done it would be to work out the changes in work at every given interval. So you can find the work occurring here. Work done in this region would have been 0 because it's an isovolumetric region. There's no change in volume. So no work here, no work here. You can find out what the work here is by saying pressure times the change in volume here. And then you'd find out what the work is here. Pressure times the change in volume. And remember, say you have to say final minus initial volume so that you can get the negative values, right? So this is going from 2 to 10. So the final volume would have been 10 and the initial volume is 2. This is going from 10 to 2. So the final volume is 2 and the initial volume is 10. And you put those in when you assess change in volume. And then that way you can find out accurately what the work done is. So you add up the work done in this situation and this situation. I hope I'm making sense, right? And it's going to be negative. Guys, you still with me? All right, I don't know if I should rush this and let's go take the break and then come back. Let's rush. But I would appreciate if we get some feedback though, because yeah. All right, so cube of side x, density dot, height dot, right? So a question like this now, this is all about Archimedes, but you're not to go that deep into it. A cube of side x, density dot below the surface. What is the pressure experienced by the bottom surface? So there are two formulas to must know, Archimedes wise. You have to know that up thrust is equal to weight of the fluid displaced. And that formula is found by saying density times volume times gravity, where density times volume is the same as mass. So this is kind of like mass times gravity. Density times volume is the same as mass because mass over volume is density, and the transpose, you get density times volume being mass. So this is the first formula to know. And then the second formula to know is the formula for pressure at any given depth. That one would be equal to density times gravity times height or depth. So if you want to find the pressure at a specific depth, this is the formula. So what did they do? So they want us to find it at the bottom. So you'd have to say density times gravity times depth, same formula. But at the bottom, it's height plus x. So that's what they did. Excellent. Young's modulus. You just have to remember the Flee mnemonic. Young's modulus is stress over strain. And when you put that together, you get Flee, FLA over E. And this question was interesting because they said you have a wire of length this and a uniform cross-sectional area that. So then get area, them get length, and then they asked to determine the Young's modulus. But they said the gradient of the force extension graph is that. So I'm gonna ask, what is the gradient of a force extension graph? So with me, guys? Yes. Spring constant. So that now you can use your brain now and say, all right, so that gradient of a force extension graph is the spring constant. So since that is spring constant, and you look in the formula, it's a force over extension in the FLE AE formula. So you can swap that in. So you just drop that into the formula, K, and then you end up with L over A. So that's how you end up calculate now the Young's modulus using this information given. So you have to be dynamic. If you use where you get, you plug it in and you get your answer. Good question. Strain is extension over length. Easy. What's happening here? Oh, this is a good question. Refers to. So this is like from SC2 string like this, say strings in series. But what you notice is that both of them have opposite or different spring constants, which means you have to draw for them formula they already say. So diagram has two strings in series and they have a mass on them of 0.8 newtons. And then they have them springs in series. They ask you for the total extension. Cool. So in my head, I would be thinking, all right, look at what I have to see so I can get what I need. They want a total extension. So in other words, they want the extension as a result of both of them put together. I realize that this is not a simple case where we can say, oh, the extension is going to be 2 times the initial extension. Because as I can see, both of them is different, 2 different springs. Therefore, that wouldn't apply. That rule of saying, oh, it's going to just double because you put 2 of them together. So less force per unit area, per unit extension, more stretchy. That not going to apply. So you have to do more work. So I'm going to think, I'm going to say, all right, when I have them, I know the spring constant for both of them. I can use that to find the overall spring constant of the spring. So do that. And when I do that, I get 0.7 newtons per meter. That's the overall spring constant for both of them. And if I have the overall spring constant and I have the overall weight force acting on them, I can solve the overall extension. And that's what I did. And I got 0.56 meters. Very good question. All right. So just use your brain and get through. This repeat question. So this is what it says, the brittle object. Brittle, very brittle. It's brittle and not as an axe, but this is one I want to memorize fully. The ductile object. And then this would be the plastic object. So see it there, brittle, ductile, polymorphic, or plastic, same logic, right? I'm going to label some stuff here. So, this color. You see, from here to here, the body is undergoing Hooke's law. This is a force extension graph, cool, Hooke's law. You'd also have a straight line on a stress versus strain graph. So it's like, in other words, it's kind of like Young's modulus is just like Hooke's law, but it's more, it's included other variables like stress and strain. But it's literally just like Hooke's law. Young's modulus is just like Hooke's law. It's the same type of graph, same everything. It's literally a knockoff of Hooke's law. But yeah, during this period, we have a proportional relationship. That would be when Hooke's law is obeyed. And then you have this point where you have something called the elasticity limit. Elasticity limit is the furthest point that you can pull the string with it being able to return back to its normal length. So everywhere before the elasticity limit, it can undergo elastic deformation. Keywords. Everywhere before it can deform elastically. It can stretch and go back. That's what happens. But once you pass the elastic limit, the next thing you see is something called what next? I think it's the yield point that is next. I think the yield point marks the beginning of when you have plastic deformation. Once you reach plastic deformation, there's no going back to its original length. So once you pass the yield point, that's it for that. And then you go up until you have this point right here. This point right here is called ultimate tensile strength. That's the maximum force that you can add to the string without it pop. Max. And then after you meet the ultimate tensile strength, for some reason, it will go down back until eventually it reaches the snap point, where it just snap. So these figures, you want to remember them name, just in case. So you have this is where Hooke's bar is obeyed. Then eventually you reach the elastic limit. Everywhere before the elastic limit is elastic deformation. And then you have the yield point. Everywhere after the yield point is plastic deformation. And then you have the ultimate tensile strength, tensile stress, where it ultimately are gonna reach max stress ever, and then eventually reach the snap point. That sounds like a bad story of somebody's life, but rough. Just snap your heel back. So that's that. That's it. So memorize those. I'm gonna take a break, eat something, and if you know guys up for it, we can continue. Like I said, we went through all of the topics then, so key is to kind of just see the questions and know it's a bit disheartening. So we're not gonna go people though, but hopefully people can watch this tomorrow. I don't know what's going to benefit. Maybe I just have to wait till tomorrow. But I can't do that because we have so much outstanding. Yeah, so I'm going to take a break and then come back and we can start. I'm going to continue up until 2011. And I hope to God people watch it tomorrow. All right, see you tomorrow. I'll come back.